class 12 is already full of organic chemistry. I have at least read GOC, so let me leave this hydrocarbon. If you are also thinking the same, then let me tell you one thing. Generally, one question you will get from hydrocarbon and the level and the concept that NTA generally ask from hydrocarbon is a very easy concept. So strategically, it will be a crime to leave such a easy question. Moreover, organic chemistry is a logical sequence. So if you jump a step, let's say you jump from step 1 to step 3, leaving this step 2, then it will always make you in a state where you are not that comfortable and you will end up saying, sir, I have to always cram organic chemistry. So in order to learn it logically, allow me to help you and make a quick revision of hydrocarbons, because I have personally given all the relevant details of reaction mechanism also, which will be helping you for your class 12th organic as well whenever hydrocarbons are required in those areas. Do not worry to write all these lecture notes, and I have personally selected all the relevant NTL logics for you, which you can obviously download all of them for free. From where? Just go to the link in the description section where you will land up with the amazing world of PW, which is also helping and guiding thousands of students like you to excel in their competitive journey. So let's begin. So to begin with, let us discuss the topics that are to be covered. So obviously hydrocarbons are carbons and hydrogen compounds. So they are basically, it is a combination of 4 chapters for us. The saturated hydrocarbon, that is alkanes, followed by alkenes and alkynes, the unsaturated hydrocarbons and relatively more reactive, and at last we'll be discussing about benzene and all the aromatic compounds, which are obviously hydrocarbons. Now obviously starting with the first chapter, which is alkanes. Now for every organic compound this will be our process, because NCERT also serves the chapter in such format and JEE also asked in the same manner. What? First, you are asked about their physical properties. You should know their physical properties, their nomenclature, the isomerism that they show. Isomerism and nomenclature we have already discussed in GOC, so obviously I'll be discussing some questions and will be revising all those concepts. But if you are very fresh, so I suggest you should go to our topic of GOC where I have discussed complete IUPAC and isomerism. Now after that, for every organic compound we'll be following this pattern. Their physical properties, post that their preparation, how are they formed, post that their chemical properties, and at last, if at all there are some important uses which are loved by JEE. And obviously NCERT also mentions some of the uses, because chemistry in everyday life chapter has been removed. So uses of organic compounds are also, sometimes they are also asked. So I'll be discussing all those relevant details. So starting with the physical properties of alkanes. Now alkanes we very well know by the name. They are also in Latin, they are also termed as paraffins. Para means little and affin means affinity. So because they are very little reactive because of presence of sp3 hybridized carbon chain. You'll say, sir, but it has C bond H. C bond H is practically non-polar. The electronegativity difference is so small that alkanes are least reactive. But if you try to be very violent with them at vigorous condition, they will also react. But obviously the number of reactions are very less, and therefore whatever reactions alkane undergoes, they are always at vigorous condition. So first talking about the physical properties. Now obviously we know alkanes are saturated single bonded carbon with general formula CnH2n plus 2. Now what about the physical state, sir? We know as carbon-carbon chain increases, what attraction forces they have? They have van der Waals forces of attraction, because they are non-polar molecules. But even non-polar molecules are attracted towards each other via instantaneous dipole-dipole attraction, which is known as van der Waals forces. Now, but sir, that means the van der Waals force is a very weak force. Yes. Therefore, till 4 carbon atoms, they exist as a gas in nature. What type of gas? A colorless and odorless gas. That means till butane. After butane, from 5 carbon chain to 17 carbon chain, because now carbon chain has been increased, even though the molecular force between one molecule and other molecule is just very weak, van der Waals force of attraction. But if carbon chain increases, this van der Waals force of attraction will increase. If this is increasing, then the constituent will try to be close to each other, and hence once carbon chain increases post 5 carbon at room temperature, they start existing as liquid, except one, that is neopentane. Neopentane still remain in gaseous state. Now, post 18 carbon atom, the chain becomes so large that even though the attraction force is weak van der Waals force of attraction, but still they start exist in solid state, and this is a solid like the wax you get. Rest all alkanes are practically colorless also. Now, sir, because they are organic compound, carbon is non-polar, so it will not like dissolves like is the rule of solubility. So they are insoluble in water, but soluble in non-polar solvents such as benzene, ether, chloroform. All these organic solvents, in them they are soluble, but they are practically insoluble in water. Now, and what can you say about the solubility? Obviously, in organic solvent also, if their carbon chain will increase, the solubility will keep on decreasing. So the solubility decreases with increase in size. Smaller molecules generally get dissolved easily, while bigger molecules, because bigger molecules are attracted to each other to a larger extent, therefore the solubility starts decreasing. These are some very basic facts. Moving forward, now this physical property is very important. The boiling point and melting point, as I have already discussed, as size increase, van der Waals forces of attraction increase. So if someone is going to ask you that, let's say this is a 4 carbon alkane, that is, this is the bond line formula of butane. What about this, sir? This is 1 2 3 4 5 6. So this is a 6 carbon butane. Sir, 6 is more, so because carbon chain is large, so van der Waals forces of attraction will be large. So as carbon chain increases, both melting and boiling point definitely increase. A very basic thing. But if you talk of isomeric alkanes, sir, isomeric alkanes will have same number of carbon chain. Now, as a branching increases, the molecules start to become compact, and because it has become a compact molecule, so one compact molecule with another compact molecule is going to have less surface area, and this surface area will allow them to have intermolecular force, which is weak van der Waals force of attraction, but that weak force also is happening to a lesser extent because surface area has been reduced. While if there is no branching, then at least those weak force lines can be larger in number. So as boiling point, as branching increases, they become compact, and because they become compact, so they are less attracted to their molecules of those type. So neopentane has the weakest boiling point, has the lowest boiling point, while normal pentane has the highest boiling point, and in between you will get isopentane. All these 5 carbon alkanes have same molecular formula but different structural formula, so they are obviously isomers of each other, and for isomers boiling point is inversely proportional to branching. Now general names are very important. So what is a normal alkane? When all carbons are aligned in a straight chain. What is an iso group? Iso is a picture, it is a photo, first carbon, second carbon and a methyl branch and its free valency. This picture is actually termed as, this photo is actually the name, the general name, which is iso. And after that what you have, because it is pentane, so you have to form 5 carbons, 3 are being utilized, so I have made 2 carbon chain. What is a neo group? Beside a tertiary carbon, if you have another carbon, then that carbon is known as neo group, and to that carbon if you add hydrogen, it becomes neopentane. So these all general names, I'm again saying IUPAC and all naming I have done in GOC, but all whatever is required I'm repeating that also. But for those who are starting exactly from zero, I suggest at least you go to GOC 1 and just revise few details about IUPAC, nomenclature and isomerism. Now moving ahead, the another physical property is, although I have mentioned about melting point, but what state of matter you melt? Sir, we melt a solid. So in solid state, actually that solid will be having higher melting point, which is having a better symmetry, because for solids only intermolecular forces of attraction, which are weak van der Waals forces of attraction, but only intermolecular forces of attraction does not govern the state of a solid. What is a better solid? Which is more symmetric, which has more effective packing. So for melting point, This is a rule that as carbon chain increase, melting point will increase. But with the values we have observed, and the observation is named as alternation effect. Now, what is alternation effect? This just statistically tells you that alkanes with even carbon, the alkanes having even number of carbon chain, because they are more symmetric, so it is observed that their melting point is relatively much higher. Now, sir, much higher as in they will not follow this trend that as carbon chain increase, melting point will increase. I'm not saying that, but their value will be much higher. So, for example, look at the example. Do not learn, but observe the trend. Normal propane has a, as in normal as in straight carbon chain. So 3 carbon lying on a straight chain is a propane. Normal propane has a melting point of 85.3. Normal butane has a melting point of 138. Carbon chain increase, so melting point increase. But look, observe the increment in melting point, sir, quite large. Now, moving forward, after butane you have pentane. What is the melting point of pentane? 143. Observe the difference. This is 138, this is 143. Just 4-5 rupees increment. Although there is an increment, but increment is small because pentane is a odd carbon chain. After pentane, reach hexane. Observe the increase, sir, it is around 180. 179. Now, after hexane, again you will have odd carbon chain, that is heptane. So for heptane, it is 180. It is somewhere around 180 to 185, just 4-5 rupees more. So what I'm saying is, if you have even number of carbon in your chain, then your melting point is relatively higher. Although the trend is not, I mean, this is not unjustified that as carbon chain increase, melting point is increasing. But observe the change of value. For even carbon, the increment is large. For odd, it is lesser. Now, at last, we all of us know this, all hydrocarbons, your oil, your kerosene, your petrol, all are just example of hydrocarbons. So all these hydrocarbons are lighter than water. But if you compare density of hydrocarbons, or as carbon chain will increase, density start increasing. But how you increase to whatever extent you want to increase, but that highest increased hydrocarbon will also be lighter than water, so their density will remain less than 1 gram per ml, which is density of water. So, but for hydrocarbons, among them density also increases as carbon chain increases. Now, let us, sir, we have discussed so many physical properties, so let us try some questions. Do JEE love physical property also? Let us see. Now, this is a JEE mains question, last year only. It says neopentane. Oh, sir, neopentane we have just seen. A tertiary carbon and a carbon next to tertiary carbon is a neo group because it's an alkane. So I'll attach hydrogen. Hydrogen I'm not showing. So this is neopentane. Neopentane forms only one substituted derivative. Only one substituted. Where substitution takes place? So C bond H is removed. So just check. Sir, there are 3 hydrogens, there are 3 hydrogens, there are 3 hydrogens, there are 3 hydrogens. If you remove any of the hydrogen, let's say remove hydrogen and add chlorine, so a substitution is taking place. Over here also, here also, here also, here also. If you take chlorine anywhere, the name will be same. So yes, this is right that neopentane when substituted will mono-substituted, as in from you remove one hydrogen, add one chlorine. So that is a mono-substituted product. So if you remove hydrogen from any of the above cases, sir, you will get the same product. So do we get only one mono-substituted derivative? Yes. So statement 1 is definitely right. Although this is a chemical property, because physical property are not much asked, but look at the statement, other statement. Melting point of neopentane is higher than normal pentane. Sir, for boiling point you said, over here you can see I've given this statement for boiling point, because for boiling one liquid molecule has to be closer to another liquid molecule, therefore surface area matters. But for solids, what is dominant? Sir, for solids their symmetry is dominant. Now you tell me which is more symmetric. If I compare neopentane, as in like this carbon having 1, 2, 3, 4, 4 CH3 groups. And what about normal pentane? Sir, normal pentane is this. Now you tell me which is more symmetric. Sir, this is more symmetric because with respect to this is a symmetrical system. This is with respect to this carbon, you have become a perfect tetrahedron. So because neopentane is more symmetric, so this is more symmetric, and more symmetrical arrangement is supposed to have an efficient packing. You have to remember this for each and every solids. So because it is more symmetric, so it will have higher melting point, and the statement is saying melting point of this neopentane is higher. So this statement is also correct. So your answer is both statements are correct. So option B, I've already given that answer. Moving forward, this quite old JEE-2004 question is also asking us the same thing, that you have to tell which is having the minimum boiling point. Now, this is butane, isobutane, butene and butane. Now, functional groups are not same. This is butene and this is butane. So remember one thing, we always compare boiling point of molecules whose masses are comparable. If masses are not comparable, then leave about their family. Leave about what functional group they have. 10 kg of anything will generally have a higher boiling point than 1 kg of any other thing, because generally more be the mass, so more will be the size. So whatever attraction I'll be having, that attraction will be larger. So in your questions also, the question is served you in such a way that you should have at least some common sense. And what common sense we can apply? Sir, intermolecular forces of attraction. But intermolecular forces of the attraction can only be compared for those species which are of comparable mass. Like for example over here, obviously these two have same molecular formula, which is C4H10, because both are alkane. But this is alkene, so this is C4H8. This is alkyne, so C4H6, but 2 hydrogen, 4 hydrogen difference. Hydrogen has negligible mass contribution, so we'll say that they have approximately equal mass. But now talking about their boiling points. So sir, for normal alkane and branching we already have done, because this is branch, so its boiling point will be lesser, and you are asked minimum boiling point. So among A and B, B will be your right answer. But sir, how to compare with alkene and alkyne? Now there's a catch. First, I'm giving you the common sense. Like take alkyne. What carbon alkyne has? Sir, alkyne has an sp hybridized carbon. So won't you feel that this sp hybridized carbon is electronegative? Sir, we know through periodic table its electronegativity is all more than nitrogen. On Pauling scale it is 3.25. So don't you feel this C bond H will be polar? This C bond C will be polar? Yes. So actually, because of polar nature of this sp hybridized carbon, the polarity of C bond H and this C and sp hybridized and sp3 hybridized C will also be high. So actually this will attain some polarity. If you compare it with an alkane, it is definitely quite polar molecule. And when one polar molecule is getting attracted with another polar molecule, the attraction force becomes dipole-dipole attraction. So because this is a polar molecule, so obviously it tends to have a stronger intermolecular forces of attraction. Therefore, obviously, although the question is done, because you were supposed to tell me the minimum boiling point. So who will have the minimum boiling point? Sir, you are saying they are polar, so polar molecule will also will only have higher boiling point, and we are supposed to tell minimum boiling point. So obviously they will win as compared to alkanes. So sir, and among them, if they win, so they are higher, so that is lower, and if that is lower, this is having the lower. So we got your answer. But if I'm giving you one step higher, a common sense, if I'm asking you to give me the order, so obviously alkyne being sp hybridized, this D will have the highest boiling point. Now, among butane and butene, so there's a experimental catch that slightly to a very slight bit, because butane is more symmetric. I mean, this is an experimental data which I'm telling you. So actually among butene, but1ene and butane should have whatever logic we have learned. So butane should have, but point is over here, butane wins the race and butene comes next. And the last will definitely be what we know. So for JEE mains, answer is done. But this is one step higher, one step more. I mean, it's an information which I'm giving you, that butane is having slightly higher boiling point than but-1-ene, but it is a practical fact moving forward. Now, next question, I said for IUPAC and isomerism, I'll give you appropriate questions. So this is a JEE mains question, 2024 question. So attempting it. Number of isomeric compounds. Okay, now including stereoisomers. Stereoisomers as in geometrical and optical also you have to see. But sir, alkanes can only show optical isomerism if their carbon is chiral. What is a chiral carbon? We'll see when you have an sp3 hybridized carbon having all 4 differently substituted bonds. And structural isomerisms, so they can show what type of structural isomerism? Chain and position. So let us try and draw all the possible structural isomers of 2-methyl butane. So butane is this is 2-methyl. So this is 2-methyl butane. And what I have to do with 2-methyl butane? You have to tell the total number of compounds formed by monochlorination. Now again, it is using a chemical property which we are just going to discuss, but because this much you know from class 10th, that's why I'm taking this question initially only. What is monochlorination? So substitute one hydrogen by chlorine. So number of products that you will get will be a mono substituted product. So let's say chlorine is added here or here. It will be same. What name will be coming? So let us revise those names also. So I just take this structure so that it can be used at least a few times. Then we'll see how many more we have to make. But for time being, I'm just making this much. Now, let's say chlorine coming over here. Name will be same. So let's say chlorine is coming over here. Let us find the names are 1, 2, 3, 4. So its name will be 1-chloro 2-methyl because C comes first. So it will be 1-chloro 2-methyl. And 4-carbon chain is butane. Similarly, what about this? Over here, chlorine is gone. Now, if chlorine is coming to this side, this will be another mono-substituted chloro product. So let us name it 1, 2, 3, 4. Its name will be, just the same. But obviously, you have chlorine branch at position 2. So it will be 2-chloro 2-methyl butane. Move again. So this will be structure number 1. This will be structure number 2. Both of them are position isomers because size of main chain is same. What is changing? The position of branch, that is chlorine. Now, sir, chlorine, these 2 positions we have taken into our consideration. If chlorine coming over here also taken, so chlorine can come over here or chlorine can come over here. Now let us check whether the name is different or not. For this one, from where you will number from that side, because 2 should be coming to chlorine because chlorine alphabetically starts with a C while methyl starts with an M. So name will be, I have to number from this side so that alphabetically chlorine, because starting from C should get the minimum number. This is rule of alphabetization of IUPAC. So this becomes our structure number 3. Name is 2-chloro 3-methyl butane. Now, what about this one? Sir, because chlorine, not because of alphabetization, by lowest location only, by lowest locant only, this is 1, this is 2, this is 3, this is 4. So name will be 1-chloro 3-methyl butane. Sir, any other option? No. So thank God we have made 4 structures only and we have got how many structural isomers? 4 structural isomers. But question is asking you to include stereoisomers. Now what type of isomerism alkanes can show? Alkanes can show conformational isomers also, but conformational isomers are not true. So what next? What type of other stereoisomers? Sir, optical isomers. But they can only show optical isomerism if they have a chiral carbon. What is a chiral carbon? An sp3 hybridized carbon with all 4 differently substituted carbon. So let us find a carbon whose all bonds are different. So for that, I am suggesting you to always, if a carbon is having more than 1 hydrogen, so obviously 2 bonds are same. So let us write hydrogens. This is H2. This is only 1 H. Okay, then let us check this carbon. 1 bond is methyl, 1 bond is hydrogen, 1 bond is this ethyl, and 1 bond is this CH2Cl. So yes, this becomes a chiral carbon. Moving forward, sir, this is CH3. This is CH3. This, okay, because this carbon has two CH3, so it cannot be chiral. This is CH2, this is CH3, so no chiral carbon. Over here, sir, CH3 rejected because it is having two CH3, so this is also rejected. Now, let us check this one. One is methyl, one is chlorine, one is this isopropyl group, and one will be hydrogen. Yes, this will also be chiral carbon. Moving ahead. No. For this one, it is having two methyl groups, so not a chiral carbon. H2, gone. So how many chiral carbon we have? This is a chiral carbon. So for optical isomers, one will be dextro, one will be levo, because we have counted one. So this will be either dextro-rotatory or levo-rotatory. So let's say this is dextro-rotatory, but you will have one more levo-rotatory compound. That will be, let's say, 4 I have counted. So that will be the fifth one. I'll mention it with different color. So this other rotatory compound will be the fifth one. What about this? Sir, because this is chiral, so this can be either dextro or levo. So let's say this is dextro. So the other, let's say this is dextro, the other levo one will be the next one. So 6. So how many structural isomers we had? 4. But because 2 of them having optical stereocenters, so they will be having their levo rotatory or other optical isomers also. So because we have counted 1, so they must be at least dextro levo. So one will be added. So for this one, I've added 1. For that one, I've added 1. So total isomers including stereoisomers will be 6. So your integer type answer will be 6. A very beautiful question, and again a very important practice for isomerism, IUPAC both. Now, so physical properties done. Coming to preparation of alkanes. Now, the very first reactant by which alkanes are prepared are alkyl halides. So capital A, because for E, now you have to make this thing very clear with yourself. What I'm for all those students who are actually starting from 0 and they are just only targeting mains, I am suggesting all should actually only target mains. But because mains also ask sometimes from a topic, they may ask a difficult question, and you may never know that in your set maybe that question, the topic which you have prepared, maybe a good question has come. But if at all you are finding it very difficult as in, sir, there is too much of information, I cannot even learn this much, why you are giving excess of information? So at least give us only that information which is quite only and only relevant for mains. So I have designed all of this lecture in such a way that I'll be telling you for each topic that for this topic you should know only this much, but I'll be discussing a bit further. But for all those who are feeling some pressure, what you can do is just learn those extra things by making a 2x speed, and but at least have a look at those stuff, because maybe in your particular set, from the chapter that we are doing, maybe you will get a good question, because advanced loves it and mains have a habit of asking good questions that has come in advance. So I'm including everything, but will be telling you that this is the part which you can leave. So I'll not be repeating this again and again. I'll be discussing some part, and to the other part I'll be saying this is extra. So whenever I will be writing extra, that means till this is the necessary basic condition, and mains generally has this basic condition only. But if it is asking basic condition, it is an easy type of question. And we also know 50 to 60% of the paper is easy, but 40% is not. But so for that, I will always be mentioning extra points about that topic. So I'll be segregating every topic like this, that till Roman number 1, how will you revise? That for this, Roman number 1 is this. Roman number 2, you can leave if you are falling short of time, because obviously you are, and if you are starting from 0, but it will be helping you. Sir, why it will be, you're wasting our time? Why it will be helping you? Somebody is hurting you this much, you will feel lot of uncomfortableness because of this. But if you have a bigger wound, this impact will not at all hamper to you. So I'm actually giving you some logics also, so that you will be feeling so much uncomfortable that this thing will be very easy for you. That you'll feel, oh, this much you have to see, okay, this is quite easy. So at least this much will become much easier for you. So moving ahead now. From the first method of preparation is from alkyl halides. So from alkyl halides, how it is formed? The first method by which from alkyl halide you can prepare alkane. So from alkyl halides also you can make alkanes by using different methods. So first method to form alkane from alkyl halide is by using reducing agent. Simply, alkyl halide is any alkyl group bonded with halogen. So this is an alkyl halide. When reacted with any reducing agent will form RH. What reducing agent do? It gives hydrogen. Reducing agent adds hydrogen. So this reducing agent will give hydrogen to this X also. So it is removed as HX. And because we are studying organic chemistry, so for R, you will getting an H and the product will be alkane. What is the most famous reducing agent? Zinc in dilute HCl. Because this is the reducing agent which NCERT mentions. So very, very, very important. Now, because we know, sir, this is common sense, dilute acid will give small number of H plus. So even if you use acetic acid although is a weak acid, but even you are using strong acid, the dilute version, so the number of hydrogen you need is not high. So that limited number of hydrogen can even be furnished by a weak acid. So acetic acid can also be used. Point is, zinc in presence of base also can do this. Next, if you take zinc copper couple, then even ethanol can be used to furnish those limited number of hydrogens. But obviously this first one that's why I've given it a different color, is the most important because NCERT mentioned this. So whenever you are supplied with an alkyl halide, zinc and acid do what? Zinc and acid attaches hydrogen, remove halogen, forms alkane with equal number of carbon atom. This is very important, you have to remember. With equal number of carbon atom, alkane is produced using zinc and acid. Now, this much you have to always remember. Now, some extra. So there are some other reducing agents also which can use this. Yes. Other reducing agents are also very famous, although there are n number of reducing agents, but some reducing agent I am giving you which are actually loved by good questions. So what are these other reducing agent? The first one is lithium aluminium hydride in presence of ether. LiLH4, but it has a trick. What trick? 1 degree alkyl halide as an halogen connected to a carbon which is directly connected to one carbon. 1 degree alkyl halide, remove bromine, add hydrogen. 2 degree alkyl halide, remove halogen, add hydrogen. So 1 degree and 2 degree will give you alkane just like that. But with 3 degree alkyl halide, instead of substitution, elimination takes place and you get an alkene. So this carbon, this bromine is removed, but over here this H also is removed. So here HBr will be removed, but H will be taken from the other carbon only. So because that carbon will give one H, this will give one bromine, so double bond will come between them and you will get a pi bond. So this is one step ahead thing. So lithium aluminum hydride also does this thing, but with 3 degree it forms alkene, not alkane. So there are some other reducing agent also. Yes, red phosphorus and HI heated at around 150 degrees Celsius. That will also serve the same purpose. Magnesium followed by, whenever in a question you get Roman number 1 and Roman number 2, that means first you react with this followed by this. I'm giving an example because this is also quite famous, although not this reducing agent is even there in NCERT, not in hydrocarbon but other areas. So this is also important, so also I'm giving you. Now for example, let's say I have this alkyl halide 2-chloroethane. Let's say it is getting reacted with magnesium in presence of ether. So generally metals are not reacted in presence of water, dry ether, as in there is presence of organic solvent. So magnesium is a bivalent atom. So what this bivalent atom do, it will come in between of all possible available electronegative atoms. So it will come in between this R and X and forms RMgX. This is the famous Grignard reagent. Now Roman number 1, as in first you react with magnesium and ether. This is formed. And after that you add water. So once you add water in Grignard reagent, as we have already discussed this, that magnesium is a highly electropositive metal. So this magnesium is satisfied with high electronegative chlorine. But if water is present, then magnesium will try to take OH from water. So here OH from water will be gone. So if OH gone, then what is left? H plus. So that H plus will go to this alkane. So you will get CH3, CH2, and the water solvent will give one hydrogen. So what have you got? Sir, again alkane. So ultimately what has happened? This R is given an H. So this Grignard, this magnesium followed by hydrolysis will also give you the same product which zinc in acid is giving you. Now, the third point, Roman number 3, is how this is taking place. Again, I marked it in extra. But again, I'm telling you why I'm telling this over here, because the Wurtz reaction, this mechanism will be helping you in mains question also. So let us see how it is happening. Actually, we know zinc is a metal. Sir, what does a metal do? We all know metal gives electron. How many electrons zinc can give? Sir, zinc can form +2 ion. So it will give 2 electron. By looking at these 2 electron, who will get the lalach, who will get the lust of seeing these 2 electron? Electronegative species. Among alkyl halide, who is electronegative? Halogen. So as halogen will see these electrons coming, these electrons will be taken. Obviously, first it will be taken by this halogen. This halogen will snatch this electron and form this minus. And initially, you will only get R radical. But once this R radical is formed, because there is excess of electron, because one zinc will give 2 electron, 1 electron has been taken up by this halogen. First this halogen will only take, because this is electronegative, but because 1 electron is remaining, so now this R will also say, this carbon will also say, that I will also take, because nobody is there to claim that 1 electron. So because halogen electronegative guy is already taken, so this carbon will also take that 1 electron and will form C minus. So, but why I have formed that radical first? Because you should know in presence of metal what intermediate is actually produced? Radical. And that radical further takes up electron and forms a carb anion. And this carb anion, because carbon is not an electronegative species, this carb anion can take H plus from even the solvent. So even a weak acid can give H plus, zinc in presence of weak acid, dilute HCl we say. So even this R minus can take that particular H plus from any weak acid and will form your desired product, which is alkane. Moving forward. So these alkyl halides can even be converted to higher alkanes by a very famous naming reaction called the Wurtz reaction. Now first is alkylides can form alkane of the form RH, having the same number of carbon atom as the parent alkyl halide. But from alkyl halides also, you through Wurtz reaction, which is you just use sodium, but again in presence of dry ether. Now the first point that I'm mentioning over here is whenever we use a metal, do not include water, because then water will be reacting with that metal only. So if you want that metal to react with organic compounds which are less reactive, at least do not involve any polar molecule. So when this alkyl halide reacts with sodium in presence of dry ether, you again get alkane. But what alkane? Higher alkane. So if the parent alkyl halide is having number of carbon R, it may be odd, it may be even. But the product that you are getting over here is that R is coupling with another R of the same type. So this will result to the formation of a symmetrical alkane, and it will always be an even number of carbon atoms. And hence it's a limitation of Wurtz reaction also. That you tell me what will be the smallest alkane possible. So smallest alkyl halide will be of 1 carbon. So smallest alkane produced will be ethane. So methane cannot be produced by Wurtz reaction, and any alkane with odd number of carbon atoms can also not be produced by a Wurtz reaction. But symmetrical alkanes can beautifully be produced, and very famous also. Like for example, let's say you have tertiary butyl chlorides, a tertiary group. We know tertiary carbon is that carbon which is directly attached with 3 carbons. Now, in order to make it 3°, I would at least be requiring 3 carbons. So this is tertiary butyl group, and to this free valency, if I add a chlorine, then this becomes a tertiary butyl chloride. Now, if it is reacted with sodium, then why I am taking 2 sodiums? Because one more molecule you will be requiring. So that one more molecule. And this box method will only tell you that what is going to be the product. 2 moles of NaCl will be removed if you react with sodium in presence of dry ether, and this guy, this R, will be directly attached with this R. So this R from first carbon, from the first alkyl group, and this R, so it will always be a symmetrical alkane. So this product will be produced, which is a symmetrical product. Now remember, in zinc and acid mechanism, now here mechanism for good questions is actually important, but this is the thing that everybody should know. Now talking about some extra stuff. So from Roman number 2, if you are finding it difficult, then you make 2x speed, else everything is important for good questions. Now talking about the mechanism, which is not also very difficult. What you have over here, sir, sodium, we already told that in presence of metal, free radical mechanism takes place. Why? Because metals are eagerly waiting to throw away their electron. Sodium acquire an oxidation state of +1, so will give out 1 electron. Zinc was giving 2, but it is giving limited electrons. Now this limited electron will be acquired by whom? Sir, by the electronegative species. So here X will be gaining this electron and will be removed in form of X minus. But this electron is only offered to the more electronegative atom. Sir, whenever metal is present, then what fission takes place? Homolysis. As in, halogen has taken its electron, taken an extra electron, and hence form halide ion. But this R has formed a free radical. That's why this is only was the case that I was telling you back with case of zinc, because there were 2 electrons. So that's why first over there also radical was formed, but it easily takes away that extra electron. But here stoichiometrically this electron is not available. So now this free radical, which is reactive, will try to stabilize itself. So many of these radicals will be created, and after that, after creation of so many radicals, this guy will think I'm very reactive. This guy will think I'm very reactive. So what they should do, they undergoes chain termination, because you are also reactive, unhappy. I am also unhappy, reactive. So let us rest in peace together. So this step is known as chain termination, and hence you get an higher alkane with double the carbons as present in initial alkyl halide. So this mechanism will also help you to predict some good questions. What questions are? Like for example, this is a limitation also. Suppose in the question you are given that methyl bromide is reacting with ethyl bromide in presence of sodium and dry ether. Sir, so now what is the problem? We know this. What you know? That one, this bond will also be broken. This bond will also be broken. Sodium will be taking these two Br. So 2 sodiums will be taking these 2 Br stoichiometrically. This radical and this radical will be undergoing chain termination, and I'm not denying to the fact that a higher alkane, which is propane, is produced, sir. But you said the limitation of this process is an odd number of carbons cannot be made. This is one of the product, not the only product. If you run an industry, you want the product to be obtained in a higher percentage. This is not the only product. This is one of the product. So there are various products which you were not even desiring. Hence the limitation is, if you get number of products, then such reactions you will not perform in industry because our efficiency of the reaction will be very less. So the limitation is, if you take different alkylides, then you get number of products. And many a times, I mean, in good questions, JEE has even asked that what are the possible products. So how will you estimate that possibility? By only knowing the mechanism. Now, because we know the mechanism, we know radicals have been formed. So if these two radicals have terminated the chain, then propane can be produced. And obviously, why I have written that product first? Because that will be produced in a relatively a larger amount. Why? Because this molecule will there, so possibility of methyl radical will be high. This molecule is there, so possibility of ethyl radical will be high. And when these radicals are high, they may chain terminate also. But I'm not saying this is the only product. What are the other possibility? Sir, methyl can also undergo chain termination. So ethane is also possible. Sir, ethyl radical chain termination also possible. So this ethyl group, ethyl radical termination will give you butane. So these are the possible products through the dimerization. Now, sir, what about this? A very beautiful common sense which you can only digest once you know mechanism. Now, if you have ethyl radical, let us look at that ethyl radical. So C2H5 radical is what? Sir, it is this CH2 radical connected with this CH3. Now, if this ethyl was chain terminating with another ethyl, then dimerization would have taken place. But what is disproportionation? If hydrogen, what disproportion is when oxidation and reduction happening simultaneously. If I remove hydrogen from you, you are getting oxidized. And if I add that hydrogen to another species, that is getting reduced. For example, if this guy, okay, I just showed this hydrogen separately. If this guy again undergoes homolysis, it can, because sodium is still present. So if it undergoes homolysis, then this H radical will be removed. This carbon will form a free radical. So this CH2, which is newly formed, this CH2, which is already having this radical. So can't these radicals undergo chain termination? Yes, because they are in-house only. So they will be more inclined to each other. So this can also be formed. Sir, but if it is formed, then this hydrogen must also have got that free radical. Yes. So when you were predicting that dimerization, when one ethyl was approached by another ethyl, so let's say that ethyl is also approaching. So if that ethyl is approaching and this H radical meets that ethyl radical is approaching, and if this H radical meets that ethyl, then they can form C2H6. So when one ethyl radical is approached by another ethyl radical, they can dimerize also, but they can undergo disproportionation also. Why I'm saying disproportionation? Because to one ethyl radical, hydrogen is getting added, so it becomes the reduced product. And this guy has lost one hydrogen, so removal of hydrogen is called oxidation. So to these two ethyl radicals, what has happened? They may dimerize as well. I'm not denying to the fact that these all are the possible products. Hence, percentage of one product is obviously less, because other will also take some percentage. And therefore, a mixture of product can be formed is the disadvantage of Wurtz reaction if you use different alkylides. And if you use same alkyl halide, then you will always get even number of carbon in the product alkane with symmetrical alkanes as your major product. So limitation of Wurtz reaction is you cannot use mixture of alkyl halides because they result in mixture of product. Now, because you have, I'm giving you, I mean, this is also some extra thing, but this detail is also there in NCERT in alkyl halides chapter, but this logic is coming from here only, so I'm offering it over here only, which is, sir, homolysis is a very drastic reaction. So actually we are talking of alkyl halide, not aryl halide. Why not aryl halide? Because through the chapter of GOC we already know that this lone pair of chlorine is under resonance with whole of the benzene ring. Now because of resonance, this bond will attain a partial double bond character, because in the resonating structures you will get bond order 2 also. So sir, if bond order is increased, bond length is decreased and bond becomes strong. So normal alkyl halide can be broken easily. But aryl halides, the bond order is high, and due to this partial double bond character, generally whatever reactions of an alkyl halide exist, those reaction will not be given by any aromatic halides, aryl halides. Therefore, I have given the formation of alkanes via alkyl halide, not aromatic halides. But here I am telling you that if homolysis is taking place, then homolysis doesn't even care whether you are a strong bond or you are a weak bond, because in presence of metals are very reactive. They are just giving away their electrons like freebies. So this sodium will still give electron, which will still be attained by this chlorine. No matter this bond is strong, still I will lure this chlorine, the electron will lure this chlorine, and there will be formation of phenyl free radical. So this phenyl free radical and this phenyl free radical will also in the similar fashion undergo chain termination. So all alkyl halide does not react, all aryl halide does not react as alkyl halide, but over here even aryl halides undergo homolysis and forms a similar product as alkyl halides, and over here what is forming in that case? Biphenyl. Obviously this reaction was certified by a scientist, and hence it is also a different scientist, and this reaction is called Fittig reaction. Sir, so Wurtz thought alkyl halide do it, Fittig proved aryl halide can also do it, so they came in collaboration. And the next reaction is also a naming reaction, which is Wurtz-Fittig reaction, is saying that aryl halide can be mixed with alkyl halide, and in presence of dry ether, what will be the major product? The major product will be alkyl benzene, because cross product generally is the major product. Although in industry many products can also be formed, but we are not running an industry, we are giving JEE examination. So in JEE examination, what product is R? If only one product is asked, although mixture is produced, then you have to give the answer as the major product. So what is the major product? Generally cross product is the major product, because you will say, na, sir, RR can also dimerize, benzene can also dimerize, but which product generally dominates and becomes the major product? The cross product. So alkyl benzene becomes your major product for Wurtz-Fittig reaction. Moving forward. So further, taking inspiration from Fittig, Ullmann came up with a similar reaction but with different metal, that is copper. Ullmann concluded that you can even form biphenyl extending the concept of Fittig but using different metal, which was copper. Students miss, so I'm giving you a trick. Ullmann, U, so Cu. So Ullmann is also the Fittig product, the mechanism, everything same, and results to formation of biphenyl. And Franklin copied Wurtz and said even sodium can do this with any of the alkyl halide and forms just higher alkane as that of Wurtz reaction. These two naming reactions are also famous, have been asked by JEE, so giving them also. But now summing it up for you, for those who are feeling not comfortable that sir you have given so many logics, so I'm summing up all the important summary of whatever we have learned. We have just done one preparation of alkane, that is from alkyl halide. What you should definitely know is when this alkyl halide is reacted with sodium and ether, it forms higher alkane of the form RR. So this is your R. So what you will get? You will get your beautiful butane. But when it reacts with zinc and acid, so it is just a reduction where you will get same number of carbon. So the same number of carbon will achieve that hydrogen from zinc. This you have to remember moving forward to the second preparation. First is from alkyl halide, second is simply from hydrocarbon, which you know from class 10th. From another hydrocarbon, that is from unsaturated hydrocarbons, because they like alkene and alkyne. What do we do with them? We do catalytic hydrogenation, because normally hydrogen is very unreactive. So how you make that hydrogen reactive, how you increase its reactivity? By using catalyst. So dihydrogen gas adds to alkene also and alkynes also. How? Using presence of finely divided, as in crushed, because if you crush the metals, the surface area increases. As the surface area increases, they absorb the gases on them. They absorb the hydrogen gas, the alkynes, the alkenes on them. What is process of adsorption? Suppose you want to hit some opponent of yours and you are not able to hit him, then you can ask your friend to adsorb that person. Adsorption as in they will, on the surface they will be stuck. So let's say you have a friend, he will stuck the hands of your opponent, so now you can have a clear picture, a clear view, a clear orientation for the attack. So when metal surface is offered, they adsorb the gases on their surface so that a clear picture can be given to another molecule, so that they are in proper inclination from each other, properly aligned, and this process is called activating the reactants. So who activate the reactants? Solid catalyst. What are famous solid catalyst? Nickel, platinum and palladium. So using them you can do hydrogenation, as an addition of hydrogen to unsaturated hydrocarbons. But yes, one extra information is platinum and palladium. With platinum and palladium, the reaction even takes place at room temperature because they are more strong catalyst. While with nickel, you have to increase the pressure and temperature, because the activity, the level to which nickel catalyzes the reaction is not so large, so temperature and pressure has to be applied so that hydrogenation takes place. This is an extra logic, this is an extra information which I am giving you. Now rest, it is very simple. Let's say you have an alkene. What's the simplest alkene? Ethene. General name is ethylene. It undergoes hydrogenation, but with nickel you have to heat, you have to apply pressure and temperature. Hydrogen will get activated, gets add up, and what you get is simple alkane of the similar carbon atoms. What about platinum and palladium? Because they have larger activity, so the reaction can even take place at room temperature. So let's say now I have an alkyne. What alkyne? But2-ine. No matter whatever carbons you have, they will get saturated. So what you form is a beautiful butane. You know this from class 10th. Now, a bit of extra information. Just like catalytic hydrogenation, nickel, platinum, palladium, even Rene nickel. Now, Rene nickel is actually an alloy of aluminum and nickel in the presence of NaOH. That is, that catalyst is known as Rene nickel, which also activate the catalytic action of nickel, and therefore the reaction is even taking place at room temperature. So what takes place? What we know, that is hydrogenation. The simplest alkyne is of 2 carbon, C ethyne, but general name of ethyne is acetylene. These general names are also very important. That's why these examples I'm giving you. So acetylene undergoes dehydrogenation. It will form what? Sir, it will also form alkane. Simple. Now, the extra Rene nickel is some extra information I'm giving you. Now, actually, what process is hydrogenation. It is a syn addition. Now when alkene or any unsaturated compound undergoes addition, those added species can be added on opposite places. That addition is called anti-addition, but they can even be added from same side. Now the logic which I'm giving you, if added atoms are very small, like hydrogen is very small, so hydrogen can be added from the same side. Such addition is called syn addition. How it is getting added? Sir, when the catalyst is used, hydrogen will get activated, alkene will get activated, proper inclination will take place because they are adsorbed by metal, so they are properly oriented. The pi bond will be breaking and this new bond will be forming, and if you use any of the catalytic reagents, the catalyst, hydrogen, heat, you get your product, which is alkane. So this is your simple hydrogenation. Moving forward, so moving to the third and last preparation of alkanes, that is from carboxylic acid. Now from carboxylic acid, they can be formed by two types. Both these types are mentioned in NCERT, so very important. First one is very simple, soda lime decarboxylation. Now what is decarboxylation? If you have carboxylic acid, D as in removal, carboxylation as in CO2 group. So if you remove CO2 group from carboxylic acid, you can form alkanes. Now how to do it? The first is soda lime decarboxylation. Soda is definitely NaOH, lime is CaO. They are used in the ratio 3:1 because actually NaOH, the soda part, is the actual reactant, while lime is calcium oxide. Lime is just used as a catalyst. Actually, its requirement is, because we definitely know sodium is a very reactive species. So sir, NaOH is also very reactive. So you want NaOH to react with organic compound. So if they get traces of water, sir, but do not put water. But NaOH nature is, it is highly hygroscopic. What is hygroscopic? If you will not add water, even if there is presence of moisture, so hygroscopic substances are those who even absorb moisture, and if NaOH absorb moisture, it will react with water. If it will react with water, which is a polar molecule, it will leave this organic compound, and if it is left, then we are proceeding for reaction of organic compound. So in order to keep the mixture dry, so that no moisture may also not interfere, that's why we use lime. Lime is not used for any reaction per se, essentially. So they are used in the ratio 3:1. And in order to keep the mixture dry, we also heat the system. We heat till a temperature of 630 Kelvin, but you can forget the temperature. So heated lime will keep the mixture dry. Now how soda reacts? So sodium is a base, but who you react with? You react with sodium salt of carboxylic acid, any sodium salt of carboxylic acid. How decarboxylation takes place? Just the box method is going to help you with this. I just make it. How the reaction is carried out, sir? CO2 is removed. Sir, it is definitely removed, but it is removed in the form of Na2CO3. Na2CO3. So CO2 is removed in the form of Na2CO3. What you are left with this R and the hydrogen of the base. So what you form is a beautiful alkane, but look over one thing. Whatever number of carbon was present in carboxylic acid, you are forming an alkane with one carbon atom less, because it was having one more dose. So this carbon would also be included in the main chain. So whatever the number of carbons present in carboxylic acid, the alkane we produced through soda lime decarboxylation is one carbon shorter alkane. Now this is what you should definitely know as per your mains, but one extra thing I'm telling you, you can 2x speed. What is the mechanism for this? Actually, for some questions, if you are given 2 carboxylic acid and you are asked that which reacts faster, so for that you should know the mechanism. So it is nothing. What are we using? Sodium salt of carboxylic acid. So who will be the active ion? Sir, RCOO minus, because RCOO minus and Na plus will give you RCOO minus, because we are using sodium salt of carboxylic acid. And through GOC we can very well see that in presence of base, what happens is, sir, This CO2 is an acidic gas. So this oxygen undergoes resonance, and when electron is given to this carbon electron is gone to that alkyl group. What you got is R minus. R minus is nothing but a carb anion. And the moment you got CO2, that CO2 mixed with that CO2 gets mixed with NaOH and produces sodium carbonate, and whatever hydrogen has been produced will be given to this R minus, and this R minus, after taking that hydrogen, will form alkane with one carbon atom less. So if you have different carboxylic acid, then who will be reacting more? Whatever will be stabilizing this carbanion. What group stabilizes carbanion? We know through GOC, electron withdrawing groups. So if electron withdrawing group is there, carbanion will get stable. If electron donating groups are there, they'll get destable. I'm stopping over here because if you have seen GOC, I guess logic is clear to you now. So after this is the first method, which is called soda lime decarboxylation. The other method is called Kolbe's electrolytic method. What is electrolysis? You put a salt, put it in water, pass electricity. What product you get is a electrolysis product. So we need a salt. We are taking sodium or potassium salt of carboxylic acid, mixing it with water, passing current and forcing chemical reaction, which is a non-spontaneous chemical reaction, can be forced by passing electricity. So what you get is an electrolyzed product. Now for this we definitely have to go to the mechanism. That's why I've not written the product. So let us go to the mechanism. This is there in NCERT. Very, very, very important. Now let us do this logically. Sir, electrolysis, although this is water, I have made the setup. Now, sir, salt, okay, because water is not conducting, I need a salt. So what is the salt? Sir, RCOO minus and Na plus. If you connect a battery, the positive terminal of the battery connected to the electrode will become positively charged. Negative will become negatively charged. Plus will attract what? Sir, plus will attract negative ion. Negative ion out of this is what? Sir, RCOO minus. So this RCOO minus will try to move towards the positively charged electrode. What minus do? Sir, what flows? Electron flows. So this will try to give electron. So at positive electrode, what is happening? Electron giving nature is called oxidation. So over here, what is happening? Oxidation. The electrode at which oxidation takes place is known as anode. The electrode at which oxidation takes place is known as anode. So for an electrolytic cell, anode carries what charge? Positive charge. So let us find what product we are getting. So this RO minus is RCOO minus is giving electron. So let us give that electron. RC double bond O minus, because it is having excess of electron. So it will give this electron in this electrode. So let us donate that electron. So when this oxygen is giving out that extra electron given. So it was initially, because it was having this extra electron, so it must be having complete octet. But because it has lost one electron, so one of the paired electron, this green, let's say this green colored electron, is given out. So this green colored electron is now an odd electron. Sir, oxygen is a very electronegative atom, but it has got an odd electron. So what it will try? It will try to force this carbon to undergo homolysis. Because if this carbon will get an odd electron, then it can satisfy the more electronegative oxygen. And who governs the world? The strong people. So because carbon is, this alkyl group is less electronegative, so it has to lose its electron and the homolysis will take place. So this homolysis will do what? This carbon is having double bond, a single bond with this oxygen. This oxygen is having its odd electron. This carbon has recently produced an odd electron. Why? To satisfy this electronegative oxygen. What is formed? Sir, CO2. Yes, it will be linear, but I'm trying to show you the mechanism. And what is left behind? this R radical. So this carbons becomes a free radical, just like Wurtz reaction. In a reaction, number of molecules will be there, so another molecule will also come, release CO2 and form R radical. So this R radical with that another R radical will do what? Will do chain termination and will form a alkane. So what is the product? Alkane. But what alkane? Whatever carbon was present on carboxylic acid parent chain, reduce one carbon, because one carbon is removed, decarboxylation in the form of CO2. Now double the carbons. So alkane is produced of the form RR at anode. What gas is produced at anode? Sir, CO2 is produced at anode. Sir, what about the other electrode? Let us move to the other electrode. Over here, oxidation is taking place. So over here, what will take place? Reduction. The electrode at which reduction takes place is known as cathode. So what are the product of electrolysis at cathode? So there is competition. There will be competition between whom? Between Na plus. But sir, why there will be competition? I do not see any positive ion. Go to your chemical bonding logic. Sodium is a metal, an alkali metal. It wants to stay in Na plus position because it is having a stable octet. So why it will try to change its octet? So actually, because Na plus aqueous is quite stable with respect to whom? With respect to water. In electrochemistry, we will see this in more proper detail, but I guess this common sense will definitely there also. It will be initiating from the logic of chemical bonding, that Na plus is a stable species. Why? Because its octet is complete. So why it will try to gain electron? Rather, if it is having another species, so another species will win the race of getting reduced at cathode. This is called competitive electron transfer. Two people are running, so who will win the race? Who is having more potential? So water is having a higher potential to undergo reduction. Now what is a reduction? You have to gain electron, because this electron has been lost. So if this electron is lost, somebody has to gain this electron. So who will gain this electron? Water. There will be a competition between Na plus and water. So water wins the race and will gain the electron. Who among water, who inside water will have a tendency to gain electron, which is in positive oxidation state? Who is present in positive oxidation state? Sir, hydrogen is in +1 state, oxygen is in -2 state. Minus minus repel each other, so this H plus will gain that electron. So hydrogen from +1 state will reach what? To its most stable state, which is 0. So H plus will form hydrogen gas. Now, I am not saying water is an electrolyte, but once hydrogen present in water has been removed in the form of hydrogen gas, then through equilibrium we know H2O gives H plus and OH minus ion to a very negligible extent. But even if out of crore of molecules, one H plus has been present in equilibrium, that H plus is removed. Why? It forms hydrogen gas. To that equilibrium, product is removed. So product removed, so equilibrium will be shifting to forward direction. So 1 H plus will be getting removed and equilibrium will be shifting to forward direction. So if H plus is removed, what is remained in the solution? Sir, OH minus. So that OH minus present in aqueous solution will be joining the party with Na plus and the product will be NaOH. So at electrode, pH of the solution at the electrodes at the cathode side, pH of the solution will be getting increased because base is produced. So base increases pH. These all are some good questions which are theoretically asked. Although I am iterating everything, but you should at least know this much of knowledge. What knowledge, sir? You have increased so much of information. Now let me summarize. So if you are having sodium or potassium salt of carboxylic acid, so water will also act as a reactant and will undergo electrolysis. So what products are formed? Now Products are R bond R and CO2. These are formed at anode, while hydrogen gas and NaOH, these are produced at cathode. This much, even if you know, is more than sufficient. Now, applying this logic, this common sense over here. Okay, now this is a good question, but I'll be coming back to this question, but let me summarize this for you, what you should know as per mains. Now, suppose you are given propanoic acid. Now, sir, acid, but these two decarboxylation reactions are of salts. So acid, because it is an acid, so acid reacts with metal also, acid reacts with base also. Do what? Forms salt, neutralization. Because acid plus metal forms salt, acid plus base can also form salt. So what salt? What acid? I have propanoic acid as in 3-carbon carboxylic acid. So what salt it will be forming? 3-carbon salt. So this will be sodium salt of propanoic acid. If it is undergoing electrolysis, CO2 is removed. What you will be getting? This R. But this R will be coupling with another R. So what product you will have? This R coupling with another R. So what will be IUPAC of B? It will be butane. But if it is undergoing soda-lime decarboxylation, then also CO2 is removed. Decarboxylation is happening. But over there, you get RH as alkane. So this is R. So you get to this carbon, you attach H. That means what is the product? Sir, product is ethane. So this is the basic point of difference that you know. Now, some good questions, how they are framed. If you know the mechanism, like for example, let's say now the question is saying that it is giving you succinic acid. Now, first you should know that general name. In carboxylic acid chapter, I'll be giving you some general names which are also famous in NCERT, but for time being, I'm telling you succinic acid is a 4-carbon carboxylic acid. And what type of carboxylic acid? Dicarboxylic acid. Okay, sir. So, sir, any acid reacts with metal, forms salt. So, both of them will form salt. So, let us form that salt. COONA. This guy will also form. So, this will be Ra, which is sodium salt of succinic acid, sodium succinate. Now, again, sir, you are doing electrolysis. So, we know what electrolysis will do. Electrolysis will, because that mechanism is even possible, is even given in NCERT. So for Kolbe electrolysis, you should know the mechanism. So this CO2 is removed. I get a free radical over here. This CO2 is also removed. I'll get a free radical over here. Now, if I have free radical in a similar molecule, then why I will go to another molecule for chain termination? Because now chain can be terminated in-house only. So what can be formed? Sir, this C single bonded with this C, because it is having radical, this guy is also having radical, so they will terminate chain. Obviously, there will be 2 hydrogens also. So what you have produced? Sir, we have beautifully created ethene. So if you know the common sense of mechanism, you can also obviously predict this. But sir, question is saying some is major product and you will also get a minor product of organic compound. What, sir? The dimer? No. I mean the one R with another R? No. Why? Because if one at both the carbon you have got free radical. So in both these carbons you have got radical. So when one radical will be approached by another radical, but radical will be there in both the carbon. So they will also try to do that. But once they do that, look at the chain termination. Sir, it has formed a cyclic compound, and cyclo compound attains Bayer strain. This carbon is tetrahedral, wants to be in 109 degree 28 minutes. But because I am forming cyclic compound, so I'll have some strain. So why will I work and form a compound which is not stable? So, but in organic chemistry, some pratishat of some percentage of everything will happen. So small percentage of the cyclic compound will also be producing, and it will be a minor product. But obviously, your major product will be this beautiful alkene. Moving forward, So just allow me to introduce this one more preparation of alkanes, that is from carbonyl compounds. Not there in NCERT in chapter of hydrocarbon, but it is there in carbonyl compounds. We'll be again discussing this in carbonyl compounds with more details regarding mechanism and every detail, because this is a loved topic by JEE Advanced also, but mains asked just this only. So because of this huge importance, I'm including here only, so you should remember this. You can also reduce carbonyl compound. What is a carbonyl compound? Aldehydes and ketones, the basic carbonyl compounds. This can be aliphatic also. This can be a benzene containing aromatic carbonyl compound also. So these carbonyl compounds, if sir we remove this oxygen, add hydrogen. So remove this oxygen, you will be adding hydrogen. It can be done, yes. It can be done by two beautiful reagents, and they are naming reaction. The first one is Clemmensen reduction, where you use an alloy of zinc and mercury called zinc amalgam in acidic medium, where this oxygen is removed as water and you get your alkane. Similarly, this other reduction is Wolff-Kishner reduction, doing the same thing, removing this oxygen and adding hydrogen. But here it is a two-step process. First, you react this carbonyl compound with hydrazine, and addition elimination takes place, and there only this oxygen is eliminated as water. And further, you boil it in ethylene glycol, basic solution of ethylene glycol. So this reagent you must remember, sir, you are not giving any mechanism, and in the backside you have given all mechanism. I will be giving this mechanism, but just this knowledge will be fetching you marks loved by JEE. See, this is a JEE 2024 question. It is just asking, this is a carbonyl group, zinc amalgam and HCl, the Clemmensen reduction. So this is a carbonyl group. This is a carbonyl group. What will happen to this carbonyl group? Benzene will remain as it is, because these Clemmensen and Wolff-Kishner reduction do not reduce. They do selective reduction of only the carbonyl group. So this carbonyl carbon will get reduced and you will get a methyl group over here. This will also get reduced and you will get CH2 attached with this one more carbon. So you will be getting an ethyl group over here. So this will be your product, was an option. Again, JEE 2021 question. This is converted to this, options were given and options were of the reagent. So this can be done by Clemmensen also, by Wolff-Kishner also. Why? Because just this carbonyl group is removed and we are having this CH2. The options of both Wolff-Kishner and Clemmensen were given in the question. Moving forward. So quickly moving to chemical reactions of alkanes. Now, as we have already mentioned this, that alkanes are paraffins. They are very least reactive. But if you are going after somebody with so much of aggression and vigorous condition, then everybody will break. So even alkane breaks, and the first and the very important reaction for alkanes are substitution reactions. Out of that, the hugely asked substitution reaction is halogenation. Remove one hydrogen, add halogen is a substitution reaction. But because NCERT mentions nitration and sulfonation also, although in just a line, but let us finish this less important, because you do not have to know much about them, because NCERT mentions it in a line. That's why I'm mentioning these substitution first, although the most famous substitution for halogens are for substitution for alkanes are halogenation, which we'll be doing definitely very properly, but just finishing in order to give courtesy to NCERT in line, that is, yes, alkanes can undergo substitution if NO2 is added to alkane, added as in hydrogen removed and NO2 added. The process is called nitration. And if sulfonic acid group gets substituted, then that process is called substitution. Coming to sulfonation first, because this is quite common sense. What is sulfonation? You have to add sulfonic acid group. So for an alkane who becomes relatively more reactive hydrogen, 3-degree hydrogen, as in hydrogen connected with a 3-degree carbon. So experimentally it is observed that While sulfonation 3 degree hydrogen is more reactive. So suppose I have this tertiary butyl butane undergoing sulfonation. What is reagent for sulfonation? Oleum. Oleum is fuming sulfuric acid, which is nothing but mixture of H2SO4 and SO3. So sometimes even it can be written as H2S2O7. It offers what? It offers sulfonic acid to the most preferably to the 3 degree hydrogen. So let's say remove this 3 degree hydrogen and replace it by sulfonic acid group. So what you will be having, sir? All 1 degree carbon will be less reactive, so will not be reacting. 3 degree will be getting substituted by what? By sulfonic acid group, which is nothing but this SO3H. That means, remember the structure of H2SO4? Sir, S double bond or double bond or double, then OH, one OH is missing. So that OH of this sulfonic acid group and that hydrogen of alkane will be beautifully producing water, and you get a sulfonic acid derivative of alkane. Coming to nitration, now as I've told you, alkane happens in very vigorous condition. This reagent itself is a very vigorous reagent because oleum is fuming as in extreme heated sulfuric acids, fuming sulfuric acid. So this reagent is itself very vigorous. How you nitrate any alkane? Normally alkanes never get nitration. You create vigorous condition. How you create that condition? By using a very concentrated nitric acid, that too at a very extreme heated level, a temperature of about 670 Kelvin. So at that particular temperature, whatever hydrogens you have, every hydrogen can be substituted. So what all possible mononitro isomers you can form, like for example, let's say over here, if this hydrogen or this hydrogen, if you remove any of one of them, NO2, it will be the same name. So what will be the first type of product? 1-nitropropane. If, sir, it is coming over here, then it will give you another product. So this can also be formed. So it will be 2-nitropropane. And because condition is vigorous, so even C bond C can break. So let us break, because we have to suggest all possible isomers. So now break 1 carbon. So broken 1 carbon, how many left? 2 carbons, sir. So if you have 2 carbon, what is the possibility of adding NO2? Sir, add here also, here also. Wherever you will add, you will get 1 nitroethane. But sir, condition is vigorous, so break one more. So if you break one more C bond C, how many bonds you will get, sir? Only 1 carbon. What is the possibility of substituting this carbon by 1 NO2? Sir, one possibility only. So it will be 1-nitromethane. Going to the more famous halogenation. So in order to understand halogenation of alkanes, let us go to class 10th basic, which we already know. Alkane, as in methane, reacts with halogen, as in X2, in presence of sunlight or high temperature, forms alkyl halide by substitution, and the hydrogen that is substituted also goes with another chlorine. Now, sir, if this alkane has got one hydrogen substituted, then other hydrogens can also get substituted. Yes. So if this methane is reacted with more number of chlorine, so substitution will be happening more number of times. So if one H is removed, then you got mono substituted product. You may also get di, tri or tetra substituted product similarly. But this is just a common sense of stoichiometry, that let's say if you have their molar ratio of 1:1, then who will be the major product? Sir, one mono substituted product. But if you will have excess of chlorine, then obviously what will be getting produced? Sir, mixture of mono, di, tri and tetra substituted products. Now this is just you have to know for mains. Now because mains have sometime asked, a bit of logic also sometimes. So I am discussing this to a higher detail. Why? Because it is somewhat there in NCERT also. Now, so in order to understand what is happening over here, just to make things clear, for mains point of view, what is if for during substitution as in halogenation of alkane, what becomes the major product? Monosubstituted product. For mains, you should just know this. But to know how it is formed and what will be the percentage of product produced, let us go to the mechanism now. The mechanism: in presence of sunlight, high temperature, what type of fission take place? Sir, homolytic fission. What is homolytic fission? Sir, two atoms take their electron and forms a intermediate which is called free radical. So who is getting dissociated? The first step of homolysis, homolytic fission, is known as chain initiation. First I need an attacking species, so attacking species created. Hence the reactivity of halogenation with alkanes will be depending on, sir, reactivity of X2. And because reactivity of X2, generally bond length decides, but because they are having lone pair, excess of lone pair, and fluorine, because of its smaller bond length, the lone pair repulsion will dominate. And because it dominates, therefore with mechanism we can say F2 reacts so violently, because in F2 the lone pair repulsion is not large, it is very large. It is a chemical bonding basic we have done. So for halogenation, fluorine is so violent that it is not considered industrially. So fluorination you will never find of alkanes because it is very violent. Now what is famous? Chlorination and bromination. For iodination I'll be talking. So chlorination, bromination are famous. So taking one of the example, let's say chlorine. So chlorine forms a radical. This is chain initiation. After that, sir, this free radical is reactive. Chlorine is an electronegative atom. It will try to attack another species. What is the species available? Sir, alkane. If it attacks an alkane, then homolysis of alkane also take place. Which bond gets easily broken? C bond H. So it can either couple with H, will form HCl, will create methyl radical. If it couples with CH3, forms the substituted product H radical. But over here, why I'm saying chain propagation? Because after formation of any product, the free radical is again produced. So this step is chain propagation. Now let's say I have 100 molecules of alkane, 100 molecules of Cl2. This will be happening. What product you will be getting? So in the second propagation step only, we are seeing that we will be ending up with monosubstituted product. Now after a time, its concentration will start to increase. Now if its concentration will start to increase, and let's say a chlorine radical is again coming to attack, but methane has been converted to this guy. So now this guy will start receiving the attack from what? From chlorine radical. But for that you need relatively larger number of chlorine radical. So sir, this can also undergo attack. So its hydrogen can also be homolytically broken. Yes, definitely. So let's say I'm just suggesting you the other possible radicals that can be created. So if chlorine radical will attack this guy, then what will be created? So that chlorine radical has snatched one more H. So this H gone in form of HCl. So again this radical. Now this radical can also undergo chain termination with chlorine, and you will result into the formation of di-substituted product. Similarly, to this di-substituted product, if chlorine radical attacks, will snatch one more H, you will get a radical over here. If that radical undergoes chain termination with another chlorine, you will get a tri-derivative, and similarly you can get tetra-derivative. So what I'm saying is, if you take excess of chlorine, then the probability of getting chlorine radicals will increase, and therefore in such cases, what product you report? Mixture of product. But in that case also, in the mixture of product also, relatively, although very to a minimum percentage, but who will be actually winning? The monosubstituted. So that's why I told you at first place, for mains, what will be your major product? Monosubstituted product. And after that, obviously, you can have the chain termination step, which can result in many number of products. Like in Wurtz reaction, we have already seen. Sir, let's say if there would have been chain of more carbons, so then radical would have came to that carbon. So in chain propagation step, just like Wurtz reaction, we have seen dimerization can also take place. That carbon-carbon radical can form higher alkane. Carbon-carbon radical can form higher alkane. Sir, over there we have seen disproportionation also, so that alkene formation may also take place. So what I'm saying is, because free radical takes place at extreme condition. What is extreme conditions? Are high temperature and sunlight photons are heavily energized. So at this extreme condition, radicals are produced, and whenever radicals are produced, number of mixture of products can be obtained, as we have already discussed a few in Wurtz reaction. So actually the limitation of such a reaction for producing what? For producing alkyl halide is industrially not good, because if you need mixture of product, then it is good, but if you need just one product, then the percentage of that product will not be that high, because mixture of products are produced. Now sir, one thing why I have given this graph is because the mechanism is free radical, although we are discussing it with a simple example of methane. But if we have some higher alkane, then sir, degree of free radical will also decide what product is formed, because through GOC we know this, that more stable intermediate is formed, and more stable intermediate has the capability to climb this activation energy barrier. So whoever intermediate is more stable will be actually having higher energy also, and will be actually getting formed. So whatever will be formed will ultimately result in the formation of product. So point is, why I have given this graph is because if somebody is going to ask you that you have a higher alkane, so in that higher alkane you will be having 1 degree carbon, 2 degree carbon, or 3 degree carbon. So the hydrogen attached with carbon will be substituted by what? By chlorine. If they get substituted, radical will come. So which radical will be most stable? 3 degree. So reactivity of 3 degree hydrogen will be highest, followed by 2 degree, and the minimum will be 1 degree. Mechanism is obviously homolytic fission. I have written that detail also. Coming to the reactivity, we already said reactivity depends upon lone pair repulsion in case of X2. So F2 is so violent that industrially we do not do fluorination, so you do not find fluorination questions. What comes next? Then Cl2 is reactive, then Br2 is reactive. I2, now with I2 you will say, sir, through chemical bonding we know bond energy of F2 is also less, but I2 is even lesser because its bond length is also high. What I am saying is, how the product will be formed? When you will climb this activation energy barrier. This activation energy barrier requires what? Requires extreme condition. What is the extreme condition? Sir, this takes place at high temperature and presence of sunlight. So that at extreme conditions, what product is formed? Sir, product formed is alkyl halide and HX. Ultimately, if it would have been alkyl iodide and HI, so don't you think at high temperature, because of high bond length, the product will also be broken and it will be coming back. So actually, in case of halogenation, iodination also is not seen, because this is such a slow and reversible process that it is largely shifted in backward direction, because HI and RI bonds gets broken at that high temperature. So this reaction is highly reversible. That's why industrially it is impractical to do it. So what is practical and what questions you get in your paper is chlorination and bromination. But as we said, which hydrogen reacts with faster reactivity? 3 degree. So let's say I'm chlorine radical, I'm attacking a 3 degree hydrogen. It will be reacting with a faster speed in comparison to 1 degree. But if chlorine is attacking, it will have a different sense of reactivity. So that sense of reactivity, the relative rate, the reactivity in case of chlorine is obviously higher for a 3 degree, for a 3 degree hydrogen. But it is higher in what ratio? Sir, when Cl2 will react, it will react with 3 degree hydrogen with a higher extent, followed by 2 degree, and the minimum it will react with 1 degree. So when experimentally it was observed, it was found that chlorine react with a reaction rate of 5 times with 3 degree, 3.8 times with 2 degree and 1 times with 1 degree. So if chlorine is reacting with a 1 degree hydrogen with a speed of 1 rupees, then with 3 degree hydrogen it will be reacting with a speed of 5 times more, that is 5 rupees. Talking about bromination now, it is an experimental data which for good question you should know, for mains you can leave this. Now for bromination, sir, with 1 degree hydrogen, if bromine is reacting with a speed of 1 rupees, then with 2 degree it will be reacting with a higher speed, but how much higher, sir? 82 times of 1 degree. And with 3 degree hydrogen, bromination reacts with a speed of 1600 times, so it is very high. Now, sir, why you are telling this? Because the product that you will be getting, the percentage of product will be depending upon both these things, the type of hydrogen and the number of hydrogen that that particular alkanes is containing. Like for example, I mean, it is a good logic, but giving you now, sir, alkane reacting with Cl2. So we know, because what product question is asking you, the product. So what becomes the major product, sir? Monosubstituted. But monosubstituted product also will be higher in number. Isomers will be formed. Why? Sir, let's say I have this carbon and this carbon. They both are 1 degree carbon. So their hydrogens will be 1 degree hydrogen. But this yellow, this orange guy, sir, this carbon is a 2 degree carbon. So its hydrogen will be 2 degree hydrogen. So if any of these 1 degree hydrogens are substituted and monochloro product is formed. Okay. How that product is going to look? Sir, we will be getting a chlorine here only, or here, there. It will be same. It will be 1 chloropropane. So let's say this product is A. But I can also have this possibility. Sorry. Which is 2 chloropropane. So this product is B. Sir, both are monosubstituted product. So which will be forming in larger percentage. Now, sir, you said 2 degree will be produced in a larger percentage. But now if the question is asking you, you give me the percentage. You will say, sir, percentage can only be determined through experiment. Experimental rate of reaction I have given you, na? Experimental rate of reaction, for good questions you should learn. That's why I have given you that data. Now, because let's say we remember that for chlorination, relative rate is for 2 degree, it is 3.8 times. So how many hydrogens are eagerly waiting to be reacting with this chlorine? 2 hydrogens. And both the 2 hydrogens will react with a rate of what? 3.8 times. So in order to calculate the amount of U produced, you have to multiply that experimental rate into the number of participants. How many participants we have? Sir, okay, I'm sorry. How many participants we have? Sir, for 2 degree hydrogen, we have 2 participants. So can you tell me what is the amount of B produced? Yes, because you experimentally know that for each 2 degree hydrogen, the relative rate is 3.8 times of 1 degree. And how many hydrogen are responsible for making this product? 2. So 3.8 into 2 becomes 7.6. Now, can you tell me the amount, the relative amount of this? Yes, sir, it is a 1 degree alkylide. So this 1 degree, how many hydrogens are willing to make this 1 degree alkylide? So 3. 3 plus 3, 6. And 1 degree hydrogen has a relative rate of what? Of 1 times. For bromination, it is 1 is to something 80 into something 1800. But for chlorine, it is quite compact, quite close. 1, 3.85. So what is the amount you got? 6. So how you will calculate? So total is this. Contribution of this one is 7.6. So its percentage will be 7.6 upon total. Total is, I guess, 13.6 into 100. This will give you the percentage of product produced, which over here, I guess it will be somewhere around 55%. So obviously this will be somewhere around 45%. But sir, we already know this is 2 degree. For some other, if you go to higher higher alkanes, mixture of product will be produced, mixture of 1 chloro. So for that particular type of questions, although advanced have asked those questions so many number of times, so how you can calculate? By multiplying the relative rate with the number of hydrogen. Do not blindly say that 2 degree will be formed in higher percentage. 2 degree is earning more, but the number of 2 degree members earning, let's say you have a family, one guy is earning 3.8 rupees, but that guy, how many type of that guy are present? Let's say 2. One guy is earning 1 rupee, but how many types of those people are there? Let's say 10 peoples. So 10 into 1 will become 10 then. So percentage of that particular product will be higher, although each hydrogen would be earning less, would be reacting with a lower percentage. So that is a I mean, that advanced have asked those questions so many number of times. This example is from NCERT. NCERT says that it is the major product, and because why it is major product? It is a 2 degree, but this 2 degree is becoming major product because its percentage is 55%, not that 90%. And how do we know its percentage is 55%? By experimentally knowing the data of the relative rate. Very good concept. Moving forward. So coming to what basic questions you should know. So discussing some, this is JEE 2023 mains question. Now, number of bromo derivatives obtained on treating ethane. Ethane as in 2 carbons. With excess of Br2. Excess of Br2 as an excess of halogen. Excess of halogen will produce all the possible substituted. Whatever hydrogen is there, all the possible hydrogens will get substituted. We just did that. See, JEE mains asked it. Now, plus Br2. But for this, you do not have to know mechanism. In the first slide only I have told you that if halogen are excess, then mixture of mono, di, tri, tetra, whatever hydrogen possible, all those isomers can be formed. Polyhalogen derivatives can be formed. So what you have to, okay, this is taking in place of sunlight. Now you have to tell the number of bromo derivatives. Now it is a permutation combination question. Sir, mono can also be formed, di, tri, over here more than tri. Why? Because how many hydrogens are there? 6. So you can substitute till 6 hydrogens because Br2 is in excess. So now it is a question of permutation combination. Chemistry is ended. So by doing that permutation combination with you, so let us practice this. Now let's say first let us check mono derivatives. Now this is, sir, remove any hydrogen. There is only one possibility. What possibility? This one. So this will be structure number 1 and this will be a mono product. Talking about the di substituted, now add one more bromine. So that bromine can be added here also, here also. So this can also be formed. But sir, you can add bromine in the same carbon also. So this will be structure number 2, this will be structure number 3. Any other possibility? No, sir. For di, we are also done. Let us count for tri. Now, let's say, now take the di and add bromine. So if I add bromine to this one, if I add bromine to this guy, what are the possibilities? Sir, you add here also, you add here also, IUPAC will be same. So there is only one possibility. So this becomes your structure number 4. Now, over here, sir, if I add bromine here, it will be same because 1 1 2 1 1 2 already done. If I add air, sir, then it will be different. So structure number 5 will be 1 bromine. I mean, I'm just drawing this one, and now if I draw here, this and this will be same. Do the IUPAC. So this there is only one possibility of adding over here. So this becomes your 5th structure. Moving forward, this is just permutation combination and you have to do it. There's no formula. This is common sense. Now come to, after tri, come to tetra. So tetra, add the 4th one in these two. So what about this one? Bromine can go here also. Bromine can come here also. So I just drag this structure because it is giving me 2 options. So let us draw those options. So bromine can be added here also and here also. So this will give us structure number 6. This will give us structure number 7. Now we have to use this also. Now if this is also substituted with the fourth one, sir, here there is no free valency. If you add here 3 and 1, 3 and 1, it will be the structure number 6 only. So not required, you will be giving me the same product, so you are not different isomer. So how many isomers we have found till now? 7, but we have reached till 4. 5 and 6 can also be added because you have hydrogens in ethane. You have how many hydrogens possible? 6. So how many substitutions are 6? So I guess now it is quite easy. What will be the 8th one? It will be having the 5th bromine. So there is no free valency, only this guy can have 1 bromine. So let me drag this one and let us give this guy the 5th bromine. What about this, sir? You will add here or there, anywhere you will add, you will get the same structure. So obviously the options has been, and the 9th will be when all the bromines are there, as in you'll add 1 more over here. I guess because we have reached till 6, so what will be our answer? Beautiful 9, but it will be requiring your common sense and your agility to know the logic. Chemistry ended over here. But once you know the logic, sometimes you have to do some hard work also in chemistry, also not only in maths. Now moving forward. So this was your JEE Mains, again a JEE Mains 2024 question. It says number of alkanes obtained on electrolysis. Okay, now it is preparation. So on electrolysis, as in Kolbe's electrolysis. So we remember, sir, this CO2 will be removed and this will give rise to CH3 radical. This CO2 will be removed and this will give rise to C2H5 radical. Sir, the major product will be cross product, CH3 and C2H5. So they will mix and they'll form propane. So they will mix and they will give rise to propane. It will be major product because cross product is always the major product. Why? Because its percentage will be high. So their collision will be high. Now, but what the question is asking you? Number of alkanes. It is not asking you the major product. So this is one of the alkane. Now you have to think of possibility. So when this will be attacking itself only, it will be ethane. So when this will attack itself, it will give ethane. When this will attack itself, it will give butane. So how many number of products we have? 3. So our answer is 3. Moving forward. Now, one thing I left, although this is also extra, so I've written extra also. We have spoken that F2 was very violent, but I2 is very slow. So this means that iodination you cannot do by any method. We are physical chemistry educated students. So we know Lee-Chatelier's principle, and Lee-Chatelier's principle says that if a reaction is moving forward to a very, very less extent, remember I told you it is highly reversible because these guys gets broken because bond length is very high. So reaction is not at all moving forward. So do we have any Lee-Chatelier principle logic? Yes. What if I remove the product? What if I remove the product? Sir, if you remove the product, equilibrium will be shifting to forward direction. Lee-Chatelier's principle. So, do I have an inorganic knowledge of removing HI? Yes. HI in HI, the oxidation state of iodine is -1. If I oxidize I minus to I2, then product will also be removed and I2 is acting as a reactant over here. So double Lee-Chatelier's principle, that is effect of concentration. If I remove product, reaction will move forward. If I add extra reactant, reaction will move forward double times. So if I use some oxidizing agents like HiO3, mercuric oxide and nitric acid, these are some, although this is a factual experimental fact, but even it was asked by JEE. Although good questions, but you should know, that's why it is extra also. So HiO3 being an oxidizing agent will oxidize Hi to I2. HNO3 will oxidize Hi to I2. HGO also oxidizes Hi, but actually it forms a solid of AgI2. So this is actually acid displacement reaction, because here oxidation state of mercury is +2 and over here also it is +2. So this is not actually redox, but because this is a solid, so this will get precipitated, and because it is getting precipitated, so Hi has been removed. So if Hi is removed, reaction will shift in forward direction, although over here I2 is not produced, so that double forward shifting is not done. And over here when HNO3 is used, I2 is produced, and HNO3 reduces itself to to NO2. And water is definitely, I mean, this is just inorganic knowledge, you can skip this also. So but this is all logic I have given you. Moving forward, yeah, so quickly moving to some other reactions of alkanes, and very easy and very important, because these now the remaining reactions are just NCERT fact. So the first one is combustion. From class 10th we know, so I'm going in a reverse direction. This we know from basic classes, that alkane CnH2n undergoes oxidation through stoichiometry, you can balance, and hydrocarbon always reacts with oxygen, as in they get combusted to form CO2 and H2, and it is highly exothermic reaction. All the LPG gas, the petroleum products that you use are just hydrocarbons, so their combustion is highly exothermic, is responsible for whatever energy we have around us. So the combustion famous reaction. Now the next thing you should know is, when your kitchen stove gives a different flame, generally it's a blue, it should be a blue flame, that is complete combustion is taking place. But if at all the pores in your kitchen, I mean the tabletop of your kitchen, the burner, if it is not giving a blue flame, that means oxygen is not sufficient. So point is, if you want to have a perfect combustion, then you need excess of oxygen. So if you limit the supply of oxygen, so incomplete combustion will take place, and the utensils will get black because of formation of unburned carbon, which is nothing but carbon black. But we use this also in our daily life. Whatever cartridges, black color ink we have is just this unburned carbon. And now coming to the actual, the logic that we will be using in other chapters also, that is, what is combustion? Sir, combustion is a reaction with oxygen. So how does hydrocarbon gets combusted? The common sense says every C bond H gets broken and replaced by OH. So let's say the understanding this from now, this we should definitely know. The basic alkane is a methane. Perfect, sir. Undergoes oxidation. Perfect, sir. Replace one C bond H by OH. This is what oxygen is doing. Replaced, what you get is a beautiful alcohol. So this becomes methyl alcohol. Now, with what this one oxygen remove, sir, the oxygen where it attacks, it again attacks with that in that particular carbon. So sir, this guy has 3 more hydrogens, so remove 1 more hydrogen. So this C bond H again becomes C bond OH. Now the first information which I'm giving you is a common sense also. Carbon, when connected with 2 electronegative oxygen, becomes very unstable. Why? Because this is also withdrawing, that is also withdrawing. So such a species, in order to stabilize, undergoes dehydration. So if this guy undergoes dehydration, that is, you have to remove a water molecule. So this H and OH becomes water. So what is the product? That's why I have not written any name. What is your product, friends? So I guess you can clearly see that I have this CH2 and this O will be double bonded with it. So CH2 double bonded O is nothing but it is HC double bond OH. Why I have written it like this? So that you can understand this is nothing but an aldehyde. So it forms a carbonyl compound. So if you make an alkane undergo oxidation step by step, complete oxidation is combustion, but step by step oxidation is actually a very useful tool for organic chemistry also and for life also. Ethane is just 2 carbon. Your LPG gas at home is mixture of butane and propane, as in 3 or 4 carbons. Let us suppose you have 2 carbon ethane. You can think of an ethane like that, your LPG gas. If you remove one hydrogen from ethane, it becomes ethanol, the famous liquor that whole world is crazy about. So what I'm trying to make you feel is addition of one oxygen does not make change the property, it completely transforms the property. Your maybe some smaller gas like the gas inside your cylinder, you can even see it, you can even drink it, you can even get high. So actually addition of these, I mean one oxygen change in a compound changes the property like anything which you can, obviously that's why they are known as functional groups. So what I'm trying to tell you is, even if you control this combustion, then controlled oxidized product will be commercially very, very useful. Hence, in organic chemistry, these questions are asked also, and they are very important also. Now, so first step oxidized product of alkane is an alcohol. Second step oxidized product is an aldehyde. Now, sir, whether still it has C bond H? Yes, this is also C bond H. So, sir, replace that also by OH. That is what I'm trying to do. So, this aldehyde, when reacts with oxygen, the last hydrogen also get replaced by OH. So, what you get is, let's say, I mean not the last one because it is having two. So the next one also get replaced by OH. What you get is a carboxylic acid. Sir, it can again happen. Yes. So because it is having one more hydrogen. So replace that also. Sir, but if I replace that also, then it will also become OH. I said one carbon attached with two OH makes it unstable. So what does it do to get stabilized? Dehydrates. So let's say, okay, I'll do it for you. One OH, another OH, this double bonded O. So in order to get stabilized, it will again undergo dehydration. Now I'm writing that water also because that is H2O. And what I am left with, C double bonded O and this double bonded O as in CO2. You ultimately have combusted your hydrocarbon. So combustion is nothing but excess of reaction of oxygen. And if you try to control, then in between you get various important functional groups. First step oxidized product is alcohol. Second step oxidized product is aldehyde and ketone. And third step oxidized product is an acid. And fourth step oxidized product is alkane has been completely combusted. So there are many oxidizing agents which are asked by JEE also, there in NCERT also, which directly converts alkane to a specific particular oxidized product. But obviously that will be the selectivity of those oxidizing agents. So some oxidizing agents are even told to you, and that becomes our next reaction, which is controlled oxidation. It is an NCERT fact, so you should learn that also. Methane beautifully reacts with copper at around 250 degrees Celsius, 100 atm pressure. Obviously one carbon will form the first oxidized product, that is alcohol, but who has the capacity to do it? Heated copper. If I want the second oxidized product, that is methane, can be converted to an aldehyde. One carbon aldehyde is methanol, generally known as formaldehyde. It is done by the selective oxidation of molybdenum oxide, MO2O3, and you have to supply some heat. But thank God, NCERT, although you can find the temperature range, but NCERT has given heat, so you do not have to remember. Whatever NCERT is there, at least I'm iterating those things. Now it is actually NCERT has taken ethane over here, but the actual fact is higher alkanes. What are fatty acids? Fatty compound is having a long carbon chain. So actually higher alkanes can even undergo oxidation to form the third step oxidized product, which is carboxylic acid. So this 16 carbon alkane, which is a very heavy alkane, so higher alkanes can be oxidized using manganese diacetate. So this heated manganese diacetate can convert this 16 carbon chain to a fatty carboxylic acid, although you can even do this for ethanoic acid because NCERT mentions it. But for good references, if you'll see, they generally mention this reaction for fatty acids. But what you should know as per mains, that acids, manganese diacetate converts carbon into carboxylic acid. And the last is The oxidizing agents that you know from class 10th, K2Cr27, KMNO4, they do not oxidize alkane because alkanes, we said at first place, they are paraffins, they are not reactive. But sir, you said 3-degree hydrogen is reactive. Yes. So 3-degree hydrogen reacts with the strongest oxidizing agent among them, that too in alkaline condition, that is alkaline KMNO4, but only 3-degree hydrogen. So for example, if you have isobutane, which is having 1 C bond H, the 3-degree hydrogen, because these will be methyl groups, so 1 degree cannot react, not reactive. So this 3-degree hydrogen only, if only this is getting oxidized, then this will become OH. Nobody else is undergoing oxidation further. So the alcohol will be your oxidized product. Moving forward, now the next reaction is isomerization. These all are very basic NCERT facts. So because NCERT, so direct questions are asked. So next is isomerization. What is isomerization? You take anhydrous AlCl3 in presence of HCl. What does it do? You take a carbon chain, a normal carbon chain, they form branched alkanes. How to draw branches, sir? Mechanism you do not have to know. It is just hydride 1,2 shifting or methyl shifting, but you do not have to know. I'm giving you a trick to learn. What is the trick? Let's say you have whatever number of alkanes is given to you. Let's say I'm given with 6 carbon alkanes. So detach, cut 1 carbon. How many carbons are left? 5. Draw those 5 carbons. So once you have drawn those 5 carbons, now tell me how many carbon you have in your pocket, because you are supposed to draw it isomers. Sir, 1 carbon. Where will you put that 1 carbon to draw isomers? Sir, this place we cannot draw because 6 member is already done. Over here or over here, anywhere you put that carbon, you will get the same name, 2-methyl pentane. And the last option will be this one. This will be 3-methyl pentane. So this is how any straight chain alkane, break 1 carbon, draw all possible isomers. All the possible isomers can be formed using anhydrous AlCl3 in presence of HCl. Now, next reaction is aromatization, which is also nothing but a knowledge, information of catalyst. A very famous catalyst. 3 metal oxides: chromium oxide, vanadium oxide, okay, I'm sorry, it is V2O5, chromium oxide, vanadium oxide, and molybdenum oxide. The molybdenum oxide that we have used for alkanes also. But any of these oxides at 500 degrees Celsius and at a pressure of 10 to 20, these are industrial facts, NCERT facts, very important. At such a condition, what happens is dehydrogenation takes place. So what is dehydrogenation? Remove hydrogen, you know from class 10th. So if you remove hydrogen, what you will form? Generally, benzene and its derivatives are formed. So for that, how many minimum number of carbons you need? So generally, this aromatization is only seen in carbons having 6 or more carbon chain. So that's why I've started with an hexane. So with an hexane, what first thing will be happening? Cyclization. So how it can become cycle? Remove 2 hydrogens, 1 hydrogen from here, 1 hydrogen from here. So if you remove, if you remove 2 hydrogen as in 1 mole of H2, so what happens is, in order to satisfy the free valency, you will get a beautiful cyclohexane. Now, sir, these reagents are already there. Reaction will not stop here. Now, because this is CH2, 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 so this is C6H6. Start removing 1 hydrogen from each carbon. Sir, but how this valency will be satisfied? Introduce a pi bond. So let's say I got a pi bond over here. So the 6 carbon chain is already there. But recently I have introduced 1 pi bond over here. Now if I remove another molecule of H2, 1 over here. Last one, I guess it is quite clear to you. So after further loss of 3 moles of H2, you get your beautiful benzene, which is an aromatic compound, and this process is called aromatization. Let us try this for 7 carbon chain. Let's say I have an heptane. Sir, benzene has to be formed because that is the most famous aromatic compound, 6-membered ring, is even free from Bayer strain. So what will be happening? The same thing. But sir, what about the other carbon? You have to remove hydrogen. So remove all this 1 mole and 3 mole of hydrogens. If I will be getting a 6-membered ring with alternate pi cloud, 1 methyl will be remaining. So this is not benzene. This is your famous methyl benzene, also termed as toluene. Moving to the last reaction of alkanes, which is pyrolysis. Pyrolysis is thermal cracking, a very famous reaction, an industrial reaction, because of which all the oil industries are running, because of which we get our petrol, diesel, whatever we have, the tools which is running a country. The oil industry is based on this cracking, and hence this is also there in NCERT, because hydrocarbons are those fuels. But when you get a crude, a raw fuel, that raw fuel has to be processed. How it is processed? It is processed using extreme temperatures. With extreme temperature, it can crack. Carbon can break. So this pyrolysis is nothing but thermal cracking. Now, thermal cracking is like something that if you kick some person from 200th floor, will the person fall? Will be falling and the same bones will be breaking? No, sir. If I kick one person today, it will definitely die. But the manner in which bones will be broken will be different on different days, because this is all permutation combination. So similarly, let's say I have a long chain of hexane, 6-carbon chain. I have subjected to a high temperature of 500 degrees Celsius. It will definitely crack. It will definitely die. But what will it form? It forms mixture of products. If it is falling and if it is thermally breaking, sometimes it can form hexene, releasing hydrogen gas. It cannot break because this is not long carbon chain, just 6 carbon. It can also form butene and ethane. It can also form propene, ethene, methane. Sir, we have to learn this example. This common sense you have to learn, and because this example is direct NCERT example, so I'm giving you also. But the most famous example for pyrolysis is dodecane. Now, what is dodecane? Dodecane is a 12-carbon alkane. Actually, it is one of the constituent of kerosene oil. The kerosene, which is a crude oil. So with that kerosene, you can make petrol or oil gas. How? By cracking. The industrial application, the industrial fact which NCERT told us that it undergoes cracking at around 700 degrees Celsius, but we use specific catalysts, nickel, platinum, palladium. Why we are being specific? Because we are subjected to obtain a specific product. What is the product? Mixture of heptane and pentene. Heptane and pentene, and this mixture is nothing but your petrol gas. Obviously, other products are also formed because number of but this will be the major product when condition is subjected to such a situation. And the last of basic fact is water gas is actually mixture of CO and H2. An NCERT fact also, it's there in hydrogen chapter, but it has been removed, but it is there in hydrocarbon also. So just one more reaction. Water gas is a mixture of carbon monoxide and hydrogen. It is also known as syngas or synthesis gas because industrially this gas is used to form number of compounds. It can also be beautifully prepared using methane. Pass steam on methane. The steam must be passed at around 1000 degrees Celsius, and the catalyst that you should use is solid nickel. When you do that, you form a water gas. Moving forward. Yes, so after a break from my side, let us again start with this question which says a hydrocarbon A undergoing combustion. So it's a hydrocarbon as in CXHY. It will be undergoing combustion as in reaction with oxygen. And sir, hydrocarbon on combustion produces what? Sir, it produces CO2, stable oxide of carbon, and water, stable oxide of hydrogen. Now, you have to know why I have told you these organic reactions, because when you know these organic reactions, you can easily make a physical chemistry question out of it. Although in mole and redox in the physical side of chemistry, I have discussed many more questions of these type have already came in JEE mains. I'm just taking one example because those I have separately discussed. So these all are the mixture of chemistry that you get. So you need to know the reactions. So now it is saying that they are getting reacted and products are produced. So 9.5 equivalents of oxygen is used. Okay, it is saying equivalence, mind you, and it produces 3 equivalents of water. So sir, technically law of equivalence says that number of gram equivalent are always equal, but sir, this number of this is 9.5, that is 3, that means it is not number of gram equivalent. Question tricks you sometime. Law of equivalence says number of gram equivalents are always equal. It is not written gram equivalents. They are saying equivalent. That means the question sometimes, the language is framed in such a way in order to trick you. So actually, because these are equivalent, so these equivalents may be representing just the balanced stoichiometric coefficients. So let us now balance the reaction. Here carbon is X, so it will be X. Hydrogen is Y, so this will be Y by 2. Doing it for oxygen, because there's a 2, so this should be X and this should be Y by 4, because Y by 4 by 2 becomes Y by 2. Now, the equivalence, it is not gram equivalent. They are just the equivalence, as in the stoichiometric coefficient, that this guy, this much of this guy is producing this much of this guy. But it is hidden in the, because generally to them, to these coefficients we represent, we take them as moles. But this is the language that they are playing with. So X plus Y by 4 becomes equal to 9.5 and Y by 2 becomes equal to 3. So Y is definitely 6 directly. So Y is definitely 6. So if Y is 6, Y 6 by 4 is 1.5 and 9.5 minus 1.5 is 8. So this is a clear answer if you know and have confidence with whether you know the definitions of physical chemistry or not. So just by knowing that definition, we have understood that this is not number of gram equivalent. So by equivalence, it is just suggesting you should think of number of moles. Now, moving to alkenes. Now, sir, alkenes done? Yes. But conformational isomers, the non-true isomers, because of sigma bond free rotations possible, which we have already done in GOC1. Go to at least that bit so that you may get comfortable. Now, alkenes, whatever physical properties of alkanes have, like 1 to 4 carbon was gas, they are also gas. Post 5 to 17 it is liquid, alkenes are also liquid. Post that, as mass increases, as carbon chain increases after 18, they in room temperature they exist as solid, they also do that. As carbon chain increase, boiling point increase, the alternation effect. The only difference is, because alkene, this is the alkene carbon becomes an sp2 hybridized system. Alkene carbon, because of increase in S character. Why this S character is increased? Sir, we definitely know there's a pi bond, and by hybridization we know this pi cloud makes this carbon sp2 hybridized. So electronegativity of sp2 hybridized carbon makes it slightly more electronegative than alkane. And if it is an alkyne, that is sp hybridized carbon, electronegativity is much increased. So due to increase in polarity, if you try to make them soluble, then alkynes are slightly more soluble, followed by alkenes, and least soluble are alkanes in water. If you talk of non-polar solvent, then alkanes will be more stable, alkene will be coming in between, and alkynes will be most soluble. So all physical and chemical properties of alkanes that we have done will be similar for alkenes and alkynes as well. Now, why I say alkanes are paraffins, sir? Because there is practically no electronegativity difference. Therefore, we have seen very few reactions of alkanes. Now, because alkene has the pi cloud, so it will be more prone and susceptible to attack of all those electron deficient species. Electron deficient species are termed as electrophiles. So this pi cloud can easily attack these electrophiles and result in the formation of addition reaction. Because pi is weak, it will always try to become a sigma bond. Therefore, reaction of alkenes will be at least more in number, because they are prone to attack by an electrophile. Now, alkenes, they are also termed as olefins. Why? Because the first alkene, that is ethylene, the 2-carbon alkene, it was reacted with chlorine and it forms an oily liquid. So because of that practical fact, alkenes are also termed as olefins. In Latin, olefins means oil producing. So, one more thing, the geometrical isomerism, the IUPAC involving alkenes, that also I have already discussed separately in GOC1 because the physical properties of geometrical isomerism, all these properties are shown by alkenes. So that particular case of geometrical isomerism, optical isomerism shown by alkanes because of the presence of chiral, I mean, you will be just requiring 40 minutes. So go to GOC1, and at least if you have not seen GOC1 in the previous video, at least have a look over those topics before proceeding to preparation of alkenes. So let us move to preparations. So first method of preparation of alkenes, just like alkanes, is by hydrogenation of alkynes. So, but alkynes, sir, when undergo hydrogenation will form alkanes. You can limit the level with which hydrogen is getting added. First point is, sir, but you said that we need a solid catalyst, someone who is holding, adsorbing the reactant molecules and then proper aligning them to react. So if somebody has adsorbed the reactants, so the inclination will be much harder and alkanes will be formed. So catalyst is required because H bond H does not break easily. So catalyst is required, but surface chemistry, which has been removed by in JEE mains syllabus, it is there in NCERT, which says that you take a catalyst in order to initiate the reaction. But if you do not wish to get the final product and get some intermediate products, then you can wish to do that if you use catalytic poisons. So the catalytic poison which we use are generally two in number. I mean, there are many industrially, but as per NCERT, we should just know two catalytic poisons which, if used with nickel, platinum or palladium, nickel catalyst is needed to initiate the reaction. But if you wish to stop, like if you have an alkane and wish to form an alkane, if you have a alkyne and wish to form a alkane, so how many moles of hydrogen will be required? 2 moles. But if 1 mole is given, alkyne can be converted to an alkene. So what are these catalyst? The famous, very famous are Lindlas catalyst, which is nothing but how question represent that Lindlas catalyst? Palladium slash BaSO4. Generally it comes like this. And the other is Birch reduction, where hydrogen, in both of them you need hydrogen. But what is Birch reduction catalyst? It is alkali metals, any alkali metal in presence of liquid ammonia and ethanol. But this is how it is mentioned. Now, if you add hydrogen to any of the alkyne using these catalysts, alkene will be produced. But geometrically, if an alkyne is unsymmetrical, as in both the carbon, both the double sp hybridized carbon, triple bonded carbon are substituted differently, then when hydrogen will be adding up, the alkene formed will be will be capable to show geometrical isomerism. So there are some reactions which also, because of the mechanism, how the way in which hydrogen is getting added, because remember in alkanes I said addition of hydrogen to form alkane is always a syn addition. But because I'm limiting the activity of catalyst, therefore the reaction mechanism also alters, also changes. So in order to make you learn, see, we are adding poison. Lindlas catalyst adds poison tremendously. So because we are adding poison, I mean I am giving you a symmetry to remember. So poison, it's a mnemonic, it's a story. Poison, giving poison is a good thing or bad thing morally? Sir, bad thing. Bad thing is a sin. So sin creates cis. It's a story to remember that Lindlas catalyst is doing bad thing using poison, poisoning people. So poisoning people is bad, and bad thing results in the formation of a cis form of alkene. So hydrogen must be getting added from the same side, while Birch reduction leads to addition of hydrogen in anti-orientation and therefore results in the formation of a transalkene. But this cis transalkene is only possible when your alkyne is unsymmetrical. Sir, if we have a symmetrical alkyne like acetylene, it can also form alkene. Propyne, it can also form propene, but they both cannot show geometrical isomerism. So this is what you should know now. One more important thing. Generally, NCERT has given these data. generally NCERT also represents these catalysts as PD/C. But actually this PD/C is not Lindlar's catalyst. It is palladized charcoal. I mean, you are using palladium in presence of C. C represents charcoal. Palladized charcoal, because JEE mains have tricked students many a times, because NCERT give this information followed by these examples. So what student feel is, they read poison and they feel that charcoal is also poison. No. Palladized charcoal can even reduce an alkene to form an alkane. Mains have asked this many number of times. I mean, advanced started it. PD/C can even reduce alkene to alkane. Sir, then why here alkene is getting produced? Because if you limit stoichiometrically, if you use very less of the reactant, then the product will also be formed to a limited extent. So this is a trick which JEE tries to play with you, but how you can overcome that, the reaction only will tell you. I mean, the options only will tell you. But for the record, I'm saying PD/C is palladized charcoal. It is not Lindlar's catalyst. If you use it to a limited extent, it can restrict alkyne to alkene, but it can reduce alkene also. Now, this is what you need to know about hydrogenation as per mains. Now, some extra things, but also important, although this thing is there in carbonyl compounds, but over for hydrocarbon it is extra, but I'm giving you make 2x speed and listen to me. Now, what is actually Lindlar's catalyst, the proper detail? Sir, obviously you need a catalyst, so palladium is a catalyst to start the reaction. What are the possibilities of poison? All the sulfur compounds. The famous sulfur compound is used as BaSO4, or you can use calcium carbonate, or you can use quinoline. These all, any of these stuff can react, can behave as a catalytic poison which will limit the activity of a catalyst. All these stuff is boiled in a solvent called xylene. So this is the actual this is the actual characteristic of a nomenclature of Lindlar's catalyst. Why Lindlar's catalyst is important? Because Lindlar's catalyst also produces aldehyde by reducing acid halides. It is also a naming reaction called Rosenmund reaction, given in NCERT in carbonyl compounds, not in hydrocarbon, therefore giving extra but important. Now, this is a bit large, you can leave this third point. So actually, lithium aluminum hydride, most of us have heard about it. It is also very strong reducing agent, but this famous reducing agent also reduces alkynes, and they reduce alkyne to form alkene. What type of alkene? The addition is also anti, so trans alkene, if alkyne is unsymmetrical, else it will be not showing geometrical isomerism. People ask, sir, lithium aluminum hydride does not reduce alkene. No, it does not reduce alkene. But if alkene is conjugated, like if you have an alkene which is conjugated with a pi cloud, so conjugated alkenes, they can be easily reduced by lithium aluminum hydride. This is an extra information which you can leave also. Moving forward. So coming to dehydrohalogenation of alkyl halides. From alkyl halides, if you remove halogen also, hydrogen also. So D as in removal of hydrogen and halogen is known as dehydrohalogenation. Now, through IUPAC, we know the general naming. Here functional group is halogen. Halogen connected to the carbon is generally termed as alpha carbon. The carbon next to alpha carbon is called the beta carbon, and because hydrogen of beta carbon is removed, therefore this mechanism, this process is also known as beta elimination. The mechanism with which it is happening is termed as E2 mechanism. Why? E represents elimination and 2 represents the order of reaction. Now the order of reaction is 2. Why? Let us understand. First point is, for elimination we need a very strong base. Now we already have seen in GOC, I'm iterating it again, OH minus is a base, but RO minus is a stronger base because the plus I effect of the alkyl group, attached with this oxygen will apply its plus I effect. and will increase the electron density at oxygen atom, and that oxide ion becomes very strong base. So actually when you have a very strong base, sir, why this strong base is required? This strong base is required because you try and understand first the electron displacement effect through inductive effect of halogen. We know halogen is electronegative, so it will withdraw electron from carbon, thereby creating delta positivity in carbon. This carbon, because its electron has been withdrawn, it will try to snatch electron from the alpha carbon. That alpha carbon will also be feeling some electron, although very less, so delta delta positive. And because of that positivity, this carbon will try to attract electron of that hydrogen. Now, because the hydrogen of that electron is also being pulled by the beta carbon, although the strength of pulling those electron will not be much high, but still it will be there. And if there is a strong base, because this carbon is not acidic, but still some of the electron displacement is felt by the beta hydrogen. And therefore, once you have a very strong base who is more than willing, who is so rich that it is willing to spend away money in every and anywhere, so that guy, that base. Now, why I've mentioned so many bases? Because as I've told you, RO minus is a strong base. So how to create RO minus? If I use KOH, it will just give OH minus. So add alcohol. So KOH becomes alcoholic KOH. So sometimes question can give you alcoholic KOH. Sometimes they write KOH in the subscript bracket, they write alcoholic because aqueous KOH will result in formation of alcohol that we'll see in alkyl halides. Sometimes they can even write RO minus because RO minus is the actually strong base. So sometimes they can even write this RO minus in presence of alcohol. Sometimes they give you the most famous example which NCERT uses is ethanol. So ethoxide ion in presence of ethanol. They can even give you the salt, sodium or potassium salt of alkoxide ion as in ethoxide ion presence of ethanol. I have given you all the possible options of representation of a base, a strong base. So I'm again repeating, a strong base favors elimination reaction, because if I have a strong base, let's say this B minus represents this strong base of RO minus. If this B minus is ready to give electron to this hydrogen, which is not very acidic, that's why I need a very rich base. So this strong base is so rich that it is even agreeing to give hydrogen to the beta carbon's hydrogen. If this hydrogen has gained electron from the strong base, it is not requiring this electron. So this electron will be getting transferred to the alpha carbon because this carbon is demanding electron from the beta carbon. And once this carbon will receive the supply of electron from where? Will receive the supply of electron from the beta hydrogen, it will now furnish its electron to the halogen. Now, this bond will be breaking, this bond will be forming, and this bond will be breaking. A transition state will come. But this whole process is a single step process. And once this bond is broken, pi is formed, and this sigma cloud is also gone. What product you get? Sir, I have a carbon which was initially single bonded, but this pi cloud is recently introduced. This hydrogen is a hydrogen or electron of this hydrogen which is leaving with the base, and the alkyl halide, the sp3 hybridized alkyl halide, will result to the formation of an sp2 hybridized carbon system of an alkene. What are the byproducts? Sir, base has given give electron to hydrogen, so BH will be removed. If it is RO minus, so ROH will be removed, and this X will be removed as X minus. Let's say if the question is taking C2H5ONa, so that will be Na plus X minus. So actually that X minus is termed as the leaving group. Now you tell me, Which halogen can act as a good leaving group? Sir, ultimately this bond has to be broken. So which bond can be easily broken? Sir, bond length decides down the group. So which halogen is the best leaving group? Iodine. Which will be the weakest leaving group? Sir, fluorine. That's why I have even not written fluorine, because this mechanism will be happening only with chlorine, bromine and iodine, and obviously the reactivity will be maximum when the leaving group is iodine. So generally it is said that a leaving group has to leave. So if it has to leave, then reverse reaction should not happen. How reverse reaction will happen? When this will give electron. So it has to be a weak base. So a common mantra, a common conclusion for leaving group I am giving you is, obviously for reactivity of halogen we have still now concluded that who will be most efficient leaving group? Iodine, then bromine, and least will be chlorine. I am here not even writing fluorine, although fluorine will be the weakest. But actually why I am not writing this is, this conclusion, this important conclusion I am making only for beta elimination, because alkyl fluoride do undergo elimination. They also form alkene, but the mechanism with which they form alkene is different. So talking only for E2 mechanism, this will be the reactivity of leaving groups. Who is a better leaving group? Weak base. So whenever, because this type of question also comes to you, if you have to decide which is a better leaving group, you have, let's say, 2, 3 or 4 options. Then go to the acid, conjugate acid base theory. If acid is strong, conjugate base will be weak, and weak base is always a good leaving group because it will leave, the reverse reaction will not take place. Point number 1. Now point number 2, as we have seen the mechanism is a single step process. The mechanism is known as E2. Why 2? Because E2 represents elimination by molecular. What is molecularity, sir? As the name suggests, number of molecules participating as a reactant for a single step of a reaction. Like, obviously this is a single step process. In the same step, base is attacking, giving electron to beta carbon, hydrogen of beta carbon. In the same step, that electron is getting transferred to the alpha carbon and halogen is leaving. So this is happening in a single step process. And how many molecules are there in this step? So not molecule, how many species? More be the base, faster will be the reaction because it will be attacking to larger extent. More be the alkyl halide, more it will be receiving the attack of the base. So how many molecules are there? 2, because there are two species. It may be ion, participating reactant species. Summation is called molecularity. Now, what is order of reaction? Order of reaction is generally given by chemical kinetics. We will be doing that also, but chemical kinetics assigns and estimates the order of a reaction, that is the speed with which the reaction is happening. This is an experimental data. Molecularity is a theoretical concept. The molecularity that we have written just now is a theoretical concept. It has to deal with whatever theory we have decide and assigned for the reaction mechanism. It has nothing to do with the experimental data. But if we do experiment, then we'll define, then we will estimate the speed with which reaction is happening. The speed with which reaction is happening, the rate of reaction is experimentally determined. And who decides how much reaction? If you have to build a home, the more raw material you use, the faster your work will be happening. The more the people that they are working, the workers, the more workers you will employ, the faster your home will be building. Similarly, for a reaction, if you want the reaction to proceed in forward direction to a larger speed, to a faster speed, then what you have to do? You have to increase the reactants, because if you increase the reactant, the speed with which the reaction will be proceeding in forward direction will increase. So experimentally, when it was seen that rate of such reactions was proportional to obviously concentration of reactants, but it came out to be proportional to concentration of alkyl halide raised to the power 1 into concentration of the base raised to the power 1. Now, this power is 1 is just God's grace, because this, like the value of equilibrium constant, is determined experimentally. So rate of reaction is also determined experimentally, and it was experimentally determined. Order of reaction is an experimental concept, and based on those experimental concept we are deciding to our theory. And the experimental concept is telling us that rate of reaction is directly proportional to concentration of alkyl halide also and concentration of base also. What is the power of concentration terms? 1 and 1. Addition of 1 and 1 is 2, and the summation of coefficients of concentration of reactant species is actually experimentally calculated and is called the order of reaction. So the order for this reaction will be then 1 plus 1. So order of reaction will be 2. So E2 mechanism has molecularity 2 and order 2. Molecularity 2 because two reactant species are attacking each other, and order 2 because summation of powers of concentration terms of reactant species on which rate of reaction is depending is 1 and 1, and summation of the power is 2. Now I've iterated this so many times. Obviously you can understand this is very, very important. You have to remember them. Now, although this is also chemical kinetics story, so because I have not, in the previous one shots also I have not discussed chemical kinetics, so I'm doing everything. You do not have to worry. If you are starting from zero also, you'll get everything. Now I hope I'm clear till this point. Now moving forward, sir, we have seen the photo. Let us look at the photo again. Sir, halogen we know has got lone pair of electron. Yes. It is electronegative. Yes. So sir, it will be electron rich. Yes. Base, sir, it is a strong base, so it will be also be electron rich. Yes. So do you know minus minus repel each other? Yes. So if a base has to give electron to hydrogen, can't you think that how it will be approaching this alkyl halide? If halogen is present over here, then base can never approach from here because minus minus will repel each other. So base will definitely try to attack and offer its electron to beta hydrogen, but it will be coming to just from the opposite side, because if it is approaching this molecule from opposite side, it will not at all be meeting this electronegative electron rich species of halogen. So that's why we say in case of beta elimination, elimination of anti-hydrogen or trans hydrogen or the hydrogen that is present exactly opposite to this halogen. So it is not 180 degree because this is also tetrahedral, this is also tetrahedral, but base will be approaching the carbon from that side, which will be exactly opposite to where this halogen is inclined in the three-dimensional space. So how I'm summarizing that point for you is, it is always anti-hydrogen is eliminated. So trans or anti-hydrogen with respect to halogen is always removed moving forward. Now, what is stereo-specific and stereo-selective? I'll be coming to it later. Now, reactivity we have done. Reactivity of degree of alkyl groups. Now, what is the product produced? Sir, alkene. If you are a reactant and a reagent is attacking you and you are forming a product, what product you will spontaneously try to form? Sir, stable product. Everybody in nature spontaneously move forward. If you are doing something at this point of time, you are only doing this for your own good, for the stability of your life. Similarly, why everybody feels the same? Because from molecular side of, we are also an organism formed by these molecules only. So our molecular genetic is telling us that in general, whenever a reaction is proceeded, the product that is produced is generally the more stable product. So can you estimate on that front that which alkyl group will be undergoing this beta elimination to a faster extent. Like for example, let's say I'm keeping the halogen same now, because for halogens we have already concluded. So keeping halogen same, can you say which alkyl group will be more reactive? Sir, if this will be, sir, this is alpha, let's say this is beta, so here this alkene will be formed, which is much more substituted, and we know alkene is an sp2 hybridized carbon. sp2 hybridized carbon is electronegative. An electronegative species wants electron. So if you give electron to that electronegative species, it will feel comfortable. Moreover, in GOC also we have seen what is the most stabilizing effect for an alkene, sir. Before inductive, check for hyperconjugation. So if a more substituted alkene is formed, then it will be having more number of possibility of having more number of hyperconjugating hydrogens will also be high. So a stable alkene can be formed when you have a 3-degree alkyl halide. Let's say if you have a 2-degree alkyl halide, then the possibility of getting substitution will reduce, because now this alkene will be less substituted, so it will be less stable. So if it is less stable, let's say if you have a in a reaction mixture, you have 3-degree also and 2-degree also, who, let's say, but only 100 bases are present and 100 molecules of these two are present. Who will be getting attack of the base to a faster extent? So that alkyl halide which will be having a better product, so it will be more fastly getting attacked by the base. So reactivity of 3-degree alkyl halide is maximum because alkene form is more stable, followed by 2-degree, and obviously the least will be 1-degree alkyl halide when there will be only substitution of one alkyl group. Now moving forward, what is this? NCRT also gives you a trick. Actually, this trick was offered by the scientist community called Saytzeff. Some references also term it as Saytzeff product. Generally, the name Saytzeff is famous. Now, what is Saytzeff product? It generally says, through common sense we know what product is generally formed. So more stable product is formed, and what alkene is more stable, which is more substituted. So in order to form more substituted alkene which is more stable, we will remove beta hydrogen of that carbon. That beta hydrogen will be removed, the carbon which is having lesser number of hydrogen. Why? If the carbon is having lesser number of hydrogen, then obviously it will be much substituted, so definitely it will be forming more stable alkene. So what I have written over here is, what is the Saytzeff product? If more stable alkene is formed in a larger percentage. In an organic reaction, we should know that only one product is not formed. The more stable is formed in the more percentage yield. Lesser stable products can also be formed, because anyway how a reaction is proceeding, molecule A is colliding with molecule B. So generally this collision will be inclined so that the product formed is good. But sometimes in improper attack can also take place. So whenever in practical life also we know that if we do everything good, generally we'll make a good life out of our hard work. But it is not always true. So we over here are talking of practical life, practical chemistry. So in nature also, whenever two reactants react, the probability of they getting reacted with proper inclination, let's say this should be exactly coming opposite with respect to hydrogen. Don't you feel this will be having some kinetic energy? Alkyl halide will also be having some kinetic energy, and they'll be getting they'll be colliding each other, and there after that the product will be formed. Do you feel every time the collision will be right? No. If I have a ball moving here, I will hit that ball. Will your strike will also be 100%? No. Because at first place they are colliding with each other because of kinetic energy. So that kinetic energy can sometimes be resulting in a collision which is not properly oriented. So this you have to make note that in organic chemistry, what product in questions, what if you are asked given the major product, then what major product will be formed, which is having more stability. But minor product can also be formed, as in a product which you feel can never be formed. In life also, you feel this can never be done, but it happens. Although the percentage of time it happens is, you do not be lucky in whole of your life, but you be lucky at some days, some weeks, some months, but you cannot just go lucky and ABCD and you always get right correct answer. Obviously you understand and feel that, but you sometimes you can be lucky. Do not study anything, the answer will be among ABCD, therefore you will have a possibility of attempting any question correct 25%. So luck, similarly, when molecules collide, the product they will form is also a luck factor, but which product is formed in the larger percentage is not decided by luck, is decided by the common sense of what should be the probability of happening you. So now if after discussing so much about this, let us now again come to this. That's why I've left it, because this needed a theoretical discussion. Now let's say I am a reaction and I am being specific that I will react this reactant from this side. I will not attack this reactant from that side, because if I'll be coming from that side, I'll be having repulsion from halogen, and I will not like that, because physically speaking, minus repel each other. But whenever a reaction, during a reaction, you have to think of this, that these reactant will, if they are aligned to each other like this, then they will form product. If like that, then they will not result in the formation of product. Then you are thinking of what? You are thinking of the stereochemistry. You are thinking of the region of space around the molecules by which they will be attacking each other, approaching each other. Such a reactions, when you are being selective, that I will react with such reactant, I will not react with such reactant. Selective. Okay. Now English. It is a very good English concept actually. So when you say specific, like for example, if you go out for eating something, you say no, specifically I like oregano, specifically I like cheese on my pizza. So when you are being selective about the reactant stereochemistry, when you are being specific and choosy about the stereochemistry of reactant, that from this side I'll react, from this side I'll not react, then you as a reaction is termed as stereospecific. And when the product that you make, we are talking that generally what product is produced? More stable product. So if I am creating a more stable product, that means I am not creating that unstable product. So I am also being selective about what product I will form. So if a reaction is selective, how? Through the stereochemistry aspect of a reactant molecule. So such a reaction is called stereospecific. And if the reaction is selective, that I'll form that product, I'll not form that product, then go to your English. I will select that product, I will not select that product, then I'm called stereo selective. Sometimes this word is also called regiospecific or regioselective, because I will attack in this region and I will produce product by removal of hydrogen from that region, because here hydrogen will be removed of beta carbon and product will be formed. So therefore these reactions are also termed as stereo or regiospecific and selective. Concluding this also, when you will say a reaction is stereospecific, when you are being choosy about the reactant. Hence I have given you this trick also. You have to learn this actually, because we have to learn now. When I'm being reactant specific, I will be termed as specific, and when I'm being product choosy, then I'm not in science, in chemistry, then you say to such reaction that they are stereo selective. Beta elimination is both reactant choosy also, product choosy also. So it is stereo specific also and stereo selective also. Moving forward, now after this, after investing much of time on this, now let us do a basic question so that we can summarize everything. Now let's say I have 2 bromobutane. Okay sir, let us draw the photo. This is butane, and to second carbon I am attaching a bromine. Sir, this is a base, RO minus in presence of alcohol. Okay. So what does a base do? Sir, base offers electron to beta carbon. How many beta carbons I have? Sir, 2. This one also and this one also. Now, which beta carbon will be removed and the product forms are at least let us do, because this is the first example we are doing, and this is also very good example also, or every common sense we'll be discussing in this example. This is halogen. This carbon will be alpha carbon. I'll just use different pen. This carbon will be alpha carbon. There will be one hydrogen over here also. This will be beta. This also will be beta, because what is the beta carbon? The carbon next to alpha carbon. If I have more valencies, I can have more beta carbons. Now, let's say if I remove this hydrogen, so what product I'll be getting? This one, that is but1ene. Let's say if I remove this hydrogen of this carbon, then what product I'll be having? Sir, but2ene. You tell me which product is more stable. Sir, more substituted alkene is more stable. And I have given you this in GOC also. If you have to assign stability of alkene, don't calculate inductive, because sometimes inductive gets tied. So count the number of alpha hydrogen. For all those who have not seen it, I'm again telling you how to calculate alpha hydrogen. This is an sp2 hybridized carbon. Directly attached carbon is this. Now count its hydrogen, 3. For this, 3. So how many alpha hydrogen it is having? 6. So it will be stabilized by 6 hyperconjugating hydrogens. What about this one? This carbon is not attached with any carbon, so it has lost its possibility of having stable alpha hydrogen. But this guy is attached with this sp3 hybridized carbon. So how many alpha hydrogen this alkene is having? 2. But this one you can see easily also. This is substituted from 2 sides, and this guy is only substituted from 1 side. So if for this case, you can also have your answer if you know inductive. But you should know everything that stability of alkene is decided by more substituted alkene is more stable. If inductive gets tied, you calculate number of hyperconjugating hydrogens. Now, because we know this is more stable, so more stable product is formed in a larger percentage. So this will be your major product. So this will be A, and this will be your minor product, and this will be B. Now, who has told us that more substituted product is the major product? Saytzeff. So some people also say that this is your Saytzeff's product. Now, you tell me, are you being specific? Are you being selective? Are you being selective that I will form this product and not that product? Yes. Such a reaction is called stereoselective. And once we will be specific about the type of reactant, then such reactions are called stereospecific. This is stereospecific also. Why? Because in the reactant also I'm saying I will not use you, I will use you. That's why that will be formed. So I am reactant choosy also, specific, product choosy also, selective. Stereo, specific and selective. Now, once more substituted product is the major product, it is called Saytzeff product. Sir, less substituted product can also be formed. Yes. Less substituted products can also be formed. But sir, if they are less stable, then you said we do spontaneously anything in life which makes us stable. Why I or why you at all do something which will destabilize your life? But it happens in nature, it happens in practical life also, that sometimes in some situation of some people in some part of universe this happens, that they know what they are doing in their life is not good for them, but for time being, or because for any, I mean, you must have seen or heard people do bad things. Do the people who are doing bad things doesn't know deep inside their heart? They know, but still they feel that's their karma. So now coming chemistry, when people say their chemistry is not matching, so chemistry is actually in practical nature also, and in our sociological and economical nature also. Moving forward. So I hope you got this beta elimination now. As I said, elimination of alkyl takes place, but all the time mechanism is not E2, which we have just finished very properly. Sometimes elimination also take place via mechanism called elimination unimolecular conjugate base, commonly written as E1cb. Not very famous for JEE mains, but questions have come, not to a larger percentage, but you should know. Now, E1cb is elimination unimolecular conjugate base. Sir, why we should learn this? First tell us. Now, let's say I have alkyl fluoride. Now we know, sir, this is not at all a good leaving group, because carbon is a second period element, fluorine is also a second period element. Second period element bond length is very less, so bond will never break. So because this bond is not at all breaking, so if I have alcoholic KOH, I will think that it will not even react, but it reacted and it formed alkene also. To our surprise, what we were expecting, okay, this bond will not break. Okay, it has broken. Some mysterious force has been supplied to this molecule and it has broken. So let's say it has broken. Okay, fluorine gone. So what alkene you should form? You should form this alkene, because that will be stable. So you should form butene. But to our surprise, experimentally what came out to be major product in case of fluorides? Less substituted alkene. Less substituted alkene is less stable, but because although it was less stable, it came out to be in larger percentage. It was experimentally determined for all the possible cases. When less substituted alkene becomes major product, they should not have been got that privilege of getting formed in that high percentage, but they were forming. Who estimated that? Hoffman. Therefore, these products are also called Hoffman products. What is Hoffman product? When less substituted alkene becomes the major product. They should not have been formed. They should not have been formed as per whatever theory you know till now. Hoffman and other scientists started experimenting that there must be something else that is happening. The mechanism with which this alkyl fluoride is reacting with alcoholic KOH must not be the same, must not be what we have theoretically designed, because that is a theory you have designed. How you have designed that theory? By looking into the rate of reaction formula. That rate of reaction was telling you, so therefore you theoretically predicted that mechanism. That's why the molecularity that we write is a theoretical concept. Although that theory we designed on basis of some experimental fact. The experimental facts are given by rate of reaction. Moving forward. So sir, how we will justify this then? Through chemical bonding and common sense of chemistry we can. How? Now proposing another mechanism, and the proposal is called E1cb because this is happening in nature. Why we designed this mechanism? To understand what is happening in nature. So understanding the mechanism of E1cb. Now, it was suggested that E1cb is a two-step process. In step 1, what it was predicted that yes, okay, elimination is happening. People said yes. So it was suggested that carbanion is formed first. Now, sir, this is alpha carbon, this is beta, this is beta. Which carbanion is more stable? Sir, 1 degree carbanion is more stable because carbanion gets destabilized by inductive effect. So this will be 2 degree, not formed. This will be 1 degree, will be definitely be formed. So definitely this beta carbon's hydrogen will be receiving from this alcoholic KOH, that is Ro minus, the strong base will be coming and giving electron to this hydrogen. And once this electron is given, ROH is removed. This hydrogen is removed by the base. And once this hydrogen has been removed, its electron is taken up by this carbon. And a carbanion is formed. So let us draw that carbanion. So the carbanion will be 4 carbons. Fluorine is still there. And this guy has recently received a minus. Why I have not this carbon ion? Because 2-degree carbon ion will be less stable. Now, because we know that fluorine is not at all a good leaving group, because bond length is very small. Second period element, bond length very small, bond very strong. But if carbon ion is formed, then in the next step, this formed carbon ion, although it will take lot of time. Why it will take lot of time? Because fluorine is not at all agreeing to the fact that I will go, because this bond length is, but this carbon ion will take lot of time, and ultimately with lot of hard work, because ultimately there is excess of electron. So if there is excess of electron, it will be supplied, and if it will be supplied, then ultimately fluorine is an electronegative species, so it will be taking electron, but it will be taking very longer time. So the second step, why I'm saying this many number of time, because second step was experimentally determined that this carbon ion giving electron and fluorine leaving in form of F minus was taking too much of time, and ultimately what is getting formed, this less substituted alkene. And because less substituted alkene is the major product, because 2-degree carbon ion will not be formed. Again, that common sense thing, in organic chemistry we will not say you will never happen. Once in a blue moon you will be formed, so you will be forming the minor product, but majorly who will be getting the profit of becoming a carbon ion? Sir, the 1-degree one. So if 1 degree becomes carbon ion, what alkene you are getting? Less substituted, and this becomes your Hoffman product when less substituted alkenes becomes major product. Sir, but how have we determined this? Through experiment. If you do reaction in, let's say, 2 or more steps, which step defines the speed? Fast step will be happening faster. Actually, out of 100 students studying in a class, which student will decide how much the teacher is going to teach? The slowest student, not the fastest one. Similarly, in industry, which stage decide the output of a factory? The slowest step, because fastest step will anyway do its work and go home. All the rate determining step for any process is always the slowest step, and therefore over here, since second step is slowest, so it is termed as rate determining step, a chemical kinetics logic. And because this is slow, that means the above will be a faster reaction, and we very well know every reaction is a reversible reaction. That's why I have given that equilibrium sign. Although I'll not be using the equilibrium logic, because those are good questions when they combine organic, chemical kinetics and equilibrium concept. But just telling you that every reaction is reversible, so you should at least know that. Because this is slow, so that will be fast, and rate will be determined by the second step, where carbon ion is giving electron and fluorine is taking so much of time because bond length is less, and giving rise to less substituted alkene, the Hoffman product. Now, how many steps involved are E1cb? So now we know 2, and you should remember this mechanism. What is the molecularity? Remember molecularity, number of reactant species. Sir, but it is a 2-step process. Practically, molecularity is defined for each step, but it is not written anywhere, but it is just a common term which every paper is in. When they ask molecularity, actually molecularity is defined for each step. But when a question is asking molarity and options are given, and it is not written anywhere that if there is more than one number of steps, then you give molecularity of rate determining step. But it is anyway, it is presumed by the scientist community without actually writing it, that if a reaction is happening in more than one step, and if at all you are asked molecularity of the overall reaction, then you say the molecularity of the rate determining step. So what is molecularity of rate determining step? Molecularity as in reactant species. What is the number of reactant species? So there is only one reactant, which is a carbon ion. This carbon ion is not getting attacked over here. The attack has all happened in first step. So in second step there is only one molecule. So actually E1cb is also very good example which shows that molecularity and order may be different, because in other mechanisms with God's grace molecularity and order both are same. So some students make it a disguise, they just assume that molecularity is same and order is also same, but it is not. And in order to actually understand this, E1cb is the best example. So here, because only one reactant species is there, so molecularity is 1. Now what about order? Sir, order, rate of reaction depends, you just now said it depends upon the slowest step. Which is the slowest stepping? Second step. So rate of reaction will be proportional to concentration of reactant. But which reactant? Of the slowest step. For slowest step, reactant is carbanion. But carbanion is not the reactant. Have you brought carbanion from the market and placed it in the test tube? No, sir. Sir, it's an intermediate. So that's why I've written this equilibrium sign. How you will write equilibrium constant of this reaction, sir? Equilibrium constant K will be equal to concentration of carbanion upon concentration of alkyl halide also and base also. Because equilibrium constant is a constant, so if you have a proportionality sign, forget about it. So concentration of carbanion can be replaced by concentration of alkyl fluoride into concentration of base. But obviously I'm writing that rate of a reaction depends on the slowest step and the reactant of that slowest step, which is actually carb anion. Raised to the power stoichiometry is 1. I can see also there is one molecule, but how I have came to this theoretical justification that this will be the rate determining step and slowest step and carbanion will be formed, because experimentally rate law has approved us. That's why we came up with this theoretical mechanism. Now, because why I'm saying this is 1, because it also must have been experimentally validated. So this one, sir, we always have to remember. Yes, that's why, because you will not do experiment now. Those who have done experiment, you have gone to those data sheets, and chemical kinetics will help you to determine that whether this is 1 or not. These questions will be given in JEE also, but in the chapter of chemical kinetics. So this one is an experimental factor and it has been determined that it came out to be 1. Now concentration of carbanion can be replaced by, so rate of reaction can be equal to concentration of alkyl fluoride also and concentration of base also. This is also power 1, so this is also power 1, this is also power 1. Molecularity is 1, but if you look, order is summation of powers of concentration term of reactant molecules. Carbanion is not a reactant. Reactant is which concentration you can change. Sir, we can put reactant into a mixture. We cannot put intermediate. Intermediate are formed by themselves. So what reactant molecules are there? RF and base. What is their concentration power? 1 and 1. Summation of 1 and 1 becomes 2. So order of reaction becomes 2, but molecularity becomes 1, a very, very, very important concept of E1cb. Moving forward. Now, after this, some people ask, sir, Hoffman product can only be formed in case of alkyl fluorides? No. Hoffman product, there are 4 different cases when you get a less substituted product, but that less substituted product becomes the major product. Sir, over there we understood. But what are those 4 cases? All these 4 cases has been introduced by JEE Advanced, but now mains have also started using them. So I'm giving that case also. Although for this particular topic, you can increase the speed by 2x. Now, if you feel that whatever we have discussed is so much for you, then you can increase and you can skip this. But mains have asked these things also, although lesser percentage of time, but have. Now, other cases of Hoffman product, there are 4 in number. First one, when bulky base is there. Now, what does a base do? Offer its electron to beta hydrogen. Let's say I am a base, but I am a bulky base. This is RO minus, but look at this R, a 3 degree R. So the most famous bulky base is tertiary butoxide ion. So when this bulky base will try to give electron, what is base? It will give electron to hydrogen. So because even I am very fatty, so technically if this bromine is going, you tell me which beta carbon will form more stable products at this one. But this guy is a 2-degree carbon, and this 2-degree carbon is sterically hindered by this also, this also, this also. So don't you feel this base, how will it enter and give electron to this hydrogen? So because crowding is so much there, base wants to give electron. So it wanted to meet you and come to your place, but because I was so heavy, I was so fat, and there was no lift, so I will not climb 16 floors and come to you. If you are there in the ground floor, I'll meet you and say hello, I'm a very good friend of yours. But if you are at 16th floor, I will just give the greeting card to your watchman and ask the watchman to give it to you. Similarly, base wants to give electron, but if this carbon is sterically hindered, and if I am a fatty base, so I cannot enter. And so what else I can do? I will not choose you, I will choose the another beta carbon. So let's say this is CH2 and this is H. Now look at this H. This H is tetrahedrally oriented outside and it is having no hindrance. So this bulky base will easily give electron to this hydrogen. If this hydrogen will get the electron, will offer the electron to alpha carbon, and the base will be gone for good. And the product that you will be getting is the first carbon getting double bonds and all other bonds are as it is. So your answer will be 2-methyl but1ene. This is the other case when you get Hoffman product. Now, what is the case 2? Sir, Hoffman product can all when conjugated. Now, we say that although these Hoffman products are formed which are less substituted alkenes are becoming major product, but still if you look at each particular case, you will feel this is the probable thing that should happen. How you make that feeling? By understanding the logic. So till now we have seen 2 Hoffman products. Don't you feel formation of those Hoffman products were actually practical? But yes, that practical mechanism and common sense comes to us through logics of GOC, chemical bonding, and the chemistry that we know, the basic foundation that we know. Now, other case, let's say I have 4-ido-5-methyl-hexene. Now this is a molecule. Okay, hexene as in this one. 4-ido as in 4th position I have iodine, and at 5th position I have another carbon. Now, if this is alpha carbon, this is beta 1, the left side beta, this is beta 2, the right side beta. What we know, generally if we have alcoholic, sorry, it is not a bulky base, neither it is alkyl fluoride. So why we will do Hoffman? As in why we will do that alkene which is less stable? This carbon is having only one hydrogen. So if this one hydrogen is removed, very stable product. Why this product is stable? Because this is inductive also and hyperconjugation also. But go to your GOC, inductive is a stabilizing effect, hyperconjugation is a stronger stabilization effect, their daddy is resonance. So if I am anyway getting resonance stabilized alkene conjugated system, then why will I look? If I am having a party of paneer and all, why will I have dal? Point is, if alkene can be resonance stabilized, why are you thinking of making a substituted alkene so that you may get profit of inductive and hyperconjugation? You are getting crore of rupees. Why will you take lakh of rupees? You will not think of those lakh of rupees. So because if this beta carbon is giving hydrogen, so alkene will be coming over here, and this alkene will make that pi cloud pi sigma pi, and that therefore the formed product will be resonance stabilized. So this is 1 2 3 4 5 6. So double bond will be coming at carbon 3rd and 4th, and post that I'll be having the groups as it is, because if this carbon would have given hydrogen, it will be not resonance stabilized alkene. This alkene is pi sigma pi, so it is a resonance stable alkene, which is actually a major and stable product. Moving to another case. Now, just like the first case when we had a bulky base, now let's say if base is not bulky, but now alkyl halide is sterically so much hindered. Now, let's say if I have alcoholic KOH, so here the base is quite efficient, it can enter. But if I am entering, and even if you alkyl halide, you are quite sterically hindered, right? For example, this is the alpha carbon. So what are the possible beta options we have? So beta this one or that or this one. If even you take beta hydrogen of this carbon or this carbon, you will be getting the same alkene, the less substituted one. So let us say this one. Now, if this beta carbon's hydrogen is gone, obviously this alkene will be more substituted. But just think of an idea that this carbon has one valency of that bulky group. It is having two hydrogens. But won't you feel that this base, when coming from the opposite side, will even meet this sterically hindered bulky group? Yes. So whenever the alkyl halide that is going to form the Saytzeff product, if its beta carbon is also hindered, then in all those particular cases also, I am a base, I just want to give electron. So why will I bother? I just have to give electron to hydrogen. So I will try to do donation to a less hindered hydrogen. So can you tell me what will be the product produced? Yes, sir. These carbons will be as it is. I will not take your hydrogen. You are very crowded. A beautiful less hindered alkene will be formed, and because less substituted alkene has formed to a larger percentage, and logically also it is right, and therefore it will, through common sense, if we know this common sense, we can say that yes, it will be practical also that this product will be formed in a greater percentage as in major product, and therefore this also becomes your Hoffman product. Now, in case of carbanion, I just missed one thing. In case of carbanion, because I mean for good questions, in case of carbanion, let's say you have two different alkyl fluorides, then which alkyl fluoride will give alkene faster? Sir, which will give E1cb faster? What will give E1cb faster? Sir, E1cb carbanion is formed. So what stabilizes carbanion? Sir, if I have electron withdrawing group, then definitely this electron withdrawing group is going to stabilize this carbanion, and therefore E1cb of that particular alkyl fluoride which is getting stabilization by electron withdrawing group will be faster reactive, which it will be undergoing elimination quickly via E1cb, although these logics will be used for good questions. Now the last case number fourth, when Hoffman product will become the major product. Like for example, you have this alkyl halide. We know through GOC, I'm iterating all those things again, but we know this, that cyclic chain are planar carbon chain. And sir, but every carbon is tetrahedral sp3 hybridized. So in order to understand that hybridized, that 3D geometry, carbon lie in a single plane, one bond up, one bond down, showing the tetrahedral arrangement. So if you have a cyclic structure, then you know this, that it is the carbons are planar. But let's say question has given you an alkyl halide and it is not representing the three-dimensional picture, then you will not consider that picture. So what you will do, like for example, I have this alkyl halide, this carbon becomes the alpha carbon, this is also beta, this is also beta. If above beta's carbon hydrogen is removed, sir, more substituted alkene will be formed. Let us form that alkene. So that alkene will be, I just remove this alpha because I'll be needing this structure few times. Here also, here also, here also. So now bromine and this bond I anyway have to remove, because we know elimination will take place. What elimination? Dehydrohalogenation. So halogen I've taken out now because there is a methyl group over here. So if I get a pi bond over here, sir, this will be more substituted alkene. Just calculate number of alpha hydrogens, 3, 2 and 2. So how many alpha hydrogen it has? So 3 plus 2 5 plus 2 7. So it is stabilized by 7 hyperconjugating hydrogens, right? Because this double bonded carbon is directly connected with 2 sp3 hybridized carbon. Count the number of hydrogens. This one is only connected with count its number of hydrogen, number of hyperconjugating hydrogens. Also how to calculate, I have again given example. So this will become your major product. And what will be the minor product? The other one will not be formed. Which other one, sir? This is your major product, but plus obviously Saytzeff said that will be product and that will be formed. But if let's say to a minor percentage I have this product, this is your minor product. Let us calculate alpha hydrogen for this. So this is CH2 and this is just CH. So how many alpha hydrogens it has? Sir, only 3. So that's why I'm saying it is less stable. And what should be formed? More substituted, more stable product. And it is formed also. When it is formed, it is Saytzeff product. But when the question is giving you the conformational the geometrical restriction, because we know a cyclic system is also a geometrical stereocenter. So a geometrical stereocenter, if the isomerism, if the isomer is fixed given to you, like for example, I know this is bromine and this is methyl. But this bromine can be upside also, can be downside also. But if the question is making it is talking about a particular geometrical isomer, like for example, here bromine with, okay, so because these are the point of difference. Because it is bromine connected, it is methyl connected. Now, because hydrogens are on same side, so it is what geometrical form? Cis form. Over here, hydrogens are opposite side, so this is what geometrical form? Transform. Now the question has been restricted you from thinking of any possible geometrical isomer. Here you have thought of only of forming the stronger product, which is right also. But now question is saying this compound this compound will have to three-dimensional orientation, geometrical isomerism, this one and that one. If this is reacting and it is going to react with alcoholic KOH, so mechanism will be E2. E2 says if halogen is at this carbon, then what hydrogen of beta carbon you have to take, which is at exact opposite. And always we have mentioned that in E2 mechanism, that E2 mechanism always follows anti-elimination. As in, if bromine is present over here, then I will always, as a base, I will always give electron to that beta carbon's hydrogen, which is opposite. And now, because we know if bromine is downside, so who will be the opposite hydrogen? This will be the opposite hydrogen. So if I have taken this cis form, so my product will be this bromine and this hydrogen gone. So product is this only. Sir, this is the major product that we have formed. But this you can only form with cis form of this particular geometrical isomer. Let's say if we have this one, sir, bromine is over here, although that will be forming more stable product. But do this with respect to bromine, I need hydrogen here. But sir, over there methyl has been restricted. Hydrogen for that particular carbon is downside, but E2 is always opposite, hydrogen is removed. So even if by coming to this hydrogen, product will not be stable, but as a base I will not even give you electron. I will only give electron to that hydrogen which is at opposite. So if preferably you wanted that, yes, my hydrogen is opposite, take that one, base will take that one. And by the way, you got obviously you will offer which hydrogen, which will make you stable. But because you do not have that hydrogen, now base is not going to offer, but base is going to offer to that hydrogen which is opposite. So you will say, okay, this one is my opposite. So here this hydrogen will be taken, and what product you will be getting, which was the less substituted product. So this becomes, let us name this product, because double bonded carbon. So this will be 1 2 3 4 5. So this will be 3-methyl cyclopentene will be your beautiful answer. Moving ahead. So quickly moving to the third method for preparation of alkenes. First is from hydrogenation. Second is from beta elimination from alkyl halides. Now if from an alkyl halide I have taken H and X and formed an alkene. So we can even take dihalides and take those two halogens. So process will be just known as dehalogenation. But for dehalogenation I need a dihalide. So you can take any dihalide. Dihalide are generally of two types. When the halogens are present adjacent to each other, it is generally termed as a vicinal dihalide, and when the halogen atom is present at the same carbon, it is called a gem dihalide. So you take any dihalide. The what reagent is famous in NCERT is zinc dust. So actual reagent is you have to take that zinc dust in a polar organic solvent like ethanol or acid. So what happens is, obviously by the name that is suggesting, both the halogens will come out, sir. But why the halogens will come out? Because you have a metal, the metal which is zinc. So zinc wants to come in oxidation state of +2, so it will form ZnX2 with any of the halogen, and you just remove those halogens and include a pi cloud. So if it is in the same carbon, then just to the next carbon you introduce that pi cloud. A very simple reaction given in NCERT, and will be your simplest third method of preparation of alkenes. Moving to the last and final method of preparation, which is by dehydration of alcohols. Now you must be thinking that, sir, elimination you have spoken of, sir, E2 you have spoken, E1cb you have spoken. Why you have left E1? Because actually the elimination of alcohol takes place via E1 mechanism, and the basic point of difference between E2 and E1 is, as the name suggests, over there molecularity is 2 bimolecular, and E1 name is therefore unimolecular elimination. Now sir, but we know, just like alkyl fluoride, oxygen, fluorine was a second period element, remember? So breaking C bond F was very difficult. Sir, oxygen is also a second period element, so breaking C bond O will also be difficult. Yes, that's why it is not getting eliminated as halogens, as beta elimination, as E2 mechanism is different. While reagent also, if you take alcohol, you need an acid. So what does an acid do? It basically does the same thing. Like for example, alpha carbon, which is having the functional group, but this time the functional group is alcohol. And the beta carbon, you will take hydrogen. So this is hydrogen of beta, but functional group now is not halogen, it is OH. So H and OH will be removed in form of water, and we need a dehydrating agent, which is generally an acid. Like the famous dehydrating agent by NCERT is sulfuric acid. So you take concentrated sulfuric acid, heat it, water will be removed, and you get a beautiful pi bond, and alkene will be formed. So everything is the same. In common sense, everything is same. Like for example, for alkyl, what we said, what was the reactivity? 3 degree was most reactive. Here also 3 degrees most reactive and 1 degree is least reactive. And in fact, although this is a very good common sense, but although I'm telling you this also, if you take 1 degree alcohol, the mechanism is also more or less the same. So mechanism for dehydration of 1 degree alcohol is also E2 only. But yes, I mean, for alcohol, you should always remember that they undergo elimination via E1 mechanism. And obviously 3 degrees most followed by 2. NCERT also gives this information about the reactivity with a very beautiful example, and because it is important, so I have given you just that NCERT reaction. What type of alcohol ethanol is? Sir, it is a 1 degree alcohol. So look at the reagent. 1 degree alcohol is undergoing dehydration with sulfuric acid, a strong acid, but at a temperature of 443 Kelvin. Remove water, give alkene. Alkene of 2 carbon will be ethene. Let's say if I have a 2 degree alcohol, this 2 degree alcohol, look at the information which NCERT is giving you. We know reactivity of 2 degree is higher. So just look at the reagent. Instead of H2SO4, they have used H3PO4, which is a weaker acid. and over there it was concentrated. Here they have said you can even use weaker acid, and the concentration also they have taken 85% of weaker acid with respect to H2SO4. H3PO4 is also a mineral acid, strong acid, but look at the beauty of NCERT, how it is telling you that 1 degree requires a very strong acid and a very high temperature. 2 degrees requiring relatively a weaker acid, and relatively, look at the temperature, smaller temperature, because it wants to get dehydration. So even dehydration happens at lower temperature. You get the corresponding alkene. Remove this OH and H from any of the beta carbon, you will get your propene. Now, if I have a 3-degree alcohol, sir, if I have 3-degree alcohol, then dehydration will be more drastic. So look at the concentration. It is a weak acid with even lesser concentration. Look at the temperature, even lower temperature, which shows 3-degree alcohol is having high tendency to undergo elimination. Now, coming finally to what this E1 mechanism is. Now, this E1 mechanism is actually a two-step process. You must be thinking in your head, so C bond F was not breaking, why C bond O is breaking, is getting broken down easily? Not easily. That's why I said you need a dehydrating agent, which should be preferably an acid. So actually why we need an acid is because the first step of the mechanism says you have to form a carbocation, because this is experimentally validated. Sir, how carbocation is formed if the bond is not broken? That's why first, if the medium is acidic, because there is presence of lone pair of electrons on alcohol, so they will give this electron to this H plus, and in return it will form a protonated alcohol. Now what is a protonated alcohol? Sir, when this oxygen has lost one of its electron, given that to hydrogen, it will attain a positive charge. So this alcohol is known as a protonated alcohol. So what difference it has made? Sir, C bond O was strong because second period elements, but because oxygen being a very electronegative atom and has received a positive charge, so now this has become very violent. It will not think of anything, and in the same time it will snatch this electron of carbon and will be released as water molecule. So dehydration actually has taken place in the first step only. Now once water is removed, this carbon, this guy will be attaining a positive charge because its electron are gone. So this will be the formation of carbocation, and always remember this most important statement of mine. Whenever carbocation is formed, it is always the rate determining step. So actually formation of carbocation is the slowest step. Shape of this carbocation is trigonal planar, hybridization is sp2, and one most important thing is, because it is this carbocation is formed in the slowest step, so it will take as much time as possible, and while requiring that time, it can undergo rearrangements. These are the reactions which are very famous. So this carbocation can undergo rearrangement, can undergo ring expansion. Therefore, the product that you will be getting will be something different, and all the GOC logic of carbocation will be applicable. This carbocation is formed in the slowest step, so it will be getting all the opportunities to stabilize itself. Once this carbocation has stabilized itself, like for example, this carbocation is already very stable. This is a 3-degree carbocation having the maximum possible hyperconjugating hydrogens, which is 9 in this case, the isobutyl carbocation. So because it is already very stable, so it will not undergo any type of rearrangements and ring expansion, because ring is not even present. But I'm just giving you a hint for the later slides, or for the questions that you'll be getting. We'll be discussing some of them, the ring expansion rearrangement. But again, ring expansion and rearrangement is only possible in case of E1. E2, it does not take place. And once this carbocation has been stabilized and it has been finally formed, it will very fast undergo this step 2. Now what is this step 2? This carbocation will be coming. Okay, I'm sorry. This carbocation will be coming, and because this H plus must be given by the reagent H2SO4, let's say, or any acid. If acid is giving H plus, the conjugate base will be present. So let's say this H plus has been coming from H2SO4, so you will be having the conjugate base bisulfate, or any acid will be giving H plus and the conjugate base will be there. Now after the carbocation is formed, now it will search the beta carbons. How many beta carbon we have? 3. You take any of the beta carbon because the product will be same. This base will give electron to one of the hydrogen of beta carbon. Rest it is still like E2. After stable carbocation formation, it is like E2. Now we go to, if there is different beta carbons whose beta carbon hydrogen which will form a stable alkene. So here also, what product is formed? Saytzeff product is formed. So if this hydrogen is removed, you will get your beautiful 2-methyl prop 1 ene. Moving forward. Now let us try and understand this reaction mechanism of E1, which is basically different from E2 because of the fact that there is a formation of carbocation, and that carbocation can undergo first ring expansion and second rearrangement so as to stabilize itself, because anyway it is formed in the slowest step. This we will be learning with the JEE mains example. This was from 13th April 23. You are given an alcohol, medium acidic, heat. So what we should do first, this alcohol, because of lone pair, will attack this H plus, gets protonated. C bond O does not break easily, but after protonation, it will be easily dissociated. Now, if we dissociate this particular bond, what we are going to get is the complete chain except that OH. That OH is removed in form of water, and we end up with a beautiful carbocation. Now, because carbocation is formed in the slowest step, it will be taking time until it is maximum stabilized. I'm again repeating, for stabilization, first, if there is a ring and just after the ring there is an attached carbon, like over here, ring is attached with this carbon because it is having 2 bonds, so there will be 1 hydrogen because 1 electron gone, so it's a carbocation and sp2 hybridized system. Now, whenever after a ring there is a carbon and it gets a carbocation, then the ring can expand because of bare strain. Ring wants to expand till what? 6-membered carbon chain is free from any type of angle strain, but smaller is the ring, more is the strain. So 5 ring will have more strain, or 4? Sir, definitely 4. So first we'll try to open up this 4 carbon ring. So this bond which this carbon is making with this carbon, this bond can be shifted. Now if this bond gets shifted, it will be formed to that particular carbon. So if this bond is formed to that particular carbon, that carbocation will gain an electron. Electron will be lost by whom? Electron will be lost by this carbon CH. So this guy will lose electron and the chain will get expanded. So this process is known as ring expansion. So post ring expansion, what we are going to have? This carbon CH, this guy which has just lost the electron, the ring gets opened up, and this carbon which was having a bond with this one will open up the bond and will form a bond with this CH. Although these were connected, so they will still be connected, but now this guy has lost its electron, so the positivity will be falling to this carbon. The rest of the system, this carbon is further connected. with this cyclic system, it will remain. Sorry, this has brought us no use. No, okay, actually this much use we can take. So this position will be acquired by this carbon. Now we have, sir, but that is looking very untidy. So let us number it. It is nothing but 1, 2, 3, 4. It is not IUPAC numbering. I'm just numbering to let you see that this is also 5-membered carbon chain. So instead, let us make 2 5-membered rings. This is first ring with this first carbon connected with this ring. Now it is looking beautiful. And if the first carbon, which is this one, is attached, where is the carbocation? Surplus is over here. Now, after ring expansion, next offer you will give to the carbocation of getting rearranged. Why it will get rearranged? If it is getting more degree, then it will definitely rearrange. What is the degree of carbon over here? So 2 degree. The rearrangement just happens to the adjacent position. So if it is shifted over here, so no profit, still it will be 2 degree. But if it is getting over here, then its degree will increase. So next offer you will make to this carbocation is you will rearrange it to so that its degree can be increased. If it is increasing, do it. If not, let it be. But over here, if this guy, because it's a C, so there will be one hydrogen. So this hydrogen will take its electron also and the electron of the carbon also. I'll just denote it with different color. So this hydrogen will be taking electron of that carbon and moving to this particular carbon. If it is happening, this is called, H is removed in form of H minus. This is called hydride shifting. This is called hydride shifting. If at all there was no hydrogen, we can even shift other carbon atoms as well. Like over here, carbon is losing electron. So ring expansion and rearrangement, you can even move, if there is no hydride, you can even move methyl groups or whatever carbon available, because carbocation needs to get stabilized. Now this hydrogen will come over here. Then what we are going to get, sir? We are going to get the same system as in, sir, 5 members over here, single bonded with 5 members in the second ring. Because this carbon has given hydrogen has came to this one. This was CH initially. Now it has become CH2 because it has got one extra hydrogen. So positivity will be coming over here. Now, sir, but still there is case of ring expansion. Yes. How? Sir, this is 5-membered ring. Yes. This 5-membered ring is connected to this carbon. This carbon is C. Yes. If, sir, you said ring has adjacent carbon which is having a carbocation, then ring expansion can take place. And because it is still 5-membered ring, which ring is free from any type of strain? 6-membered. So will 5 want to become 6? Yes. So will we give this carbocation offer? We will not give this carbocation offer. This carbocation is already formed in the slowest step. It will be rearranging and ring expanding till it stabilizes itself, because it is the slowest step. It will take as much time as it wants to take. So let us again do that. This C bond will be opening like this, and this carbon will be taking this positive charge. Now I'm making it directly. How much carbon ring will be getting? Let me number it for you so that you can directly see. 1, 2. Now this second carbon will be getting attached to this carbon, so it will become third carbon. This will be 4. This is 5th. This is 6. So how many carbon chain you have now? 6 carbon. So after this ring expansion, what is going to be taking place? So this 5-membered ring is as it is connected with this carbon, but this carbon has recently made a bond with the second carbon, this one, and became the third carbon. So if this is the third carbon, let's say this is the second carbon, this is the first carbon. So how you make a hexane? Because it is a 6-membered ring. This is how you make a hexane. Now let us number it also, so that, I mean, this is not IUPAC numbering. This is first carbon, second carbon, third carbon, fourth carbon, fifth carbon, sixth carbon. I've just made the ring beautiful so that you can, I mean, not that looking beautiful, but it is six membered. This is how you draw six membered ring. Now, which carbon has lost its electron? Sir, you have given electron to third carbon, fourth carbon has lost electron, this fourth carbon. So positive will be coming to this fourth carbon. That's why I have numbered it. So this guy must have got the positive charge. Now sir, still it is the same case. How? This is a 5-member ring. Yes. This is to the 5-member ring. This fourth carbon is directly connected. Yes. This carbon is CH. If this bond, as in this bond from third carbon gets broken and it is made with the fourth carbon, positivity will be coming to this third carbon, and this chain will also become a 6-member chain, because presently it is 5-member chain, so it will turn into a 6-membered chain. So this 6-member chain I'm numbering with a different color so that you may understand. This will be its first carbon, second, third, fourth, fifth, and this fourth carbon will become its sixth carbon. Now, so again ring expansion will take place. How many rings I'll be getting in the green side? So 6. So how do you beautifully make 6 carbon ring like this? Now, let's say this is the first carbon. Let's say this is the first carbon, second, third, fourth, fifth, and sixth. Now, sixth carbon and first carbon is similar as third and fourth carbon of the pink chain. So let me draw that pink chain with a pink color. The third and fourth. So this is third and this is fourth. Those are 4, 5, 6, 1, 2 connected to a third. Sir, they both have got 6 membered, but now who will be having the positive charge? So that third carbon which is first. So this guy will still have the positive charge. Now, because this carbon is having proper ring also, now no further ring expansion can take place. Let us look into a rearrangement. So this is 3 degree. Here also it will be 3 degree. Here also it will be 2 degrees. So why it will degrade itself? Here also it will 2 degree. So it is the best possible case. Now no rearrangement, high, dry shifting, nothing will be happening because this is stable. It can't change from, it can't upgrade from 3 degree. So after 3 degree carbon, after the stable carbon, now this is the stable carbon formed. What was the next step? Sir, the next step was deprotonation to form alkene. So now search for that beta carbon. Where is that beta carbon? So this also, but they both gives the same alkene over here. But instead of that alkene, I'll be forming alkene with this CH. Why? Because it will be having more hyperconjugating hydrogens. So next step will be deprotonation. Whatever base will be present will come, give electron to this hydrogen, and this hydrogen will make a pi bond over here. So we will be getting a beautiful pi bond between the two. 6-membered ring. A very beautiful question. I mean, if you ask me, as per mains, it was a very good question. But I've discussed this question so that you may understand mains also, although a good question, but whole of the common sense of ring expansion and rearrangement is clearly understood by this example. Now, going back to this E1 mechanism, sir, we have learned everything. Now, just summarizing this one thing for you is, if you write rate of reaction, it will be proportional to, sir, it is the first step you said is the slowest step. So for first step, who is the reactant? So reactant is alcohol. H plus is just a catalyst, because if you have taken H plus initially, the H plus while deprotonation is removed also. So H2SO4 is not a reactant, it is not utilized. The reaction is happening in its presence. So for rate of reaction, we only take reactant, not catalyst. So who is the actual reactant? Only the alcohol. So rate of reaction will be depending upon concentration of alcohol to the power 1, but the power 1 we have obviously determined experimentally, and it came out to be 1. So order of E1 reaction is 1. Now if someone is asking you what is its molecularity, sir, definitely what is molecularity? Number of reactant molecules in the rate determining step. So what is the rate determining step actually? Sir, this step. What is the reactant? Sir, it is a protonated alcohol. So number of species also 1. So as I told you, It is irony of nature that E1 has order and molecularity both one, E2 has molecularity and order both two. So in order to understand that no, they can be different also, that's why E1cb was also important. Now, moving ahead to other. Yes, so moving to chemical reactions shown by alkenes, now we have already seen they are covered by pi electron clouds and pi wants to become sigma. That's why they are more reactive than alkanes. So what reaction they are going to form? Sir, those reactions in which the pi bond will become sigma. How it will become sigma? By addition reactions. So alkenes show number of addition reactions. The very first and the obvious one is hydrogenation. You know from class 10th, we have discussed right now also. Alkene can undergo hydrogenation when we have hydrogenating agents. Famous hydrogenate, I mean there are many hydrogenating agents, but for mains, you should know lithium aluminum hydride, catalytic hydrogenation already done. And one thing I was telling you, that hydrogenation happening with palladium and with palladized charcoal will also reduce alkene and the corresponding alkane will be produced. So the second addition reaction shown by alkenes are addition of halogens. Now, sir, hydrogen was adding HH. So remember, it's a syn addition. Hydrogen adding from same side because hydrogen are very small. Whenever halogens X2 you have to add, generally halogen, because they are large in size, anti-addition of halogen takes place. This you have to remember. Now, sir, what halogen will do? Remember, for alkanes we've discussed F2 is very violent and I2 over here also is very slow. So what halogenation is famous for alkenes, sir? Bromination again and chlorination. But bromine is a liquid at room temperature. Now this bromine is mixed in an, because organic compounds we are getting the reaction, so bromine is mixed with an organic solvent which is CCl4. Br2 when added to CCl4 in organic chemistry it is termed as bromine water, although there is no water, but it is generally named as bromine water because its color is beautiful orange reddish color, and once it is present its color will be present. We know it reacts with alkene and gives addition product. What addition product? Alkene gets added to anti-addition, as in, I just draw the structure for you. Like I have this carbon chain and bromine gets added. Anti-addition, as in one bromine over here, one bromine over here. Although this is just a bond line projection, this three-dimensionally does not mean that if I made a bond one over here, because all this is tetrahedral arrangement, but just for in order to make you understand with a simple logic that hydrogen is small, so it is adding from the same side. But because X2 is large, so because in order to minimize repulsion, it has a anti-addition. But what is the product produced? It is a vicinal dihalide. Now, who was having this orange red color? Sir, Br2. So when Br2 as a molecule was existing, the color would have been there. Because Br2 has reacted, now it has formed a alkyl bromide, so the color will also go. Yes, and decolorization of bromine water is therefore a test of unsaturation, a very important point. Now, so similarly Cl2 can also do. Yes, definitely yes. So if I have this R, similarly vicinal dichlorides can also be beautifully produced. Now this much you have to remember for basic. Now for some good questions I'm giving this extra. Now what is the mechanism? Sir, we already know this, that whatever alkene is doing, alkene is having pi cloud, so this makes it electron rich. Now the famous mechanism is with bromine, although Cl2 also reacts via same mechanism, but bromine JEE has asked. Good questions, but has asked. So extra, but discussing. Br2, after seeing this pi cloud, will get attracted. So because bond length of Br2 is high, so Br2 gets broken in Br plus and Br minus. So who will attack this cloud? So this is minus. So if you compare Br plus and Br minus, who will be having the first opportunity? Sir, plus, because plus will be Electron loving and electron loving species are called electrophiles. So this electrophile will attack the benzene ring. We to nomenclature, to pronounce it, we say this is the attacking species and it is attacking. But for the electron cloud, we know what moves. Electron moves from higher concentration towards lower concentration. So the mechanism line will be drawn like this. Although this is attacking species, but where you find electron density here, where you find deficiency of electron here, how this Br plus has formed, Br2 has broken down to Br plus and Br minus. Who is given the preference of attacking first? The positivity. Why? Because minus plus attract each other. Now, after the attack, now this we are knowing through the experiment, and therefore we are suggesting this mechanism. Actually, what I'm trying to suggest over here is, when this, like this alkene is a planar geometry having pi electron cloud upside also and downside also. Now that planar geometry will be approached by Br plus, size of bromine is high, so it can either be approached from upside or from downside. Let's say it has approached this alkene from upside, so this Br has approached alkene. Now once it has approached alkene, it can form bond with this carbon also, but it can form bond with this carbon also. As soon as the bond is broken, this pi bond will be broken. So actually the intermediate, the mechanism says that in the intermediate a cyclic chain is produced. Now sir, because this is, let's say this is 0.5 bond order, this is 0.5 bond order, then one bond has to be broken. So because one bond has to be broken, therefore I'm not showing this pi bond now, because that bond order was 1. So this carbon also can form bond with it, this carbon can also form bond with it. So these three species are getting attracted to each other with, because who has attacked? Br plus. So positivity will be lying in between. So this is called a cyclic brominium cation with no specific atom attaining charge. Now why I'm emphasizing on this is, here carbocation is not formed. So how do you know this? Can we see atoms and electrons to such an extent through spectroscopy? No. But through experiments we have seen that no rearrangement takes place during such reactions. So rearrangement, we have recently seen, rearrangement is only happening whenever carbocations are formed. So if carbocation would have been formed, then rearrangement could have been possible. So because there are no rearrangements seen in cases of these type of addition, therefore it is for the mechanism of addition of halogens for Br2, it is suggested that a cyclic brominium cation is formed and no one is getting the positive charge, so no rearrangement. Now because bromine has attacked from upside, so the other guy will also be waiting, the Br minus. So Br minus will say, now it's my turn, you got your chance, now let me take the pleasure of attacking. So this Br minus will obviously, it can't come from that side because that side has already been occupied. So the anti-addition you can obviously feel. Now let's say this minus is giving electron to this carbon, it can give to either carbon. Let's say it is giving to this carbon. If it is giving these extra electron to this carbon, so this guy will not be needing its pi electron. So it will give its pi electron to this bromine. And this guy was already having its pi electron. So this pi electron and the pi electron of this carbon will be transferred to this bromine and the bond will form. How this bond will form? This bromine is already bringing one extra electron for this carbon. So you can clearly see, let me make those carbon with the yellow color. Okay, let me make it with a brown, pink color. So this Br minus, let's say, has added to this carbon, but from the opposite side. So that Br would be there on the opposite side. I'm again saying, when we draw a 2D structure, this does not mean this is opposite, because these bonds are obviously tetrahedral, but just to make you understand and learn that what type of addition Br2 has. Br2 has this is an anti-addition without actual formation of any carbocation. A good knowledge, but you should have it. Why? For some good questions. Now, this is a type of question which advanced started and mains also started asking. Now, the fact behind Br2 addition is that the reaction, sir, we are being specific in the reactant that I'll attack from this side and attack in this side. So this reaction is obviously, you can see it is choosy about reactant. So this is obviously stereo specific, but now I'm telling you it is stereo selective also, because once we have done experiments and found their products, so whenever we had an alkane which has the capacity to form a chiral and optically active carbon, like for example, let's say I have this butene. It may be cis also, it may be trans also. So for cis, let's say first Br plus will be coming. So let's say it is coming from this side, then other Br minus will be coming from that side. Now the three-dimensional geometry is fixed because we are talking for cis isomer. Now, if you do not know the isomerism, let's say we are adding to butene, but Br once added to butene, both these carbon will become chiral. Why? Let's just look at this carbon. This carbon is having one CH3, one H, one bond with some big carbon, and other will be bromine. So it will be a chiral carbon. For all those who are not comfortable, I've already said that for GOC1, the geometrical optical you should definitely go and watch. If not, I'm telling you now only that a chiral carbon is a carbon which is sp3 hybridized having 4 different substituted bonds. Now, so this becomes a chiral carbon. Sir, this also becomes a chiral carbon. So whenever you see such a chiral carbon which is symmetric as in you number this compound from this side also and that side also, it will be same. Then in those particular cases, it was observed that although the molecule had chiral carbon, but the overall compound was optically inactive. Sir, if a compound contains chiral carbon, how can it become optically inactive? We have discussed in GOC1, optical inactivity can be imposed by 2 ways, by internal compensation and by formation of racemic mixture. So now, a trick I'm giving you. The trick is the keyword team. The trick is the keyword I make my students, and therefore now you are also my student. So learn this team. What is this keyword? It is a mnemonic to help you with. T stands for trans. For trans alkene, A stands for E, doesn't stand for anything. I just like the word team. So T stands for trans. If trans alkene has A stands for anti-addition, Br2 does anti-addition, then you get a mesoform. Team trans subjected to anti-addition forms a mesoform. Now what's a mesoform? So above this is cis, this is trans. So this is first carbon, this is second carbon, third carbon, the chiral carbons. How we draw a chiral carbon Fischer projection? Let's say this is the second carbon, this one bond is CH3, the second carbon, the third carbon, and the fourth carbon. Now this is what I'm saying. It is symmetric. I'll just draw the structure, you will get to know. One Br and one H on this carbon. Similarly, one Br and H on this carbon. Now this is the Fischer projection, which is also signifying its stereochemistry. So what is, when you have an alkene which will be after formation of vicinal dihalide, if at all it is forming a chiral carbon, it will be optically active. But if it is a symmetrical compound, now what is a symmetrical compound? A symmetrical compound is that which if you divide using a plane, you get mirror images of each other. That's a compound, because now if you number this compound, you can number 1, 2, 3, 4 from this side also, from this side also. This is the definition of a symmetric compounds in GOC1. We have discussed a lot. Now, because of the presence of this plane of symmetry, because of the presence of this plane of symmetry, this compound, although having 2 chiral carbons, but it will be optically inactive, and this inactivity is because in the molecule only, let's say this is rotating in clockwise, so this will be rotating equally in opposite anti-clockwise direction. So overall optical activity will be 0, and such a form is called mesoform. So product is optically inactive, but due to formation of mesoform, the keyword is trans when subjected to anti-addition produces optically inactive product. But when it is symmetrical. What type of optically inactive product? Mesoform. And sir, what about cis? Sir, they produce optically inactive, but it will be due to one is meso, trans is meso, so cis will be the opposite, which is racemic mixture. So how we draw a racemic mixture? So draw that chiral carbon. This is CH3. You should not, if you have to become optically active, do not have the same plane of symmetry. So if bromine is over here, place bromine over here. Hydrogen over here, hydrogen over here. So this will be either dextro-rotatory or levo-rotatory. So 50% this will be formed, and 50% this I'm using a mirror. And what will be its mirror image? The same compound only, but with mirror of each other. As in, if here I have this bromine, so this bromine will be coming here, this hydrogen will be coming here, and to the far, this H and this Br. Dextro-rotatory or levo-rotatory compound can only be determined through experiment, but if one is dextro-rotatory, then mirror will be levo-rotatory. So both 50% of both are produced, therefore the product will again be optically inactive, but individual components are optically active, but the mixture is 50% this, 50% this, so you will get a racemic mixture. Sir, if alkene is not symmetric, then you get a chiral carbon and the product will be optically active. So, but that optical activity you can obviously guess by chiral carbon. But if it is symmetrical, it will be optically inactive because of either mesoform or racemic mixture. Mesoform will be created in trans, and cis will be creating optically inactive racemic mixture. Moving to another reactions. Moving to fourth extra point regarding halogens. Sir, they only do addition to alkenes? No. Free radical substitution can also be happening with halogens, but not always. Remember, when we were talking of alkanes, when X2 were reacting with alkanes in presence of sunlight or high temperature, because sunlight and high temperature generally makes reaction homolytic. So when homolytic fission takes place, what intermediate you get? Free radical. What is the most stabilizing effect as per GOC? Sir, resonance effect. After that, hyperconjugation, and least is inductive. Now, if you have an alkene, and if that alkene is in a possession of an allylic carbon. What is an allylic carbon? The sp3 hybridized carbon just beside an sp2 hybridized system. Because if this guy attains a radical, then this radical will be resonance stabilized. So, because this radical is not stable, it is resonance stabilized, very stable. So in such cases, these halogens subject to substitution, because this hydrogen can easily be removed. I mean, I'm not making hydrogen over here. We just take out this allylic group. If I remove one hydrogen, I'll be left with two hydrogens and a free radical will be coming. So what are the reagents? Sir, Cl2 and Br2 in presence of heat or sunlight, actually they are quite heated to an extreme temperature, because extreme temperature also will give that amount of thermal energy which has the capability to form to break C bond H. X2 bond will anyway be broken. The H which will be given by this carbon chain will be taking one halogen, so HX will be gone. So here HBr will be gone, here HX will be gone, HCl will be gone. So what about the other group that you're having? Sir, add add as in not an addition reaction. It will be a substitution reaction because we are substituting what? We are substituting hydrogen. So here the chain will be terminated by bromine. Here the chain will be terminated by chlorine, so you get a substituted product. Now one more reagent, it is also very famous, asked by JEE also, N-bromosuccinimide. Now what is it, sir? Succinic acid is actually 4-carbon dicarboxylic acid. So succinic acid, when undergoes dehydration, forms succinic anhydride. When it reacts with ammonia, it forms succinamide, and that nitrogen, when substituted by a bromine in presence of sunlight, this guy also undergoes homolysis. So you again get a bromine radical. So over here also chain is terminated by bromine radical. So these are some famous example where alkene can give substitution also, although whatever reactions we have seen and we will be seeing are generally addition reactions of alkenes. So this is a beautiful example of substitution reaction. We'll be seeing this again in alkyl halides. Now moving to the last extra part for addition of Br2. Now all these parts are important. The previous one also and this one also, although not there exactly in NCERT, but loved by mains because the common sense is there. Now talking about the last extra point, the formation of halohydrin. By the name it is suggesting halo as in halogen and hydrogen as in water is involved. So we said bromine water is actually Br2 and CCl4. But what if I actually add water, sir? So because bromine is a liquid at room temperature, therefore it can also be added to water. So if water is also introduced, then sir again even now solvent is only polar. If in CCl4, which was an organic solvent, Br2 was breaking as Br plus and Br minus, so in polar solvent it will also break as Br plus and Br minus. I am not denying to the fact that first Br plus will attack because bromine is electronegative. If get that positive charge, it will attack pi cloud. So carbocation will be formed? No. A cyclic brominium ion will be formed. We have already done it. But now instead of Br minus, OH minus will be coming into picture. Why? Because Br minus will be taken by H plus of water and HBr will be extracting away and OH minus will be now active species. So actually halohydrin Br2 in water will give you Br plus as electrophile who will be starting the reaction. Post that Br minus oxygen is more electronegative. So this OH minus will be now taking up the further attack, that is anti-addition. So let's say over here, so Br plus has attacked and formed a cyclic brominium cation. Now where you, sir, now deliberately by intentionally I have taken an unsymmetrical alkene, because if it would be symmetrical, on one side you will add Br, on another you will add OH. But now you have to think of common sense also. So that cyclic brominium cation is formed. Now in such cases what I'm suggesting you is, this is beautifully used. The pi bond is broken, sigma bond is there, and you get your cyclic brominium cation. But when this OH minus will attack, one point is carbocation formed over here? No. But for such cases you can again go to your GOC. Think of the positivity with a partial charge. Let's say if I have a partial positivity over here, so that will be, I'm not saying a carbocation is formed, because then rearrangement may take place, and because rearrangement was never found with when Br plus is attacking, therefore I'm not creating carbocation, but I'm asking you your basic GOC knowledge. Think of a partial charge. So if partially this carbon is getting positive charge, so it is what? Carbocation? Not complete, but partial carbocation. But it will be a 2-degree carbocation. And over here, it will be a 1-degree carbocation. So you tell me partially who will be having that extra stability of forming a carbocation? This guy. So this OH minus will be attacking this carbon, and therefore the bond will be breaking like this. So our product will be this CH3, CH, bromine over here, and the recently introduced OH minus over here, and this product is known as halohydrin. Now, one thing which I want you to learn, because NCERT also mentioned is the word which is Markovnikov addition. Although for mains question, most of the time it is not applicable, because it is a rule to learn the product, and the rule says negative part of attacking species goes to that double bonded carbon which has lesser number of hydrogen. Now why it is saying lesser number of hydrogen? If you have less number of hydrogen, then you will be more substituted. If you are more substituted, then you will form a better carbocation. Carbocation is not formed over here, we know that. So even if cyclic brominium cation is formed, the partial positivity will be stable over here. So if you just allow this Markovnikov addition, then you will, negative part is OH minus will be going to that double bonded carbon which is having lesser hydrogen, so it is going over here. But I am suggesting you Markovnikov addition you should know by the word, by the name, by the property, you should know. But while making product, you will never go wrong. While making product, think of the stability of carbocation. When carbocation is formed, first ring expansion if possible, rearrangement if possible. If not, like in this case, think of the partial carbocation. And wherever carbocation is stable, the product, the minus will be attacking at that point only. Now, stability of carbocation, just making you revise that GOC again. Most stable carbocation is stabilized by resonance effect. So benzylic carbocations, allylic substituted carbocations. Post that, see, count hyperconjugating hydrogens, and at last, if you have to give preference to inductive effect. So if a carbocation is not having resonance, so simply hyperconjugation you can always calculate. So now, sir, what about this? This is a simple case, Br2 and CCl4. So what I'll do? Sir, nothing. Take that alkane, that alkene, make it alkane and add. So just this CCl4 and water is making the difference a very good point. And now, because we have already discussed Markovnikov addition, so it will be much clearer for us to understand the third capital C, the third type of addition reaction of alkene is HX. Now, first we have done H2HH added, then X2XX added, now HX. So because H and X are different, so for symmetrical alkene, we'll add anywhere H, anywhere X, the product will be same. So therefore I have started, I'm obviously, because that you can obviously say 1H, 1X product. But if you have an unsymmetrical alkene, again the question will come, where H plus will go, where X minus will go, because HX is definitely a polar molecule. Now you know, alkene always allow whom to attack? Electrophile, that is H plus in this case. If electrophile is attacking and getting added, the mechanism is called electrophilic addition. We have seen these mechanisms. But now, as per product which we have seen, rearrangements are also seen over here. That means here complete carbocation is formed. So whenever this HX or any polar molecule, as a matter of fact, which we'll be seeing in the later slides, but mechanism will be this only. So this will make you many more reactions. So H plus will attack, carbocation will be formed. Sir, where carbocation will be formed? If the pi cloud is going to this H plus, if here carbocation comes, it is 2 degree. If here it comes, it is 1 degree. By in GOC, electromeric also we have seen. So you tell me where it will be formed. At 2 degree. This is very simple. But this is a simple case of propene. If you get another alkenes, then sir, we'll think of carbocation stability. How? Resonance stabilized, most stable, then hyperconjugation. Let's say apply hyperconjugation only. How many hyperconjugating hydrogens it has? 6. So stable. If you get a plus over here, then how many hyperconjugating structures you will be having? Only 2 hydrogens, because then this guy will have that H. So obviously 6 is more. So more stable carbocation formed. Can you rearrange it to a better position? No sir, this is 2 degree. Here it will be 1 degree. Here it will be 1 degree. So while I will degrade myself, I'll be here only. So no rearrangement, but because carbocation is formed, so it will be the slowest and rate determining step. Now this is a piece of cake for us. Again, X minus will attack. you will get your product. What type of product it is? It is also Markovnikov product. Why? Because negative part is going to that double bonded carbon which is having lesser hydrogen. But how we are learning this? We are learning this through the common sense that product is always formed as per stability of carbocation. Moving forward. So this brings us to second point of addition of HX. A scientist named Kharash has observed that when he used HBr only with HBr, when he used HBr with an alkene, he found that if peroxide was used in presence of sunlight, then whatever product Markovnikov has predicted, the addition product, the product came out to be just exactly opposite. As in, negative part of attacking species for HBr, negative part is Br, was going to that double bonded carbon which was having more number of hydrogens. And therefore, this product and this effect is called Kharash effect or peroxide effect or anti-Markovnikov addition. Very, very important. Now, sir, how it is happening? Obviously, for symmetrical alkene, you will add HX, so no problems. So obviously, I am deliberately again taking that unsymmetrical alkene. So, as we all know through GOC, that peroxide and sunlight results in the formation of free radical. For Markovnikov's, the attacking species was an electrolyte. So the mechanism was electrophilic addition. But actually over here, the mechanism is free radical addition. So because mechanism is only getting changed, which is getting changed to free radical addition. Now, sir, who is the free radical which is attacking? The main chain initiator, like in case of alkane, chain initiation. The main chain initiator is this catalyst guy. This RO, I mean, this can be any alkyl group. It can even be benzoyl peroxide. So this O and O, because they do not have any electronegativity difference, and moreover bond order of oxygen is also 1. So in presence of sunlight, this peroxide bond can easily be broken, and therefore peroxide always initiates free radical mechanism. So now this electronegative oxygen is very unhappy because a radical is there. So it will try to satisfy its radical. Now it will try to attack whatever possible. In case of alkanes, only alkanes were possible, were present. But now HBr is also present. Alkene is also present. Alkene is also relatively, it is a minus cloud. So minus minus repel. So it will try to attack this guy will try to attack the weakest person. Who is weakest person? Hydrogen. So this will be attacking HBr, forcing homolysis of HBr. So once HBr is homolytically getting broken, this hydrogen will be carried by this oxygen, and now this oxygen is happy. Chain terminated, but the chain got propagated actually, because this resulted in the formation of bromine radical. Now bromine is also electronegative, so it will try to attack whatever possible reactant it has. What is the other possible reactant? Now there is only availability of alkene. So now this Br radical is going to attack this alkene. Now again I'm using your GOC common sense. Obviously, if radical is attacking, so here also homolysis will take place. You tell me, if bromine attaches to this carbon, it will be a 2-degree radical. If bromine attaches to the middle carbon, it will be a 1-degree radical. Radical are also electron deficient, so they will be always stabilized by, for inductive effect, they are thought of like carbocation. In GOC we discussed. So because they are electron deficient, so a 2-degree radical will be more stable. In all further cases, radicals are also first stabilized by resonance, then by hyperconjugation. So which radical will be more stable? So 2-degree. So this Br radical, when it will be attacking to propene or any unsymmetrical alkene, as a matter of fact, stable radical will be created. So what radical we will be getting? This CH2 And this beautiful 2-degree radical, I'm writing that also, it is a more stable free radical. This is as per GOC. That's why I say that is the main foundation. Now, after formation of this free radical, radicals will try to now terminate the chain. So bromine, see bromine added over here. So there will be availability of another molecules also. So again a chain propagation step will be taking place, and this guy will now be attacking another HBr molecule. Another HBr molecule will again be getting homolytic fission. The hydrogen, the weaker one, will be acquired by this radical, creating one more Br radical, and the chain will continue to propagate. So percentage, if this H is going to this radical, you will be getting your product as per opposite of Markovnikov, that is anti-Markovnikov rule. Now, this much is more than sufficient for mains, but one thing I'm iterating. Can you tell me what is the reactivity order of HX? Yes, sir. Reactivity order of HX, if you ask, sir, HI will be most reactive. Why? Bond length for electrophilic also and for free radical also. Reactivity is actually HI is most reactive, followed by HBr, and the least is HCl. HF I am not even writing because HF is a very weak acid. Because bond length is very small, because fluorine is very small, therefore HF does not easily dissociate to form H plus and F minus. So what is the reactivity for hydrogen halides? Sir, this. But this reactivity is for electrophilic addition. Sir, then what about free radical? I have said why I have not written HF, because H plus and F minus is not formed. For homolytic fission also, the bond dissociation energy for HCl is also high. So this guy will also not form radical. So that's why this person got cancelled for Kharash effect for homolytic fission. Sir, but why only HBr? HI is bond length is very large, so it can be easily homolytic fission also. It for HI can easily take place if HBr is getting fission. So this will be requiring less energy. Yes, because this is the order of reactivity. So actually HI easily gets homolytic fission. I radical also forms, but when this I radical is formed, another I radical will also be coming, will be generated. I radical and I radical love each other because they form I2. I2 is a solid. That solid precipitate out of the reaction, and because it precipitate out, reaction cannot proceed backward. It proceeds to forward direction only. So because iodine radical forms I2, that's why with HI also a Kharash effect is not observed. This is also a very important logic you should know. Moving forward. So moving forward, applying the same logic of Markovnikov addition and electrophilic addition which we have seen, let's say now I have water and sulfuric acid with the same logic, added getting electrophilic getting added to an unsymmetrical alkene. So first thing, water is, sir, it is not a it is not an ionic compound. It cannot form H plus and OH minus, and very partially it can form. So for water, you always have to add few drops of concentrated acid to make the medium acidic, so that the reaction can be started, because this H plus will definitely attack the pi cloud and forms the carbocation. Carbocation will be formed. It will be ring expansion also, rearrangement also, because I'm taking a simple case, because JEE mains generally do not ask that ring expansion, the best question we have done as per JEE mains. But since we have discussed it, so I'm telling you that H plus will attack, carbocation will be formed. Think of whatever possibilities, and the learning method is called, because negative part will be going to that double bonded carbon which is having lesser hydrogen generally. So it is also Markovnikov addition. So what we are going to beautifully have over here, so 3 carbon, negative part of attacking species. In case of water, it is OH minus ion. So this will be 2 propane 2 ol. Sir, what about H2SO4? I'm taking pure H2SO4. NCRT example it is, so very important. So sir, H plus again it will be giving, but then it will be having bisulfate. So bisulfate will be negative part. Okay. What is bisulfate? Sir, H2SO4, H plus must be given by oxygen. So that oxygen will be having that minus further getting connected to the other groups. So this is nothing but propyl hydrogen sulfate or propyl bisulfate. Now, one point I'm mentioning over here. When we talk of alkene, there are many NCRT important reactions like hydroboration, oxidation of alkenes, like with alkenes you can also do oxymercuration, demercuration. It is not there in NCRT, but we will be discussing much about addition reaction of alkenes with water and different types of water. I mean, for oxymercuration, demercuration, you again can add HNOH through the processes which we will be discussing but separately in alcohols chapter. So maybe you will be getting some question that will be related to alkene, but alkene can also react to form alcohol. So those will be preparation of alcohols and they are also very important, but I will be dealing about those reactions of alkenes in when we will be studying alcohol. So moving forward and discussing about the fifth set of reaction of alkenes, that is their oxidation. With alkanes also we have this knowledge that what is oxidation. If you supply oxygen to an organic compound, to a hydrocarbon, it will completely burn and form CO2 and H2O. But if you control the number of oxygen given, then you may have various useful oxidized products. So oxidation of alkenes, you may completely burn it, it will just form CO2 and H2O, but that we have already done. So now talking about the controlled oxidation, so it can be done again using some suitable reagents. The very famous reagent are over here, the three. First one being Bayer's reagent. Now what is Bayer's reagent? It is cold, dilute and aqueous cheminophore. It has to be made cold at ice cold water situation. So it is somewhere around 273 Kelvin. Now through inorganic you must be knowing, if not I'm telling you, cheminophore is a dark purple colored solution. So sir, when cheminophore is existing, the color will be existing. When cheminophore has reacted, so the color will be gone. So again, like bromine water, it is also your test of unsaturation. Now these are very important slides. That's why I've written them beautifully so that you take them as your notes. Now, what does Bayer reagent do? Sir, it reacts. It reacts with alkene and forms vicinal diol. Now, because this Bayer's reagent is very dilute cheminophore, so the extent to which it will oxidize will be less. So it can break a weaker bond. The pi bond only is broken by Bayer's reagent. Sigma bond cannot be touched by this dilute cheminophore. So you get a vicinal diol, but because Bayer's reagent is gone, so color will be gone. So it's a test of decolorization of dark color of Bayer's reagent is a test of unsaturation. Second oxidation process is ozonolysis, very loved by JEE. Now what is ozonolysis? So you react alkene with ozone. Sir, oxygen will get into this alkene and actually it will form an ozonide. Intentionally I am not writing this ozonide because writing ozonide is, I mean, I've already made it, but I want you to learn this slide. Now that ozonide will be formed. What to do with that ozonide? You reduce it using zinc and water. Zinc will restrict the further oxidation and will reduce this ozonide. And what you will get? Now, you can clearly learn this product because in advance also, mostly this knowledge of learning will be making your question. Now, but I'm talking of reductive ozonolysis. What is undergoing after formation of ozonide? Who is subjecting to that reduction zinc in presence of water. Now, how to make the product? Sir, here complete oxidation will take place. Yes. So here the C double bonded C, this bond will be broken, and what will be introduced? A double bond can be satisfied by an oxygen. So out of those 3 oxygen of ozone, 1 oxygen has been taken away by water in form of H2O2. Not giving you those details. The important point is the remaining 2 oxygen are given to this carbon and that carbon. Sir, why you have specially mentioned this hydrogen and those hydrogen which is connected with the double bonded carbon? We have reached to ozonolized product. Ozonized product we know, but if we use a even stronger oxidizing agent, sir, it will do this much. And that those stronger oxidizing agents you know from your class 10th. The famous D block compounds K2Cr2O7 and KMnO4. One extra point, K2Cr2O7 is a strong oxidizing agent only in acidic medium, while KMnO4 is a strong oxidizing agent in both basic and acidic medium. So these strong oxidizing agents will do this much. What ozonolysis was doing, they will also do, but they will do one more thing. Whatever H is there in the carbonyl carbon, that will also be replaced by OH, because they will be oxidizing one step higher. But C bond C is never broken. If you look over here, the C bond C is still intact, because the action of oxidizing agent is to oxidize the sp2 hybridized carbon. They cannot break carbon-carbon bond. That is not their capacity. Yes. To the carbonyl carbon, whatever hydrogen is present, 1, 2, 3, whatever, they will oxidize all those possible hydrogens, and that's why I have given them a different color. So this H will be replaced by an OH, will give you a carboxylic acid. This is an acetaldehyde, 2-carbonaldehyde. So this is acetic acid, 2-carbon acid. That is 1-carbonaldehyde, that is general name is formaldehyde. So you will be getting, sir, formic acid? No. Why not formic acid? Because one, you have 2 OH, 2 hydrogens. So both the hydrogens, because strong oxidizing agent oxidizes all possible C bond H. So you get 2 OH, and in through alkanes also you know diol. 1 carbonyl carbon having more than 1 OH, as in 2 OH is not stable, it will undergo dehydration. So this OH and this OH will form beautiful green colored water. I mean, I have marked them green, water is not green. And this C with this double bond O and this double bond O will form a CO2. So ultimately it has been completely burnt, CO2 and H2O. If there is C bond C, we will not, the C bond C is not broken by oxidizing agent. Just with this knowledge, you can make number of questions involving oxidation. One point I'm making, but not famous in mains, so I have not written that. I have not made them for you. Now, what is it? Actually, ozonolysis can also work as a strong oxidizing agent. How? Don't reduce. Roman number 1, you make ozonide and then you just add water. So that will become an oxidative ozonolysis. Sir, what oxidative ozonolysis will do? What strong oxidizing agent is doing? So if there is, let's say there is no zinc given, then the product will be same as strong oxidizing agent. So ozonolysis will also be acting as a strong oxidizing agent. But NCERT always uses reductive ozonolysis. So I have restricted myself for mains till there. Moving to the next and the last reaction of alkenes. The last reaction of alkenes is polymerization, but thank you to NTA, because polymers chapter has been removed from your board syllabus also, and JEE mains syllabus also. So actually polymers, they are of huge importance industrially in our day-to-day life. Ethene is a monomer, let's say 1 molecule. You take n number of ethene. Okay, sir. A specific temperature, a specific pressure, and in presence of a specific catalyst. Those you have to learn when you learn polymers. So not mentioned over here because not required. But during the action of extreme temperature, extreme pressure, and in presence of specific catalyst, they polymerize. How? Pi want to become sigma. So the monomer opens their pi bond and start connecting to the molecule like them only and forms a addition polymers. And this addition polymers, if monomer is ethene, this becomes polyethene. If monomer is propene, it becomes polypropene, with just the addition of the molecules this side also and this side also. So n number of molecules will be added and a linear polymer will be formed, which will be having huge importance. So this much only you should know about alkenes. Now, why I was using probably, because of this logic, this dienes reaction was actually started by advanced obviously, but now mains have also some of the time started asking it. So I'm giving you this knowledge because this is a good logic also. Now, generally how you make your product? By determining the stable intermediate. Why? Because only those reactant can form product who has the capacity to climb this activation energy barrier. We already did this. This is a chemical kinetics logic. What reactant can climb the activation energy barrier? Sir, they can be climbed not by reactant, by their intermediates. So whatever stable intermediate you get can only climb this activation energy barrier and form product. So what product we normally form? Through this knowledge. This knowledge is knowledge of chemical kinetics. So what product we generally make? We make a kinetically controlled product. And while making a kinetically controlled product, which we have already done, while making that product, we think of the stability of intermediates. So stable intermediates climb this activation energy barrier, although they have high energy also. But because they climb this activation energy barrier, so they only result in the formation of product. Now, let us do this, apply this common sense for a diene. Okay, sir. Let's say this diene is also undergoing attack of H+. That's why I'm including in alkenes electrophilic addition. Okay, sir. This much so, sir, we know. What is advanced about it? It is nothing. So this pi can also go, this pi can also go, both are same. So let's say this is closer, so I'll make this attack. So what you have formed? Sir, pi, this pi is as it is. Now you tell me, this carbon or this carbon, who will be getting this hydrogen? Sir, this one. Why? Because carbocation over here will be more stable. So this carbocation will be formed and I have added that hydrogen over here. Let me mark this. This is 1, 2, 3, 4. So I have added the hydrogen at first carbon. Now, what carbocation? So this is very stable carbocation. How? It is resonance stabilized pi sigma plus. So because this is a resonance stabilized, let me make its resonating structure also for you. So pi sigma plus. So this plus can be even carried by. So this is very stable. Okay, beta. Now because you are watching a stable carbocation, now pi bond will be coming here and this plus can be even shared by this carbon. So these are the two possible intermediates, and because of resonance stability, this carbocation is very stable. Yes. Now, let's say we have HX. So after attack of H plus, who will attack? Sir, X minus. So if you make the attack of X minus possible over here, then let's say that X minus is attacking. This will, because this is a 2-degree carbocation. Resonance stabilized, this is also resonance stabilized, but because this is resonance stabilized also 2 degrees, so this is more stable. What? Intermediate. And if you attack, if the X minus attack this stable intermediate, obviously sir, this intermediate will be having the capacity to climb this activation energy barrier, so this should also only produce the product. Yes, I'm not denying to that fact. So let me make that product for you. So let me take this. Actually this is not helping us, na? But no worries. So the plus has gone from here because this carbon has got electron of X. Now you tell me what type of product it is. Sir, it is 1,2 product. This is 1,2 addition product in case of dienes. And whenever you have 1,2 addition, it will be a kinetically controlled product. Sir, but this is common sense. Actually, what happens is if you increase the temperature for a particular reaction, if you increase the temperature, so then those intermediates who are even not stable will attain that kinetic that energy, because I'm supplying that energy by applying more temperature. So even those people who cannot climb so much high can also reach and climb this activation energy barrier. For example, some only most strong person can climb 16th floor easily. I cannot climb, I'm fat. But if I use a lift, I will also reach 16th floor. So lift is provided, that lifting action is provided by high temperature. So when high temperature has provided that potential to the less stable intermediates also. So this has also reached, this guy has reached by itself only, but this intermediate has reached using lift, high temperature. Now both are there. So both will fall down and both will form product. Now who will decide what product will be formed more? Product stability. Because now both the intermediates have crossed the barrier. So I am not denying that they have to cross the barrier. But if the barrier crossing is easily attained because of high temperature, anybody can reach. After forming product, who will be deciding? What will be the deciding criteria? You are also there, I am also there. If someone is forming a stronger product, a more stable product, equilibrium will be shifting to that direction, so percentage of that product will increase. Yes. So what I'm saying is, just look at this structure. If I add, let me make this with another color. If I add X minus to this position, what is the product that I'm going to have? So this you will be obviously taking, but this plus will be satisfied by this X. So this is 1, 2, 3, 4. So this is 1,4 addition product. And look at this product. So here the alkene is in between. So it will be having inductive effect from both the sides. Whereas this is a alkene at the terminal position. So it is not having plus I effect from this side. It is having plus I effect from this side. So you tell me which alkene is more stable. So this is more stable product. And this was beautifully asked and started by JEE Advance. Actually, they used an inorganic fact. What after polymer? So this becomes the thermodynamically controlled product. Okay, this is TCP, that is KCP. So initially at normal temperatures, I form kinetically controlled product, which we know. But if temperature is high, we do not think about intermediate stability. We have to think about product stability. Now, what inorganic tadka, what inorganic spice Advance made to the students? That is, if you take HBr, for HBr, actually even room temperature is a very high temperature, because that activation energy barrier is different for different species. So for HBr, even room temperature, actually the temperature is around 40 degrees Celsius, but room temperature these days, 40 degrees Celsius is only room temperature for us. If you are staying in Delhi, then you must be I mean, this is a cold period, but obviously you can relate to that 40 degrees Celsius is normally a normal temperature, sir. So actually for HBr, even room temperature 40 degrees Celsius is that extreme temperature. So due to that extreme temperature, what product will be formed? Sir, thermodynamically controlled. Thermodynamically controlled product is what? Sir, product stability 1,4 addition. So over here, Br will be coming here, and the H will be coming here. This is a thermodynamically controlled product, as in 1,4 product is formed. So this will be your answer, and the alkene will be over here. The T, the thermodynamically controlled product. And what is normal temperature then, sir? It is very cold, minus 80 degrees Celsius. So minus 80 degrees Celsius, what you will be getting? The 1,2 addition product, which you obviously know through the stability of intermediate. Now, for HCl also, room temperature, we think room temperature is normal temperature. So if you do this for HCl, actually at room temperature only, HCl will form the normal product. How you form the normal product? Thinking about the kinetically controlled product, because, sir, in the whole GOC we have studied about intermediate stability, so we will think about intermediate stability. So for HCl there was no bouncer. What do you think? The more stable intermediate form, it is forming. HBr forms that product at minus 80 degrees Celsius, and at room temperature, HBr is known to form a thermodynamically controlled product. This finishes our alkenes. Now, moving forward, I want you to take out your rough copy and pen. We'll be discussing these JEE mains question. I'll be moving aside, and you can pause and you can try, and then we'll be attempting these questions together, and together we will, in this video only, over here only, at this point of time only, if you're watching me, if you're watching it for the first time, doesn't even matter. Pause, attempt, and you will only, with this 5-10 questions, you will get to know and come in sync with the fact that yes, mechanisms and common sense is required. You do not have to mug them up. What mug? I mean, all the common sense related to not all possibilities or reagents. All the reagents you should know, that is there in NCERT. Now, this is a question which is having a alkyl halide. Alkene is also there. This is a bulky base, tertiary butoxide with potassium salt. So potassium tertiary butoxide is a is a bulky base. Hoffman will be clicking inside your head, sir, because alkene is also there, so probability of conjugated alkene formation will be there, because I'm not asking you to learn those Hoffman facts. What product, according to Saytzeff also, Hoffman also, what product is formed? Sir, more stable product is formed, more practical and probable product should be formed. So obviously, because both these carbons are equally hindered, so it will not make that impact to that bulky base, and moreover, sir, resonance stabilized alkene will be more stable. So we will form a resonance stabilized beautiful alkene like this. Okay, I'm sorry. This pi bond is already there, so we'll be forming like this. Now, next step is ozonolysis. So what does ozonolysis tell you? C double bond. I mean, watch the double bonds, break the double bonds, and what you will get after that? Double bond on all the sides. All the carbon, as in this carbon and this carbon, it will get the double bonds. So this first, second, third, fourth. This carbon has recently introduced with this double bond. Obviously, there will be an H also. What is the other part? So these two carbons, but they will be getting separated, and you will be having these double bonds here also. Done. Now, but you will say, sir, in NCERT, in the reactions that we have given for ozonolysis, that was ozone followed by zinc and water. Sir, this is just ozone and this methyl substituted sulfur. We do not know this reagent. So you have given us only reductive ozonolysis. Although we know oxidative ozonolysis also takes place when we do not use zinc. Sir, zinc is not there. So maybe it will be oxidative ozonolysis. Look at the option. It is an aldehyde, and whatever options you are given with, they are also aldehyde. So JEE doesn't want you to learn all the possible reagents that will be existing in nature, but you should at least know the common sense that reductive and oxidative both can take place. And because no option is serving you the possibility of oxidative ozonolysis, so that means this will also be one of the other reagent apart from ozone followed by zinc and water. This can also be used as reductive ozonolysis reagent. Do not learn it, because now options are telling you that if you know the logic that maybe oxidation can be happening or reduction can be happening, so you will definitely crack the answer. You are having two products, only one option is giving you those two products, option C. Moving forward. Now I'm moving aside. Try this question. So I hope you have attempted. That's why I've given the answer also. You must have got the answer. Now it is saying you are using KMnO4 H2SO4 acidic medium strong oxidizing agent. So what strong oxidizing agent do? Sir, we already know. Break this double bond, add double bonded O. So you have a 6-membered carbon chain. Once you break the double bonded carbons, you get double bonded oxygen. But here also and here also, one free valency will be of hydrogen. Now this is a strong oxidizing agent, so that hydrogen will be replaced by OH. And now you will be getting a dicarboxylic acid. Now this is an NCERT fact. You will be getting this NCERT fact when we're discussing carboxylic acid chapter. A 6-carbon dicarboxylic acid is commonly known as adipic acid. So that will be your answer. But I'm giving you details also. Oxalic acid is 2-carbon dicarboxylic acid, picric acid and acetic acid. Acetic acid we know, CH3COOH. This is picric acid, a tri-nitro substituted phenol, and this is obviously oxalic acid, which is 2-carbon dicarboxylic acid. Moving forward, this JEE 2019 question, let's try. Yeah, so I hope you have attempted the question and got the answer. But let me tell you one thing, it's a good question, it's a tricky one, because the question is asking you to have an alkene. Just to be time efficient, I have already drawn this for you, because one example of ring expansion we have already done in detail. So doing this with beautiful picture, so you can save it, keep it as your class notes also. Very good logic. Now, sir, alkene attacking H plus, carbocation will be formed, and this carbon will be getting that positive because it will be more stable carbocation. So you can see that stable carbocation. Now this stable carbocation is quite stable. Over here also it will be 1 degree, so it is best stable carbocation. You can see it is getting hyperconjugating hydrogens 3, 3, 6, and this 1 is also next to it, so it is stabilized by 7 hyperconjugating hydrogens. Moreover, 5 and 7 membered rings are not unstable. Yes, they are definitely less stable with respect to 6 membered, because 6 membered ring has 0 bare strain. 5 and 7 member ring have strain but very minimum, but they are not unstable. So many a times in questions you can get this also, that 5-membered may not get ring expansion and forms a 6-membered. So but how will we know that? Will we have to predict? We are not doing experiment. Question will not ask you to do experiment. Question will be just asking you a common sense, but that common sense I'm giving you. 5 and 7 member ring structures are not unstable, so they can also be formed. So if at all you are forming a stable carbocation, like for example, let us say 5-member ring is good, it can be formed. So do not do ring expansion. Then what option you will have? Rearrangement. Sir, over here it will be 1 degree, over here it will be 1 degree, and even this carbon comes over here, then over here also the number of hyperconjugating hydrogens will be less. You can check and do it. So sir, that means if we suppose there is no ring expansion, then this is the best possible carbocation. So you will get a Cl minus ion over here only, and you will get your alkyl halide. If you just go and look at the options, this option is given to you, where just look over here. These CH through on at the same carbon, and chlorine is getting attached at the same place with a 5-membered ring structure. So this is already given in option D. But if you look at other options, there is one option which is having a 6-membered ring. There is another option which is also having both 6-membered ring. So now we will think of ring expansion also. But I am telling you, 5-membered ring structure are also not unstable. And whether practically 5-membered ring is actually changing into 6-membered ring does not take place all the time. So if at all it is taking place or not, sir, how will we know that? Options will tell you. Like for example, you have that 5-membered ring option with you. Now I'm not denying to the fact that you have to think of ring expansion, because 6-membered is best, 5-membered is good. But if someone is given an offer of getting the best result or good result, if I ask you to, you want AIR1 or AIR10, you will definitely say I want to become AIR1. You will get the best rank. So similarly, I am asking you to think of ring expansion, so I'm doing that also. Like this carbon will be giving electron to that carbon and will be forming a 6-membered ring. If you properly make it, beautifully make it like we have done it, so I've done everything for you. So this will be 6-membered ring. Now the next offer again, over after ring expansion, we also give offer for carbocation to get rearranged if it is getting stabilized at the adjacent position. So over here this is 2 degree, but if it rearranges and gets over there, it will be more substituted, but that carbon is having no hydrogen, so no worries, the complete methyl group will be shifting. I told you. So this methyl group will be taking electron and coming to this carbon, so this positivity will be going to that particular carbon. Gone, sir. Now attack of Cl minus take place, so you will get this product. So if ring expansion take place, you will get a 6-membered ring and methyl and chlorine at the same carbon like this. Now let us go to the options. 6-membered ring, yes, but this 6-membered ring is having methyl, but it is also having this carbon. This carbon is not at all available. It should be direct chlorine. Look at this option. Chlorine is coming here and there are 2 methyl groups. Again, how that extra carbon has come? If you look at your answer, there is only 1 extra carbon after after other 6-membered ring formation. So actually in the option is telling you they have given option of 6-membered ring structure, but the option of 6-membered ring structure they have given is not correct. So sir, if that is not correct, then what will be answer? That will be the answer. That is what I was telling you. 5 and 7-member are not unstable. So practically, if they are undergoing a ring expansion, then the cyclohexane would have been the major product, and they would have given that cyclohexane which should be formed. But they have given cyclohexane structure, but the structure containing chlorine is logically not correct. So logically speaking, we will tick that option which we are getting out of our reaction mechanism. So because this we are getting, therefore this option D will be your right answer. A very beautiful question. That is what I was telling you. Now I guess this is a quite easy question, so I'm not giving you time also for this, that I'm not moving aside. Anyway, I'm not giving time, but I'm not moving aside because the team, remember team, bromine adds to alkene via what? Via the stereo specific and stereo selectivity, how we have understood and learned it through the keyword team. Remember team? Okay. So in trans alkene, when anti-addition takes place, meso product is formed. Now read the question. You have trans butene. Now because this is butene, so it will form a symmetrical structure. We have done this question only. Because it will form a symmetrical structure, the product will be optically inactive. But once bromine attack from its upside, the other one will be coming from downside. But the probability will be, I can attack upside 50%, I can attack downside 50%. So you will getting 2 different types of product. But both the products will be a mesomeric product. This we know through our keyword team. So which option is asking you to have a mesoform? This is saying you get mesoform, but it is saying you have enantiomers also. No, then the mixture will become optically active. I told you it will always be optically inactive. It is saying enantiomers. No, enantiomers, racemic it is saying, but it's saying enantiomers also. It is saying 2 identical. 2 will be formed because it can be either all dextro, all levo. Then in that case 50% this will be formed, 50% levo, so it will be a racemic mixture. But racemic mixture is formed in case of cis form. For trans form, you will be having a mesomeric. How many? 2 identical mesomeric structures. A very good example of whatever we have done till date. Now moving forward, now let us attempt this question. Let's see you can make it or not. Now this is also a good question which is shouting at you and telling you, do not learn and mug up reactions. Try to understand the logic and mechanism around it. Now it is saying you have to use HCl and the product formed after reaction with alkene should be an anti-Markovnikov product. Sir, but only HBr gives anti-Markovnikov product, that too not alone if HBr presence is there in presence of sunlight. That we have seen through NCERT logic, but this is also a JEE Mains question asking you to apply your common sense. Read the question. It is saying you all these four reactants alkenes are treated with HCl and they have to produce anti-Marconi product. If leave anti-Marconi product, if you attack these alkenes with HCl, what will happen? We know mechanism. There is no peroxide, so first H plus will attack. H plus will form what? H plus will form carbocation. So who will form stable carbocation? Let us see. This will form a carbocation over here because this will be 1 degree, so 2 degrees, okay. This carbocation is stable. Do not think of 2 degree because this is only carbon giving inductive effect from one side. I told you for carbocation stability, always think of first resonance effect. Sir, this carbocation is resonance stabilized. Lone pair sigma bond plus. So this carbocation will be very happy to be formed. And because it will be formed, so negative part will be coming over here only. So this is Markovnikov addition. So not an answer for us. Now, I'm leaving this option. I'll tell you why. Now, if carbocation is coming over here, now let's say if at all it is coming over here, because if it will be coming over here, then only it will be having Markovnikov addition, as a negative part will going to that double bonded carbon which is having less hydrogen. That is Markovnikov. But Markovnikov is happening why? Because of common sense. So I am applying that common sense only. In that time also, while telling Markovnikov, I have told you this only. Now, this chlorine actually it has also plus sigma bond lone pair, so it is also applying plus R. Although I am telling you we will be doing it in alkylide, it is an electron withdrawing group, because although it is applying plus R, but it is minus I also, so we'll do it in alkylides. But because it is doing plus R, so ultimately this guy will be getting, because it is plus R, so it is stable. I mean, it is still, this carbocation is resonance stabilized. Now coming over here, if I get a carbocation over here, so this is also very beautiful, resonance stabilized. So resonance stabilized, so not an answer. So why I have not completely rejected this one? Because as I told you, chlorine applies plus R also. So I'm not denying to the fact that this carbocation is stabilized by resonance, but actually there is some extra knowledge about it which I will be dealing in alkyl and aryl halides. So sir, but how we will do the question? If you look at option B, it is quite clear to you that this carbon is attached with 3 electronegative fluorine atom, which are highest electronegative elements. So because of 3 fluorine atom, this will be a very strong electron withdrawing group. Sir, but you are seeing inductive. See, it's inductive also. That's why I'm telling you. It is also minus I, but there are 3 fluorines, although not directly attached, but 3 fluorine. If number of electronegative atom increases, obviously this will be most electron withdrawing group, and because this is most electron withdrawing group, so carbocation will not be coming over here. Why carbocation comes to a carbon which is more substituted? Because generally those substitution gives electron donating nature. This guy is a strong electron withdrawing group, so why I will be coming over there? Because H plus is attacking, so carbocation will be formed, but carbocation will be coming to this carbon because at least it is far away from the electron withdrawing group. And now if carbocation is formed over here, because it is at least trying to stabilize itself from very strong electron withdrawing group by being very far from it, so minus will be coming over here. So now negative part has gone to that double bonded carbon which is having higher hydrogen. So this is anti-Marconi. A very beautiful example of JEE Mains asking and shouting at you to always learn the logic, not the theory. Moving ahead, let us try this question. So in this question, alkene is directly attacking, getting attacked with HBr only, and because peroxide is present, so anti-Markovnikov product will be produced. So this alkene, the name that is mentioned, we have drawn the structure. The compound A is this, because bromine will be attaching to that double bonded carbon which is having a lesser hydrogen. And the common sense is, because first who will be attacking? Br radical, so radical will be that green radical. And where that green radical will be more stable? So sir, over there, because here it will be 3 degree. So this is the product that we have formed. Now question is asking you number of stereoisomers possible. So every carbon, if all the 4 substituted bonds are different, then it will become a chiral carbon. So let us mark those chiral carbon. Sir, we can clearly see this is one chiral carbon and this is one chiral carbon. Rest all carbon are having same number of similar hydrogen. So not all 4 bonds are different. So because chiral carbon are 2, so what is the number of optical isomers? 2 raised to the power n, simply because the chiral center is 2, so 2 raised to power 2 is, answer will be 4. Moving forward, now these simple questions are asked. Now next question is a question relating to physical properties. This is getting reacted, sir. This is nothing but peroxide. This is benzoyl peroxide. The O bond O linkage will still be there because 2 molecules. So sir, peroxide HBr, what will be formed? Beta, simply anti-Markovnikov product. So in this 4 carbon chain, you will be having bromine at first carbon. Anti-Markovnikov product. Sir, it is only HBr, so it will be Markovnikov. So it will be getting attached to that double bonded carbon which is having lesser hydrogen. So it will be 3 carbon, 1 bromine and a methyl group. What about this one? It is a symmetrical alkene. So do whatever, add H and Br on at one side, and anywhere you do anything, you get this 2-bromo butane. Now remember the boiling point thing. I told you everything is same for the physical properties are same. So because this is most linear, so more be the surface area, more is the boiling point. So this P will have the highest boiling point. This is also 4 carbon linear chain, but at least it is having branching at second carbon, so it will create some a bit compactness. So boiling point of this R will be less. But this Q, sir, this is 3 membered, this is highly branched. So more highly branched, compactness will increase, and this Q will have the minimum boiling point. So your answer will be option number A. Moving ahead, I guess these questions are quite simple and you will get the confidence that you need common sense also, apart from just mugging will not help you. Moving ahead. A hydrocarbon X having formula C6H8. Okay. So if I have 6 carbon for saturation, I should have 14. 2n plus 2. How many hydrogens I'm falling short? Sir, 4 plus 2 as in 6. So 6 hydrogen as in, what is the degree of unsaturation? 6 by 2 as in 3. So there is 3 degree of unsaturation. I told you, you do not have to learn the formula. Just count the number of hydrogens falling short in GOC we have discussed. So degree of unsaturation is 3. Now it uses 2 moles of hydrogen. Array, degree of unsaturation is 3, but it is still using only 2 moles of hydrogen. That means out of those 3 du, 2 will be of pi bond. Now let us think what that one will be. Sir, cyclic ring also creates a 1 du. And it is saying that on catalytic hydrogenation, it gives only 1 mole. The 1 mole of the compound uses only 2 moles. So there will be only 2 bi bonds and one will be cyclic. Okay, sir. So we know that this is a cyclic compound having 2 pi bonds. Now on ozonolysis, now it is giving you structural information. That's why I told you ozonolysis is very important. This compound yield 2 moles of methane dicarbaldehyde. Now methane di as in 2, carbaldehyde as in CH double bond O. CH double bond O. Okay, this will be H2. So methane dicarbaldehyde. Sir, if 2 of these are produced, that means ozonolysis do what? It breaks double bonded carbon and add double bonded O. So double bonded O added from this side, it will also be added from the other side. That's why you are getting 2 moles. That's why you are getting 2 moles of these products. That means these are the members who will be just connected by double bond. So what is this? Sir, this is a 6-member carbon chain. Let us do the numbering. The numbering will be, you have to give minimum number to multiple bonds. So start from anywhere. So it will be 1, 2, 3, 4, 5 and 6. You can make a beautiful photo also. I'm just telling you, you just pick a pen. If you know the logic and confident about it, you can quickly do the answer. So answer will be cyclohex 1,4. Cyclohex 1,4 diene. Your beautiful answer will be D. Now this is a question related to mole concept. Let us attempt this question. Yeah, so if you know just the basic detail of this organic reaction, that pentene is nothing but C5H10, 5 carbons. When it gets reacted with Br2, it produces a vicinal dihalide. So that vicinal dihalide will be this 5 carbon will be as it is, and one bromine will be coming over here, and one bromine will be coming over here. That's it. So we know if we just know this organic basic, then we know that, sir, 1 mole of this is reacting with 1 mole of this. So if n moles of this is used, then n moles of this will also be required. So you are given weight of pentene. So number of moles is equal to weight of substance upon its molecular mass. Molecular mass of pentene will be 12 5 is 60 plus 10 is 70. It will be equal to number of moles of bromine also. Number of weight of bromine, that is what you have to calculate. So weight in gram, you will find out this W. Upon molar mass of benzene is, it is given 80. So 80 into 2. So this is quite simple. This 0 0 got cancelled. So weight is coming out to 5 into 2 is 10. 10 into 8 is 80 by 7. But what is the integer type? You have to report the answer as 10 raised to power minus 2. So what we'll do is nothing. Just add 100 and your answer will definitely be coming in this term. Now this is our answer. Just into divide, approximate, and you will get your answer. Moving to this question, next question. So this is also our theory. Chlorine, when undergoes reaction with CCl4, sir, this is just vicinal dihalide formation. So chlorine will be adding up. So this B will be chlorine on vicinal position. B will be, no, it will be chlorine. It will be, yes, this can be good. This can be good. No. Now, sir, what about A? We have halogens can do substitution also, but at extreme condition of high temperature and sunlight. So this will be allylic substitution. So double bonded carbon, this is also allylic carbon, this is also allylic carbon. Now because both the option C and D are telling you 2 chlorine, sir, so if we do allylic substitution 2 times, so it will be happening doubly. So that's what it is telling you. This is also allylic substitution. No, this is not allylic substitution. This is allylic substitution. So we have got our answer. Moving forward. Now, moving finally, with questions only, I'm moving to alkynes. Because like alkanes, physical properties, the physical state, they are all the same. So we'll directly jump to preparation of alkynes. So let us summarize the physical properties with a JEE mains question. Sir, we know alkyne carbon is sp hybridized, so it is electronegative, it is polar, it is highly soluble as compared to alkenyl alkyne, and the shape, because it is sp hybridized, so it will be linearly shaped and will have 2 pi clouds. Because of the presence of 2 pi cloud, whatever reaction alkene was showing, it will be showing all those addition reaction, in fact to a larger extent, because here pi cloud is more, because it will be along x. Let's say bond is formed along z axis, so this is x axis, this is y axis. This is the beautiful picture which is showing you that pi cloud is surrounded in an alkyne to a higher extent. So this will also be attracting all those possible this E plus electrophiles. So these electrophiles will preferably attack alkyne, so they will just show all the reactions which alkene was showing. Now, doing this basic JEE question, it says the C bond of alkyne is shorter. Yes, sir, because as S character increases or as bond order increases, bond length decreases, bond becomes strong. So this is definitely correct. Question is asking you incorrect question. So this is definitely correct, so not an answer. Carbon is sp hybridized, correct, so not an answer. It is linear shape, correct, so not an answer. So obviously this is the answer, but let us check. Carbon bonds is weaker. No, because bond order is more, so bond will be strong. Moving to preparation of alkynes. So the preparation of alkynes are very short and sweet now, because very less in number. Actually, as per NCERT and as per JEE mains, 2 methods of preparation, from calcium carbide and from vicinal dihalides, will basically make your job done. Now, what is calcium carbide? Calcium carbide is actually an ionic salt with formula CaC2. But inorganically, you should know that calcium carbide is formed by decomposition of limestone, which is calcium carbonate. We know this reaction from class 10th. It forms calcium oxide, quicklime, and CO2 gas is released. If to that quicklime you add coke, carbon, that carbon will combine with quicklime and forms calcium carbide along with production of a poisonous carbon monoxide. But gas goes away. So this calcium carbide, sir, how to prepare alkyne? Put water in this calcium carbide. So when this calcium carbide takes water, now because we know it's an ionic compound, so calcium will take what OH of water, forms calcium hydroxide, but we are interested in this C triple bonded C minus, and these minuses will be taking hydrogen from water, giving rise to alkyne, the very first and very important methods of preparation. And the second method is, sir, alkyl halides, we have done beta elimination to form alkene. So if you have vicinal dihalide, do that beta elimination twice. But sir, over there you said we need a strong base. Yes. So use that strong base, alcoholic KOH, but it will be doing beta elimination one time. So you will be getting a double bonded carbon, but because I'm using a vicinal dihalide, so there will be one more halogen remaining. So in order to again perform beta elimination, you need an even stronger base. An even stronger base, now this is a experimental fact we should know. It is a common sense also, because in alcoholic KOH base was Ro minus. So the donor atom was electron rich, but it was oxygen. So if you use sodium amide, because alkali metals when mixed with ammonia form these amides. Now minus is on nitrogen. So nitrogen is relatively less electronegative than oxygen. So NH2 minus is even a stronger base. So now you need an even stronger base to do the same thing, beta elimination. This base will be giving electron to hydrogen, and this electron will be coming over here, and this bromine will be removed. So everything is just like beta elimination. Similarly, even it is also anti-elimination. If this bromine is going, then the hydrogen of the beta carbon of the next carbon will be of that carbon which is exactly opposite. Just the example of beta elimination, but since it is happening twice, so you will get your alkyne. If you use only alcoholic KOH, then also you get product, but percentage of product is very less. So NCERT has given this form that first you can use alcoholic KOH, but later you have to use a stronger base like soda amide. Now basically these reactions are done, but some preparations you can also predict through common senses. Like first of all, let me discuss about the second one. Sir, we have already seen that when we were trying to do preparation of alkenes, sir, vicinal dihalides when reacted with zinc can take that bromine and form zinc ZnBr2, remember, ZnX2, and was creating alkene. So use tetrahalogen derivative of alkane. So that tetrahalogen derivative of alkane will be removing this bromine also as ZnBr2 and this bromine also as ZnBr2, and will be introducing one more pi cloud. So that pi cloud will make alkene into alkyne. So tetrahalogen derivatives when react with zinc also forms alkyne. Now one factual thing you should know is, this is sometimes has been used. So this is a famous inorganic reaction but producing organic compound. If you use chloroform is an organic compound. But why I'm saying inorganic reaction? Because generally over here AgCl is a white precipitate which is an organic compound, and because AgCl gets precipitated out, so who gets combined? The carbon of chloroform. So stoichiometrically, how much silver is required? 6 moles of silver reacts with 2 moles of chloroform stoichiometrically, and you also get your acetylene gas, the smallest alkyne. Now one reaction, we have even performed this reaction through common sense, through mechanism in alkanes. Remember Kolbe's electrolysis? So sodium salt of carboxylic acid, now use a dicarboxylic acid but have unsaturation in between. So we know the mechanisms are CO2 will be released and a radical will be coming in this carbon. Similarly, this CO2 will also be released, a radical will be coming in this carbon. We have even done this question in alkanes. The radical chain termination will take place, and the alkene will be converted into an alkyne. So these are all preparation of alkynes. Moving to its chemical properties. So as we already know, these alkynes in fact will be having higher reactivity as compared to alkenes towards all electrophilic addition reactions. So whatever reactions alkene was showing, alkyne will also show. That's why I have made a beautiful picture for you, a handwritten picture, so that if you are falling short of time, these PDF will be acting as a notes for you. You can just revise these table and everything will be come to you whenever you need a strong revision, because time is less. Now, just the same thing. The first reaction is like alkenes hydrogenation, but we all already know it can be complete. You can form alkane. It can be partial. The Lindlas catalyst, the Birch reduction forming the cis and trans alkene. But obviously that will be possible when this particular, like for example, if you take propene, then if you take propine, then you do Birch or Lindlas catalyst, it will not even matter, because the alkene formed will be not capable of showing the geometrical stereocenter, because in this case both the hydrogens will be having same end. So those GOC common sense will be applied, but whatever hydrogenation we know we can do, and this will be a beautiful example of addition reactions. Now, the addition of halogens, sir, alkene used to form vicinal dihalide, so they used to form tetrahalogen derivatives. Okay, I'm sorry, over here obviously because they are formed, so this double bond, this bond will be going, so this will be, I just update this will be single bond. Okay, moving forward. Sir, moving forward, just like alkenes, Markovnikov addition of HX. So here also it will take place. First H plus will attack. So H plus will be attacking here. Why? Relatively, this will be a beta carbocation. So X minus will be coming to this place. When you get a double bonded halogen, generally it is termed as vinylic halide. I've discussed all these general namings in GOC1, but iterating again. So this is called a vinylic halide. Now, sir, but still there is double bond. Yes. So again add HX. Again H plus will go here. Negative part of attacking species C is going to that double bonded carbon which is having lesser number of hydrogen. So it is definitely a Markovnikov addition. But sir, that is a rule to just learn. Give us the logic. We already have the logic that if positivity will be coming over here, sir, this positivity will be resonance stabilized, because plus sigma bond lone pair is a resonance stabilized system. So therefore obviously this should happen also. This is happening also. So the dihalide that you'll be getting is a geminal dihalide. What is a geminal dihalide? When you get halogens, two halogens substituted in the same carbon. Moving forward, the other example of addition reactions being, sir, we added water also. So here also you can add water, but now here you have to be very specific, because NCERT gives this data. There also when we add water, we made the water acidic, because in order to initiate the reaction, in order to make carbocation, I need an attacking species H plus. Water is not an electrolyte. So the detail which you have to learn for addition of water in alkynes, the catalyst is obviously an acidic medium, but it is specifically you have to add few drops of concentrated mercuric sulfate and sulfuric acid. So HgSO4 and H2SO4, you have to slightly heat it to a temperature of 60 degrees Celsius. Although you can forget all these things also, but what you need to remember is you need water and it has to be acidified. So acidified water will do what? So again Markovnikov addition. First H will go here, OH will go here. Why? Because carbocation was stable. But here, sir, this is still 1 pi we have broken. It will again have 1 pi, more pi. Again GOC is required. This is enol form. This is enol form. So how enol form stabilizes itself? It tautomerizes. How tautomerizes? The hydrogen of alcohol goes to the carbon and the pi cloud transfers to the oxygen and it becomes a double bonded O, giving rise to a carbonyl compound. So in this case, what is formed? The smallest ketone, which is acetone. Now, sir, over there, alkene used to get polymerized. Here also they'll get polymerized, sir. But for that, we need them to learn temperature pressure. Sir, polymers is out of chemistry. So I'm just telling you, just like alkenes, alkynes also undergo linear polymerization under specific temperature, pressure, and catalyst. But Now, this is a very famous reaction. The alkyne, not all alkynes, but precisely I'm talking of the smallest alkyne, which is acetylene gas. When acetylene gas is passed through a red hot iron tube, red hot Fe tube, the tube is heated at a temperature of around 600 degrees Celsius, then the polymerization actually takes place in a linear fashion, because six-membered carbon ring is free from any type of strain. And sir, if six-member carbon rings are formed by each other, then what they will form? Sir, they will form an alternate pi cloud. That alternate pi cloud can be delocalizing in the whole ring, and therefore it will result in the formation of the famous benzene. And actually this is one of the preparation of benzene, also a very famous reaction. Moving forward, sir, why you have written capital A? I have written capital A in electrophilic addition because alkynes show one more type of reactions, which is the second type of reaction, a very small logic, which is acidic nature of alkynes. So how alkynes can be acidic? Because sp hybridized carbon is almost, the electronegativity in Pauling scale is 3.25, more than nitrogen. So nitrogen is acidic? Yes. Therefore this sp hybridized carbon is also acidic. But what does acid do? Acid can snatch electron, but snatch electron from the weaker section of the society. What is weaker section of chemistry society? Hydrogen atom. So terminal alkynes, mind you, terminal alkynes. What are terminal alkynes? When the sp hybridized carbon is present at the terminal position, then only this guy will be in a position of this acidic hydrogen. So only terminal alkynes show obviously acidic reaction. Although it is acid, but it is not a very strong acid. So it cannot react with the base, because actually this terminal alkyne is a weaker acid than water. So who does neutralization? All those acids does neutralization who are stronger acids than water. So therefore it does not go simple acid base reaction, because acid base forms salt and water. So who undergo neutralization? The acid which are stronger than water. This is not stronger than water, but still contains acidic hydrogen. So weaker acids reacts with what? So they react with active metal, forms salt, and the hydrogen is released in form of hydrogen gas. The salt that is formed, the general name is alkynide, because we have used propine, so it is propynide, sodium salt of propynide, as in sodium propynide. Now, sir, if we have seen in preparation of alkynes, the very strong base, sodium amide, NaNH2. NH2 minus is even a stronger base. So this stronger base can also react with terminal alkyne. The NH2 minus will take away the H plus of terminal alkyne and forms ammonia gas. It will be released. What is left behind? The salt. Again, the sodium salt. Now, one more very important acidic nature, Tollens reagent we'll be discussing in carbonyl compounds. It is freshly prepared solution of ammonium nitrate and in excess of ammonia. Now this solution, what is the active ion, the active species, sir? The silver metal. The silver is in positive +1 oxidation state, and it forms a beautiful complex with 2 ammonia. The coordination number is 2. This is the active ion of Tollens ion, which actually performs reaction. Actually Tollens test is given by carbonyl compounds, but this terminal alkyne, due to presence of acidic hydrogen, this terminal alkyne also reacts with Tollens reagent and forms a salt. Although silver salt has covalent nature, that's why over here I have given minus plus, but over here I have shown this bond. The oxidation state will be same only. The silver is in +1 state, carbon is in -1 state, but this salt is having covalent character, and because it is having covalent character, so it will be precipitated. So this is even seen as a white precipitate, and whatever you see, that reaction can act as a test. So this also confirms the presence of a terminal alkyne, the formation of a white precipitate by using Tollens reagent. You again get ammonia and water in case of terminal alkynes. Now quickly moving to, because we have recently discussed formation of benzene. Now sir, what about the physical properties? What is aromaticity also you should see from GOC1, because that is also a very important topic, and all aromatic compounds follow a definition of Huckel's rule, which we have already discussed. Please invest again these 20-30 minutes in GOC1, where you will be seeing all the aromaticity and the basic definition of aromaticity, the resonance which makes aromatic compounds stable. One of the most famous aromatic compound is benzene, and benzene and its derivatives we will be discussing in hydrocarbons, because obviously it is a hydrocarbon. What about, sir, its physical properties? Its physical properties is also just the same. Just we should why they have got the name aromatic, because in the aroma means generally all these aromatic compounds have got characteristic aroma smell. Therefore, they are called aromatic. Next is whenever benzene ring are fused together. So fused benzene rings have a chemical property, although it is a chemical property, but I'm generalizing it in the physical side only, that they are carcinogenic. Carcinogenic compounds are cancer producing. So I'm not writing all these stuff, but this is all basic. If you go to GOC, you will get to know. Now, so what is important over here? Their preparation and chemical properties. So coming to the preparation, very small, only 3 preparations, and that also you already know. Sir, cyclic polymerization of acetylene. Now, you can also reduce phenol, but phenol cannot be reduced by any and everybody. It can only be reduced by zinc and heat it, because zinc will take away the oxygen of phenol and forms zinc oxide. Removed this hydrogen, because benzene is C6H5, because valency is free over here. So this is phenylic group, not actually benzene. When this hydrogen is carried by this carbon, it becomes perfect C6H6 benzene. So the second preparation of benzene. And the last preparation of benzene, we also know it is soda lime decarboxylation. But use what carboxylic acid? Use a benzene derivative of carboxylic acid, as in benzoic acid. So when salt of benzoic acid, which is sodium benzoate, reacts with soda in presence of lime, lime is used to keep the mixture dry, again because we want this NaOH to react with this. NaOH is hygroscopic. You heat it, this whole thing will be released. The CO2 will be released in the form of Na2CO3, and you get your beautiful benzene. Moving to the chemical reactions of benzene. So the first and most frequently asked reactions of benzene are electrophilic but substitution, because like alkene and alkyne, benzene ring having this pi electron cloud, we know this pink, this pink, this pink, and this pink are alternate positioning of pi cloud. Similarly, this green, this green, this green is also the alternate positioning of the pi cloud. We have already discussed in GOC that they have a stable aromatic nature. So because of the stable aromatic nature, they will definitely entertain and allow an electrophile, that a electrophile, come to us, because we are rich in electrons, so we are minus, so we will definitely attract plus. But they will not undergo addition, because then addition will make their aromaticity destroyed. So if I am very aromatic stabilized, the extreme resonance stability, then why will I deform my aromatic nature? That's why they allow the attack, but one hydrogen gets substituted. One hydrogen of C6H6 gets substituted, so it becomes C6H5, and the electrophile makes an electrophilic substitution. Now, what are the most famous reagents and who all are the electrophiles? I have made a beautiful picture. So let me take out this laser, because if you are actually not confident in hydrocarbon, then I am suggesting you, I have done for you, I have done the work for you. You can obviously download the PDF, and these will be acting as your class notes. Just take this picture and it will be helping you, because if you will read from one place again and again, then only it will come in sync. Because our memory, we always, like when you give an examination, if you have not revised well, maybe your 10th board examination, some of you can relate, something was written on left side of this copy. You remember the place, but you forget the content because of less revision. So that's what I'm saying, we have a photographic memory. So that's why I'm not disturbing these notes, and I've written them properly so that they can even serve as a class notes for you, because at this point of time I understand you cannot write them, and you do not even have to write them. That's why I made them. Now, What are the list of common reagents? Sir, there are actually 5, but I have written 6. Now, what are these? The reagent and the electrophile that will be creating the aromatic substituted product. So the first is sulfonation of benzene. What is the reagent of sulfonation? Oleum. What is oleum? Fuming sulfuric acid. Like the villain of old Hindi films used to go to heroin with a acid. The acid used to give fumes. That represents it is a highly concentrated sulfuric acid. Actually, inorganically, it is nothing but H2SO4 mixed with SO3. So the SO3 gas actually makes it super concentrated, because that SO3 can further take water and will not dilute H2SO4, because SO3 plus H2O will further become H2SO4. So that is an inorganic knowledge. So I have written that also, that oleum is H2SO4 plus SO3. So what electrophile it furnishes? It furnishes you the sulfonic acid group, that is SO3H. So the substituted product after substitution of hydrogen that you get is benzene sulfonic acid, that picture. The next reagent is the next example of SE reaction is nitration of benzene. Now for what is the reagent for nitration? Concentrated HNO3 in presence of concentrated H2SO4. It creates an electrophile which is NO2 plus. The NO2 plus gets substituted and you get a nitrobenzene. Now then the two reactions are halogenation, but I have written them separately because among halogenation from alkanes we remember F2 is violently reactive, so we do not do. I2 is very slow, so we do not do. So the most famous halogenating agents for us are chlorination and bromination of benzene also. Reagent, you just need to break the X bond, and how will it be broken? You have to use a metal or its salt, because that will be metal. What metal? D block metals like iron. Salt like FeCl3, because D block cations and D block metals have empty d orbital. Empty d orbital can accommodate electron, and because of accommodation of electron they behave as Lewis acid, because I can accept electron. So if I accept, so let's say 1x gets broken in form of X minus attracted by that Lewis acid, so an electrophile X plus is created, and that X plus can substitute the benzene ring as chlorobenzene and bromobenzene. Now the last two reactions are Friedel-Crafts reaction, which is just the same logic. Friedel-Crafts used a Lewis acid of anhydrous AlCl3, and hence it goes by its name, that is Friedel-Crafts. Now if you have a Lewis acid, preferably in questions what halogen you take, generally they serve you with chlorides. So if you take any alkyl chloride, this R bond, this Cl bond, the Cl takes away the bonded electron as Cl minus in influence of this Lewis acid, which is AlCl3, giving rise to carbocation, that is R plus. So this R plus gets substituted and you get your beautiful alkyl benzene. General names we have discussed in GOC for aromatic compound. General name are very famous. Let's say this R is a methyl group, so methyl benzene is also known as toluene. And what is Friedel? That is Friedel-Crafts alkylation, that is substitution of an alkyl group. Now last is Friedel-Crafts acylation. What does acylation mean? Substitution of an acid group. What is the acid? Acyl group. Acyl group as in carboxylic acid. Remove OH of carboxylic acid, what you get? The alkyl group, the carbonyl carbon with a double bonded oxygen. The carbonyl carbon gets the plus. Why? Because the reactant over here we use is an acid chloride. The chlorine under the influence of Lewis acid forms an electrophile, and the substitution takes place and you get an alkyl phenyl ketone, because the carbonyl functional groups has alkyl groups on both the sides. If this R is CH3, that is you have taken an chloride of acetic acid, that is you have acetic acid derivative of chlorine, then it is an acid chloride of acetic acid. So this will be CH3. So what is the general name of this? If it is CH3, it is generally known as acetophenone. So these common names are very, very crucial, very, very important moving forward. Now, sir, we have to just remember those 6 reactions. Yes, definitely yes. But again, mechanism is also important, because question tricks you with mechanism as well. So mechanism of SE reaction is basically a 3-step process. Step 1 is Generation of electrophile, we have already spoken about it, but let me give you the brief also. Like in sulfonation, what is the electrophile? Sir, it has sulfuric acid, only sulfuric acid. So sulfuric acid molecules interact with each other, obviously give the solution is acidic, so one molecule gives H plus, forms bisulfate, the other molecules releases. I've marked this hydrogen and this OH because they will be producing H plus. H plus in a solution exists as hydronium ion. What is left behind? SO3. Sir, but SO3 is neutral. Look at the sulfur. Sulfur has an oxidation state of +6 because it is under influence of 3 electronegative oxygen. Obviously, the sulfur is sp2 hybridized, having a trigonal planar structure. So this trigonal planar sulfur at the center will be attacked by the benzene ring cloud. So if someone is asking you in sulfonation, what is the electrophile? It is not charged. It is uncharged. But still that uncharged sulfur is having +6 oxidation state, which is its maximum oxidation state, and hence it is becoming acidic. And moreover, sulfur has empty d orbitals as well, so it can accommodate the incoming electron of benzene. So the electrophile for sulfonation is not a charged electrophile, it is SO3 group, a very important point. Now nitration, sir, how electrophile is generated? I mean, this is quite clear. H2SO4 is a stronger acid in comparison with nitric acid, gives H plus. Nitric acid furnishes OH minus ion, produces water. HSO4 minus gets separated out. It will not interfere because minus minus repel each other. Why will it approach benzene ring? So who will approach benzene ring? The plus. Obviously, you can see nitrogen got the positive charge. So this NO2 plus act as your electrophile. Moving forward, sir, what about halogenation? I've already discussed. We take a Lewis acid, XX bond breaks and you get X plus. Sir, what about Friedel-Crafts reaction? Again discussed. Lewis acid taking the Cl, creating R plus, creating plus on the carbonyl carbon of the acid group. So Friedel-Crafts alkylation and acylation, sir. But this is just step 1. Yes. Step 1 is first you have to generate the electrophile. Now the electrophile plus is generated, so plus will attract minus. What is minus? Benzene ring. So this minus, that is pi cloud of benzene ring, will attack electrophile. What will happen? Electrophile gets attacked and attached. The attack and attach take place. This is the photo. But sir, this rhenium ion is not aromatic stabilized. I definitely understand the aromatic nature is lost. That's why it will be regained soon. But whatever the rhenium carbocation, this carbocation you have formed is not unstable. It is not a poor carbocation. It is also very stable. Although not aromatic stable, but still it is also very stable because this is also resonance stabilized. How, sir? This is positive charge. So this plus can be delocalized in the ring till this carbon. So it is still having a delocalization, an extended delocalization, although not cyclic, because this carbon will be stopping the complete delocalization. But still, this plus is carried by, is taken by, is shared by the 5 carbons, not the 6. So my point is, rhenium carbocation is also not unstable. It is also resonance stabilized. Yes. Still, it is not aromatic. So what will be the next step after the attack? Sir, the rhenium ion will attain aromaticity. How? This hydrogen which was there, which will be there where electrophile has attached, its electron is taken by the adjacent carbon and you will beautifully regain your aromaticity. Hence, it is not addition, it's a substitution reaction and you get your substituted benzene. Now, coming to the derivative influence of groups. So just to be time efficient, which we have already exceeded, but the benzene derivatives also, so benzene ring is there, so it is still electron rich, so electrophile will approach. But if these benzene derivatives, as in if they are substituted by a group which can show in GOC, we have done the electron displacement effect. If they have electron donating groups like this OCH3 when attached with benzene makes it anisole. This CH3 when attached with benzene makes it toluene. applying hyperconjugation, this OCH3 applying plus R. So all these atoms attached with the ring who has the capacity to give electrons will activate the ring. And remember, resonance and hyperconjugation all are operational at ortho and para position. So they will create an excess of electron density where at ortho and para position. And because they have excess of electrons over there, so these electrophiles will be feeling happy, activated, like you having food at home but friend calling you, there's a paneer party or pizza party, you will leave the food at your home and you will be feeling activated to go to the place. Similarly, the electrophile that would be creating, let's say NO2 plus in this case, will be going to ortho position also and para position also. Why? Because the directive influence of these plus R and plus hyperconjugating groups are obviously ortho and para, because they create electron density due to resonance and hyperconjugation. Now, one more point which will also be repeating in the later chapter of organic chemistries, but learn it over here. I have therefore curated this slide to be time efficient and make these slides as your revision slides. You do not have to write them. If you're learning for the first time, around the first time, then these slides will definitely help you. I'm not making them bad also. That's why I'm using a laser now. One more thing you need to understand, and it's a common sense also, when you have substitution at ortho position, bulky groups are closer to each other, so nucleus will be repelling each other, and because of the steric hindrance, generally this ortho isomer is produced in a smaller amount and hence called the minor product, and the para isomer generally becomes the major product. Now, one more example, application of GOC. If we have phenol, sir, phenol is also not having any vacant d orbital, so it is also plus R. Actually, the plus R of OH is much larger. So because plus R is much larger, therefore electron density at ortho and para position is also much larger. In such cases, it has been experimentally observed. It is common sense also, because electron density is highly increased. You have food at your table, but if someone is calling you and offering you pizza and money with it, you will definitely rush to that place. Similarly, when such a strong activating group is present, this can also be seen by the reagent. You do not have to use an acid like HNO3 and H2SO4. HNO3 is still an acid. It is forced to give OH minus, and the force is done by the concentrated sulfuric acid, which is a strong acid, then HNO3. So H2SO4 produces H plus and forces HNO3 to produce OH minus and forcing the production of NO2 plus. Similarly, in Friedel-Crafts reactions, the halogenations, why we use Lewis acids? Because we are forcing the electrolyte to be formed. But when the electron density has been such tremendously increased, I do not even have to force the creation of electrophile. Even if I use dilute HNO3, no H2SO4, even concentration of HNO3 I have taken dilute, still it will itself break and furnish those NO2 plus ions, and they will be attaching to obviously ortho and para position. Now, because I have used dilute, so HNO3 is lesser in number. Therefore, the produced NO2 plus electrophiles will also be lesser. Therefore, you have mono-substituted product at ortho and para position. But rather, if you use concentrated HNO3, HNO3 is anyway feeling very much activated because of the presence of this highly activating electron donating group, which is creating huge amount of electron density at ortho and para position. Therefore, this is a very beautiful fact of NCERT, although of class 12 phenols. But this is a common sense we are deriving from GOC and hydrocarbon basics, that these NO2 plus are so much willing to be getting substituted at ortho and para position that you take larger concentration, as in if you use concentrated HNO3, no H2SO4, still NO2 plus produced and produced in heavy amount and will be getting substituted in all the possible positions. So you will get a tri-substituted phenol, which is also known as picric acid. Now, one more chemical bonding logic, GOC logic. Generally, ortho is the minor product as over here. But because of intramolecular hydrogen bonding. Intramolecular hydrogen bonding is always applicable when there is formation of a cyclic ring. So this orthonitrophenol forms a cyclic ring. So practically we say that no, because that ortho product is not sterically hindered, it is in fact stable, therefore its percentage will also increase, and NCRT reports that we get a mixture of product. Why mixture? Because its concentration, which is expected to be lesser, has been drastically increased. So this is formed somewhere around 30-40%. Depends on the situation of how much dilute HNO3 you have used. So it is not, NCRT has also restricted itself by writing the concentration percentages, and generally it is around 30 to 40%, and generally someone is asking you if the option are telling you it is in fact rather can be even called as the major product. But to be safe, what we say is mixture of them are produced, because ortho you were not expecting to be produced, but it is producing to a larger amount. So we say mixture of ortho and para isomers are produced. Moving forward now. So activating, you have so deactivating also, yes, if you apply minus R, but sir, resonance is always operational at ortho and para position. So if I withdraw electron, if I apply minus R, I may be having vacant d orbital, so I'll be withdrawing electron cloud of benzene, but still resonance will be operational at ortho and para position. But because I'm withdrawing, so positivity will be coming at ortho and para position. But still, at first place, one pi cloud is removed, other pi clouds will still be there. So benzene will still be having those pi electron clouds, but maximum of the electron density has been removed. So electrophile will not be that much feeling comfortable, because anyway this benzene is like a situation which we have also discussed in GOC, like you have not eaten for like 10 days. Now, if I offer you two roti, two chapatis, even though those two chapatis you will take. Similarly, if at all electrophile is produced, sir, in the previous slides we have seen, you use reagent to force the electrophile to be produced. So we are forcing electrophile to be produced. So if any of these electrophiles are produced, and yes, in this case we will be definitely requiring all those Lewis acids, all those catalysts which will be forcing the production of electrolyte, because electrophile is not feeling good, it is not feeling activated, this is not electron rich. But if at all I'm produced, so I'm plus, I'm having deficiency, but I'm not activated. So that's why the term the deactivating groups. And who all are deactivating groups which apply minus R? The famous example of deactivating groups are all those groups which have carbonyl group, because carbonyl carbon will through resonance will snatch away the pi electron cloud, creating a positivity in carbon. The vacant orbital of carbon will always be making it electron withdrawing through minus R. So whatever aldehyde, ketone, carboxylic acid derivatives, acid halides, whatever you will be having, all will be electron withdrawing group, deactivating group towards electrophile. Electrophile would not be very much interested, but if at all it is formed, it will attack where? Because resonance is operational at ortho and para position. So what is the position which is relatively having minus? Sir, at least benzene is electron rich, the pi cloud is still there, some of the cloud has been removed, but two pi bonds will definitely be still remaining. If you draw the resonating structure, please go to GOC if you're feeling uncomfortable with this, because definitely after that, after seeing that GOC, the aromaticity, the resonance, you will definitely feel comfortable. So now, because positivity is there in ortho and para position, so they will acquire this meta position. But single mono substituted product, because I'm not very much interested, so meta substituted product you will be having. So these are the directive influence of these groups when they are attached to a benzene ring. Now, in the next chapter also, we'll be discussing it again, what these groups. There are some groups like halogens which apply plus R also because they have lone pair, but because they have empty d orbitals also, so they will apply minus R also. So these group apply both plus R and minus R. Moreover, these halogens are strong electronegative elements, so they'll be having minus I also. So overall, when these halogens are connected to benzene ring, they ultimately removes electron. So if I remove electron, I'm activating or deactivating? Deactivating. So electrophile will be activated or feeling deactivated. So not good, not feeling happy, very much happy. But if at all I'm produced, I'm hungry, I'll take those two sukhi roti, 2 rotis, 2 chapatis. So where I will but. Now this is the halogens are deactivating groups. But what about if at all this electrophile is produced, where will it be directed? It will still be directed at ortho and para position. Why? Because if you just see, ultimately they are plus R groups, but their minus R and minus I are more dominating while deciding that whether they are activating or deactivating. So definitely they are ultimately electron withdrawing. But if at all an electrophile is produced, it will fractionally see if I offer you 2 chapatis 3 days old, or if I offer you chapati only, no sabji, but this morning. I mean, this morning chapati will also be very, I mean, if this is night, and if I made 2 chapatis in the morning, but another option I made 2 chapatis 3 days back. So relatively those 2 chapatis of today morning, they are less older, so you will be preferring that one. Similarly, electrophile not feeling activated, but instead of meta, which is not at all having any minus, for some of the times it will be having few minus also because of plus R at ortho and para position. So these mysterious groups, chlorine, bromine and iodine. Why not fluorine? Because fluorine has no vacant d orbital, it cannot apply minus R. So chlorine, bromine and iodine, these all are electron withdrawing groups, but if at all electrophile is created, the directive nature is again ortho and para, where para becomes major product because of lesser steric hindrance. Now, these aryl halides like chlorobenzene, we will again be discussing this in alkyl and aryl halides, but learn here only because these are all NCERT facts. Now, if this chlorobenzene, let's say if we know this, sir, so if this chlorobenzene is reacted with Cl2 in presence of Lewis acid, what you will get? Sir, we will get ortho and para substituted product. Major product will be para because lesser steric hindrance. But what if I use this chlorine in excess? Then this electrophilic substitution will be happening again. So if we increase and excessively do this chlorination, then obviously every hydrogen will be substituted and you get C6H6, which is hexachlorobenzene. Now, one thing is, whenever you see chlorination and bromination as in SE reactions of chlorination and bromination, generally question tricks you by writing this dark and cold. Why this dark and cold? This brings us to the last slide of our hydrocarbon, which is sometimes addition reaction are also seen. Sometimes, because sir, alkanes, even you said alkanes are paraffins, they do not react, but you have shown us so many reactions. So if you create some vigorous condition, then obviously everybody is forced to, we as humans, we are organic compound, we do not support combustion. But even if you put my body on a pile of wood, put ghee, so after I'll take 2 hours, but even I will burn. So similarly, if you create vigorous condition, everything is gonna react. So there are few addition reactions also. And when this halogenation, coming to this halogenation, yes, when this halogenation, as in you use Cl2 but not dark. Why dark is written over there? Dark represents there should be no sunlight, because when this halogenation takes place in sunlight, actually addition reaction takes place, because that becomes a vigorous condition for these aromatic compounds. And what under vigorous condition, what they will do, they will lose their aromatic nature and addition reaction will take place. So if this is C6H6, then in presence of sunlight at around 500 Kelvin temperature, addition takes place, that is hydrogen is not removed. So the product is C6H6Cl6, hydrogen is still there, but in bond line projection it is not shown, but you should definitely know, because there is no pi bond, there is no delocalized gola circle, so there is hydrogen also. This is C6H6Cl6, but although this is hexachlorocyclohexane, 1, 2, 3, 4, 5, 6 hexachlorocyclohexane, but it is generally termed as benzene hexachloride, because Obviously, it can also show geometrical isomerism because the ring chlorine can be up and down. So, but that is an advanced topic. I'm just telling you one thing, that its isomers, the benzene hexachloride, why it is named, although it is not benzene, but still named benzene hexachloride, because its isomers are very famous insecticides, which are also known as gemexane and lindane. So, a very important fact for JEE mains. Moving ahead. So if I create vigorous condition, then hydrogenation can also take place. Yes. So at vigorous condition, at around if you heat at around, some references say 170 degrees Celsius, some references use higher temperature. So I have not mentioned the temperature, not very famous reaction as per mains. But you can also, at extreme condition, you do hydrogenation also, so it becomes cyclohexane. Now advanced loves it. All for mains you can leave it, but still one reaction I'm adding. Benzene is actually a thermodynamically stable product. Obviously, we know that because pi cloud is resonance stabilized, so it is thermodynamically stable. We have discussed in alkane. What does Birch reduction tell you? If you subject benzene to sodium in presence of solvent like ammonia or alcohol, methanol, Birch reduction takes place, which leads to the formation of this alkene, which is a kinetically stable product. We can, like the addition we have done for dienes, this can also be done, but that will be also an advanced topic, and already we have exceeded a lot of time. So this is me, Gaurav Singh Arora, signing off with the advice of to you is, go to the description section. Please download and attempt those questions and revise this as many number of times as you can. If you do not have notes, use them as your notes, because that is the extra work that I have done for you, that I have written these notes so properly, so that those of you who are not having time to write and you are reading it for the first time, this can also act as a notes for you, which will help you to revise and secure a better rank. This is again me signing off. Thank you. We'll meet in the next one shot. Bye-bye.